Quand vous tournez Isabelle Huppert, le juge et l'assassin avec lui en 1976, vous êtes toute
Hello, everyone. I will begin. And welcome back. We will continue our sessions. And now let me introduce our next session chair. Okay, let's welcome next one.
Hello, good morning. Good morning, everyone. Good day. I cannot share my screen.
Sorry.
That's okay. So I'm very happy to join you here at MICAD 2020. First, a small word about me. I am Nashwa Baker. I'm postdoctoral researcher at INRIA Grenoble Alpes from France. And my research interests are computer vision and deep learning. Here's my webpage. Don't hesitate to contact me. So in this oral session, we're going to talk about medical image segmentation, registration, and reconstruction. We will have 1 hour of oral session, and we will have 5 interesting papers. Just a gentle reminder, each paper we will have 10 minutes and probably 2 to 3 minutes for questions. So without further ado, let's invite the first speaker, Rinka Sharma from University of South Pacific in Fiji. Please start your presentation.
Hi there, I'm trying to share my desktop. Just give me a second.
Yeah, take your time.
Thank you. Good morning, everyone. I am Priyanka, and today I'll be presenting to you on the art of hyperparameter optimization with desirable feature selection. With me in this research, I have Dr. Kailash Chaudhary and Associate Professor MGM Khan. We are from School of Information Technology from University of the South Pacific, all the way from Suva, Fiji. So our outline for this presentation is organized as we will begin with introduction, followed by our aim, objective, a little bit of background with problem statement, our data set information, experiment setup, results, and finally conclusion. Moving towards our introduction. Our introduction is more grounded on towards machine learning algorithms. So in fact, machine learning algorithms are used everywhere from a smartphone to a spacecraft in current modern era. So these algorithms automatically adjust or rather learn their internal parameters based on data. However, there is a subset of parameters that is not learned in fact and have to be configured by an expert. Now, such parameters sometimes or are referred to as our hyperparameters, and they have a big impact on our life as we use AI in our daily activities. The performance of our model can drastically depend on the choices of our hyperparameters. So since the goal of an algorithm is grounded heavily or rather dependent on the data types and the data volumes that rather change from one project to another, there is no single best choice for hyperparameter volume or other values that fits all models and all problems. Instead, hyperparameters must be optimized within the context of each machine learning project. And therefore, our figure 1 shows the portrayal of the HP schemes that we have utilized. Our aim was, in fact, to control an automated approach in utilizing optimization possibilities, meaning we deliberate more about the issue simultaneously, choosing a learning algorithm and its hyperparameter going past work that usually tends to address this issue in isolation. We have showed that the issue by completely automated approach utilizing ongoing developments in machine learning. So our research objective was to actually locate the current model coherence between the prediction identified and the estimated errors. We had a problem statement which highlights that in many cases, there is huge assortment that is needed in applying machine learning, and this is particularly important in context of our AutoML. So in order to approve the performances of machine learning is not simple by just tailoring them to a problem by hand at initial stages, but rather with the proofs that different methods can be compared fairly if all they receive the same level of tuning problem by hand. So currently every machine learning system has its hyperparameters, and most basic task in automated machine learning, known to be as AutoML, is automatically set these hyperparameters to optimize its performances. The same kind of machine model eventually can require different constraints, for example, weights or learning rates to generalize different data patterns. Now, these measures are called hyperparameters and have to be tuned so that the model can optimally solve the machine learning problem. The hyperparameter optimization finds a tuple of hyperparameter that yields an optimal model which minimizes our predefined loss functions on given independent data. So the objective function takes a tuple of hyperparameters and it retains the associated loss. And henceforth, we have used cross-validation to estimate this generalization or general performances at this point in time. Our dataset information is as portrayed in table 1. The experiment, this experiment dataset was actually downloaded from virus shareware, a website that keeps up a continuously updated database of the malware. So to analyze these samples, the initial researchers, they used Cocoon Sandbox just to automate this analysis. And henceforth, we acknowledge Dr. Daniel for his data sharing. Moving on to our methodology, or rather the experimental setup. So figure 2 shows the optimization strategy that in fact we utilized. So we can say that a typical optimization procedure just defines the possible set of hyperparameters and the metrics to be maximized or rather minimized for a given problem. Therefore, our method of, or rather for optimization procedure follows these classical steps as depicted in the diagram, which is figure 2. And we have utilized the WECA tool. So to achieve the objective of this research, the classification method on ransomware detection data set were applied through WECA environment. And WECA, what is WECA? WECA is the best state-of-art facility for making machine learning systems and the applications to genuine information mining, such as anomalies. It comprises ML algorithms for information mining assignments, and WECA executes algorithm for information pre-processing, such as classification, regression, clustering, association rules, so on and so forth. So moving to our results, that was the test control as portrayed in table 2. We used that tuning test control, and we have, so we determine the most relevant features through the knowledge based on the data observation. And we have used the feature evaluator as gain ranking filter, and evaluation mode was evaluating on all training data set. And we managed to get out from our result the most relevant features of each class, which is depicted in figure 3 that shows the most relevant features out from all for each class. So table 3 was the final optimum result that we obtained, whereby in each we have tested 10 algorithms in total with HPO and without HPO. So there were actually 14,631 extracted features with 1,522 instances that were initially loaded. However, a total of each ML algorithm or rather 6 algorithm configuration were evaluated 50 times with 5-fold cross-validation multiplied by 10 repeats. And then we compared the algorithm configuration based on the percentage of accuracy. Thus, the results that we achieved were impressive, right? And 10 ML algorithms in total were used for this research. Furthermore, feature ranking and file transformation in ARFF were further performed with, again, Weka tool. So in each model analysis, we set the K value, which was 10, and it encapsulates the number of base classifiers. And henceforth, we took n is equal to 5 for cross-validation and weight assignments independently. So to achieve the best outcome, feature selection method along with tuning methodology, as shown previously, made an impact on the performance level of the land model as portrayed in table 3. So finally, the conclusion, the results just shown in table 3 demonstrate that AutoWeka is ineffective at optimizing its given objective function. However, this is not sufficient to just allow us to conclude that it fits model that generalize well. So as the number of hyperparameter of a machine learning algorithm grows, so does its potential for overfitting. The use of cross-validation substantially increases AutoWeka's robustness against overfitting, but since its hyperparameter space is much larger than the standard classification algorithm, it has an important to carefully study whether or not to an extent of overfitting poses a problem. So finally, to conclude, AutoWeka makes it simple for non-specialists, for example, our novice researchers, especially to assemble great classifiers for any application situations just to reduce time and resources. So thank you so much. That was a short presentation by me. And if you have any question, clarifications, please feel free to email me on priyanka.sharma@esp.ac.fj or either contact me. So thank you so much for today. Thank you.
Thank you, Priyanka, for the presentation. Indeed, the hyperparameter optimization is an important aspect of machine learning design, and it's almost important in every domain that uses machine learning. So let's see if we have questions from the audience. Please, if you have questions, post them in the chat or in the Q&A section. I have a small question waiting for others about the AutoWeka. So is the AutoWeka available? Is it an open source tool? Priyanka?
Thank you, ma'am, for your question. Yes, it is an open source tool which was initially initiated by a university in New Zealand, Waikato University. So it's very easy and efficient, widely available, just to use, just to start off. This is, I would recommend for our novice researchers at early stages. I think it's at this point in time, it works very well for analysis purposes. Thank you.
Okay, thank you. So we have a question? No. Okay, let's move to the next paper then. I'll invite the next paper. The paper is Dual Supervision Guided Attentional Network for Multi-Modal MRI Brain Tumor Segmentation. And the speaker is Tong Zhu from University of Rouen in France. Please start and introduce yourself. Thank you.
Okay. Can you hear me?
Yes.
Okay, I will start. Hello everyone, I'm Tong Zhou, a PhD student at University of Rouen-Normandie. I'm the first author of paper, a dual supervision guided attentional network for multimodal MR brain tumor segmentation. Today, on behalf of all the co-authors, I will present our work. The presentation is divided into 5 parts. introduction, proposed network architecture, implementation details, experiment results, and conclusion. At the beginning, I will give you some backgrounds about brain tumor segmentation. Well, brain tumor is one of the most aggressive cancers in the world. Early diagnosis of brain tumors plays an important role in the clinical assessment and treatment planning. While multimodal images can provide the complementary information to improve the segmentation accuracy. However, brain tumor segmentation is still challenged by the various brain anatomy structure, low image contrast, and fuzzy contour. Here I show you 4 brain MR images with the real annotation from breast 2019 dataset. So in this paper, we propose a dual supervision guided attentional network for multimodal brain tumor segmentation. Following that, I will show you the details of our proposed network architecture. Well, the proposed network architecture consists of 4 parts: encoders, dual attention fusion block, decoders, and the 2 deep supervision paths. Here, the 4 encoders are used to extract the individual features from the 4 different modalities. To obtain the most important features, a dual attention fusion block is introduced. It includes a modality attention module and a spatial attention module. They can reweight the features according to their contribution to the final segmentation, so as we can get the fused feature. And finally, the fused feature is guided by the 2 deep supervision paths to obtain the final segmentation. Here, the first deep supervision path is the reconstruction path, and the second deep supervision path is based on the spatial attention module. We first extract the spatial attention features from the different levels, which are denoted as FSN, FSD, until FSL. And then we use these features to predict the segmentation result. Finally, all these multi-skew segmentation results are combined together to get the final segmentation. Okay, here are the details of our proposed network. Next, I will show you the details of the dual attention fusion block. The dual attention fusion block includes a modality attention module and a spatial attention module. First, a concatenation is used to combine the 4 individual features, and then they are passed to the dual attention fusion block. On the top is the modality attention module. A global average pooling is first used to transform the individual features to 4 hidden nodes, and then a fully connected layer is used to get the modality weights. On the bottom is the spatial attention module. A convolutional layer is used to get the spatial attention weights. Finally, the 2 sides of weights are multiplied with the input feature to get the attentional features. And then the attentional features are added together to get the fused feature. So in this way, the network can weight the feature representations from the 4 modalities according to their contribution to the final segmentation. Well, we evaluate our method on breast 2019 dataset. In this dataset, there were 335 training data. There were 4 modalities, T1, FLAG, T1C, and T2. And there were 3 segmentation classes, including whole tumor, tumor core, and enhancing tumor. We crop and resize image to 128. Bayes field correction is used to correct the distortion of MRI data, and intensity normalization is used to normalize each image. And the loss function is combined by the dice loss and the mean absolute loss. To evaluate our method, we use 2 metrics, dice similarity coefficient and Hausdorff distance. Now let's check the experiment results. We first did the ablation experiments to demonstrate the effectiveness of our proposed components, including the dual attention fusion block and the dual supervision strategy. Here, the baseline denotes as our proposed method without the dual attention fusion block and without the dual supervision strategy. From this table, we can observe that the proposed components can gradually improve the segmentation results, which demonstrates the effectiveness of our proposed components. And then we compare our method with the state-of-the-art methods on breast 2019 validation dataset. And we can see that our proposed method has a better result. In addition, we visualize the segmentation results. And here, the first column shows the results from the baseline. And then we gradually add the proposed components, including the dual fusion block, spatial attention-based supervision, and the dual supervision strategy. So the fourth column shows the results of our proposed method, and the last column shows the ground truth. And here, the green box highlights the missegmented regions. So from the visualization results, we can also see that the proposed components can gradually improve the segmentation results. Furthermore, to demonstrate the effectiveness of the dual supervision strategy, we visualize their feature maps. Here, the first row shows the ground truth and the prediction. And the first column shows the 4 different modalities. And the next 5 columns shows the feature maps from the spatial attention-based supervision from different levels. And the right part shows the reconstruction results. So from the left part, we can observe that thanks to the spatial attention module, the network can learn the tumor-related features to improve the segmentation result. And on the right part, we can observe that our method has a good reconstruction result. So we conclude that the proposed dual supervision strategy can enable the network to learn the discriminative features to improve the final segmentation result. So in brief, we propose a dual supervision guided attentional network to do the multimodal brain tumor segmentation. The proposed dual attention fusion block can emphasize the most discriminative features from different modalities, and the dual supervision strategy can help the network focus on the regions of interest. And the experiment results evaluated on breast 2019 proved the effectiveness of our method. And here are the related references. Okay, that's all about our paper. So thanks for your attention, and please feel free to ask questions. Thank you.
Thank you, Tongzu, for the interesting work. Let's see if we have questions from the audience. Please don't hesitate to post your questions in the chat. I have a small question about the deep supervision of the spatial attention part.
Yes.
How do you perform the supervision? If you can talk more about this part. How's the supervision compared to what exactly?
Yes. So the dual supervision path, there are 2. The first one is the reconstruction path here, and the second one is based on the spatial attention fusion block. So from the spatial attention fusion block, we can extract the spatial attention feature. Here is the FS and FS2 until FSL. And then we use these features to predict the segmentation result in each level. So finally, we can get multi-skew segmentation results. And then we add it together and then to pass to activation block, and then finally get the final segmentation result.
Okay, that's very clear now. So it's in fact compared to the segmentation, not to the reconstruction, not to the whole block of the input. Thank you so much. It's very interesting work.
Okay, thank you.
So if there is no more questions, we're see if we have questions. No. Okay, so we can, I guess, move to the next paper. In this case, so our next paper is about three-dimensional image reconstruction of marine heart and using image processing. It's presented by Huawei Zhong from South China Agricultural University in China. So please start your presentation and introduce yourself. Do you hear us? Okay, so as we cannot hear from, please, if you hear us, or I think you might have a problem with the connection. Once you're back, please send us a message to probably slide your presentation after the next one. Okay, so we're gonna move to the next presentation, and then if he comes back, we can see this his presentation again. So paper number 34, glioblastoma tumor multiform patient survival prediction. I would like to invite the speaker, Snehal Rajput from Pandit Deen Dayal Petroleum University in India.
Yeah, hello. Let me share my screen.
Yeah, please.
Yeah, first of all, very good afternoon to all for giving us the opportunity to present our work. I am Snehal Rajput from Pandit Deen Dayal Petroleum University, and these are my teammates, Professor Rupal Agrawal from Ahmedabad University, Mohandra Roy from Pandit Deen Dayal University, and Mehul Rao from Ahmedabad University. So on behalf of all the team members, I would like to present our work that is based on glioblastoma multiform patient survival prediction. So let me begin with the introduction that GBM is the most common type of primary malignant brain tumor. And in case of the adult population, if we see that the GBM accounts for 60% of all the brain tumor. So most of the institutions follow WHO classification, and WHO has classified the brain tumor into different category based on their nature and behavior of the brain tissue. So we can see here that WHO has classified the GBM as grade 4 type of cancer, which means it is the most aggressive and diffusive nature. And also the GBM survival rate of the patient is very less, around 10 months. And this is because of the heterogeneity in the cell tissues, tumor tissues, and variability in the location, extent, shape, and unpredictable response to the different type of therapy. So for the survival prediction, segmentation of a brain tumor is necessary. So segmenting the brain tumor from the healthy cell into three different classes, which is whole tumor, tumor core, and enhancing tumor. Although our work focuses on the survival prediction rather than the segmentation, so our work aims to come up with the feature set that can give better result for the survival prediction and to develop a correlation among the feature set. So basically the problem is that we'll be segmenting the tumor from the healthy cell, and then extracting the handcrafted features, and then coming up with the feature set that can increase the performance of the survival rate. So we have used the standard breadth data set, which is the data set is a 3D MRI data set, which include training, validation, and test cases. So although we have not participated in the data set, the breadth competitions, we have access to the training and validation data set. So all the results that we have obtained is from the training and validation data set, and the result from the validation data set is obtained from the online evaluation platform that is available on the breadth's website. So moving on to the training data set, there are 369 cases of samples, which include high-grade glioma and low-grade glioma. Separate metadata is given for the survival prediction, which include age information about the patient, survival days, and resection status of patient. So out of 369 cases, survival prediction information is given for 236 cases. And for the competitions, we need to submit the result for the patient whose resection status is GTR, gross total status. So for that only, we have evaluated the survival prediction. So for validation data set, there is 125 sample for segmentation and 30 samples for survival prediction. So now each sample includes different modalities, that is T1 weighted, T2 weighted, T1 gadolinium, flare, and ground truth. So basically this is a 3D data set with a dimension of width, height, and the channel is 240, and 150. And there are 3 different classes. We can see here label 1 is tumor core, label 2 is edema, and label 4 enhancing tumor. So this is the methodology we have used. So this is the pipeline for the segmentation, and this is the pipeline for the survival prediction. So we for the survival for the segmentation, our work is mainly focused on the OS prediction methodology rather than segmentation. So for segmentation, we have used one of the top ranking method, that is no new network. It is also known as ICNC model. So here we can see that it has the architecture of QNet with the encoder and decoder architecture. So with increase in the depth of the network, the encoder is able to extract deeper features, whereas the decoder is able to generate a segmentation map. So here we can see that here multiple segmentation map is aggregated to generate a segmentation of a tumor. So we have implemented the no new network, and for that the validation score is 0.88. This is DICE score for the validation data set is 0.880 for whole tumor, 0.858 for tumor curve, and 0.759 for enhancing tumor. So for the OS prediction, we have used 2 different prognosis method, that is image-based features extraction and radiomic-based feature extraction. So in image-based feature extractions, we have extracted features from the segmentation result that we have obtained from the segmentation task. So we have extracted volume of the ROI, that is whole tumor, tumor core, and enhancing tumor, as well as we have obtained the surface area of different ROI, and the age information. We have used the age information that is given with the data set. So we have included only 7 features to reduce the dimensionality and to as we know that the training sample is very less, especially for the GTR resection status. So to reduce the dimensionality and to stop overfitting, to overcome overfitting, we have used very less feature. And then we have trained each prognosis method onto different predictor model. So 4 different type of predictor model we have used: ANN, linear regressor, and ensemble-based learning called gradient boosting regressor and random forest regressor. So there is another prognosis model we have used that other than the image feature that we have extracted radiomic based features using PyRadiomic packages that is available. So we extracted different shape features, that is 22, gray level features 66, and first order statistical features 19. So total 107 features we have extracted and experimented with it. Similarly, we experimented with the dominant features after applying recursive feature elimination on this 107 features. So we come up with 20 features, and then again we trained each of this method onto all the predictor models. Then also we experiment with the shape features, which is 22 features. So let us see the result from the different prognosis model and different regressor model. So for the model image-based features, we have used 7 features. These are the regression models, the accuracy for the training and validation result. So we can see here the correlation is quite good and the performance is also quite good. But after a certain point, the model's performance saturates. Maybe one of the probable reason can be that the model was unable to learn complexity since the feature set is small. And with the radiomic feature based extraction, we found that since the training sample is very less and the numbers of feature dimension of features was very large, so it didn't perform well, although the correlation among the features was quite good for even validation data set also. So to reduce the dimension of the radiomic based features, we try to reduce the feature set to come up with the 20 dominant features after applying recursive feature elements. These are the feature set. These are the feature set, 20 feature set that we have used to train different regression model. So here we can see that this is the different regression model and this is the accuracy on training model, and this is the coefficient, Spearman correlation coefficient on the training data set, similarly on the validation data set. So here we found that the simple linear regressor with proper regularization and proper parameter tuning is able to give good result on validation data set, and even the correlation among the features is quite good compared to others. Similarly, we experiment with the shape features also. So like reviewing the shape based features, we found that there was a difference in there was a quite different statistical difference among the shape features, and we can say that it is able to capture the genetic anomalies. The shape feature is able to capture that. So using the shape features, these are the 22 shape features. We found that the ensemble based learning is giving the quite good accuracy compared to some of the top performing models. So even the correlation is also good. So here the GBM has performed well on the shape based features comparative to the other regression models. So let me compare the OS prediction for our proposed model and the correlations. And these are the team name and their accuracy and the correlation of the top ranking models on the BREDS 2020 validation dataset. And this accuracy and result has been obtained from the leaderboard of the website of the BRED dataset. So here we can see that GBR model trained on the shape-based feature is giving good accuracy, and the correlation among the shape feature is also good. So in summary, we have evaluated two different feature set, that is image-based feature set and radiomic-based feature set, and we have trained over 4 different predictor: ANN, linear regressor, gradient boosting regressor, and random forest regressor. So image-based model is the image-based prognosis model perform well, but it saturate after some time, after a certain point of time, the accuracy has not improved. And the reason is that the model could not learn complexity because of the less number of feature set. And similar observations were made for the 107 features and 20 principal features and the regression combination. So we come up with the feature set, that is shape-based features have better correlation among the features, and this shape-based feature is able to predict the survival rate more accurately compared to others. And in terms of the model, we found that the assemble-based learning in assemble-based learning, gradient boosting regressor help us to develop to predict the survival rate more accurately. And comparing model will just say that assemble-based learning is giving a robust result compared to other model. That's it from my side. Thank you for listening. And if you have a question, please ask me.
Thank you, Sunal. Thank you for the presentation. Let's see if we have questions. Please, if you have any questions, post them on the Q&A or in the chat. Well, I have a small, I wonder, what do you think about merging all the features, image-based and radiomic features together? Do you have intuition what can this do? Is it gonna make it better or even better than only shape-based features?
So we tried that also. We tried various other combination also, merging image features and then radiomic based features. And then we found that even for radiomic based features, there were only 107. So it was performing very poorly. And merging image based features and radiomic based features also, we found that the dimension space was quite big, and the accuracy was suffering.
Okay, so with the shape features, in fact, it was reducing the performance, adding
Yes.
shape, adding other features that, including the shape features, reduces the performance.
Yes. Yes.
Okay. Okay, thank you so much. I'd like to check if the speaker of paper 10 joined us. Hawei Zong. No, I don't think so. Okay, unfortunately, so I'm gonna move to the, if there is no more questions, I'm gonna move to the last presentation of today's session, this morning session. So it's the paper of color-based diffusion of MRI modalities for brain tumor segmentation. It's me, the speaker, so I'm gonna show the presentation, the video, and don't hesitate to ask questions.
I'm happy to present to you our paper on color-based fusion of MRI modalities for brain tumor segmentation. This is Nashwa Abubakr, and this work has been done in collaboration with Mihaela Popova and Professor James Crowley. Competent diagnosis of MRI imagery requires years of experience. MRI imaging, in particular, are difficult to interpret, as an accurate diagnosis can require adjustment of a number of parameters and the exploration of different MRI modalities. The automatic segmentation of MRI images offers a unique set of challenges. Pixels in each 2D image need to be considered as a part of a 3D volume, as neighborhooding voxels provide contextual information that can be important for the interpretation. This information can be lost when processing each slice independently. For that, some approaches to MRI segmentation uses the whole 3D volume for segmentation using 3D convolutions. These approaches require training large models as well as considerable computational power and training data to converge. On the other hand, approaches that consider slice-by-slice segmentation of pathologies are more affordable in terms of model size and the number of parameters. However, these approaches they tend to ignore contextual information from 3D voxels, and this generally comes at the cost of reduction of performance. To overcome the limitations of 2D approaches, several works have investigated ideas to transform the 3D MRI volume into 2D while keeping some kind of contextual information. These techniques consider a 3D transformation of the MRI volume to 2D image, use the 2D images for segmentation, then reconstruct the final segmented 3D volume from multiple views. 3D transformation approaches include the use of multiple planes from different angles of an MRI image, and also other approaches like projection-based techniques that project from a 3D volume to 2D, use the 2D for segmentation, and then back projects the segmentation to segmentation masks to 3D volume. We find these type of approaches are very promising as they have a comparable model size to slice-by-slice approaches, and in functionality are comparable to 3D volume segmentation. However, they are still far in performance from approaches that consider the whole 3D volume as a 3D unit. For that, in this work, our objective is to improve transformation-based methods and find a trade-off between quality of the segmentation and the computational complexity needed for the segmentation of pathologies in MRI. To do that, we first investigate the use of different MRI modalities and propose a method to fuse them in the color space. And second, we improve the network structure of a recent projection-based method and demonstrate our model structure choices in an ablation study. Different MRI modalities illustrate different information, and those can be useful for the segmentation. For example, T1 shows healthy tissues with high intensity and the pathology with low intensity. T2, on the other hand, illustrate the pathology with a high intensity response. With T1 with a contrasting agent, the tumor border can be visually distinguishable by the bright signal of the accumulated contrast agent. In flare modality, signal of the water molecules are suppressed, which helps in distinguishing edema region. Works that studied the fusion of medical imagery modalities either fuse the modality at the input level or inside the network at the layer level or at the end in the decision phase. To exploit this information exists in different MRI modalities. We study the fusion of these modalities at the input level by stacking different modalities on the color channels. Then we convert the stacked images from a specific color space to RGB using color space conversion formulas. we compare between different color spaces, namely RGB, XYZ, HSV, and LAP, taking the segmentation of tumor in brain MRI images as a use case. We consider the following MRI modalities in this order: FLAIR to be in the first channel, T1 with GAD in the second channel, and lastly T2. Here we can see three slices of three different MRI modalities. By only stacking them on the color channel, we can get a visually appealing RGB image. And by converting this image into other color spaces, we get these other images. To evaluate this idea of color fusion with a projection-based pipeline of MRI segmentation, we develop a similar structure to a previous work of Angerman and Haltmir. Starting from an MRI image volume, we use the maximum intensity projection to get projected images at different angles on the axial plane. Here is an example of the maximum intensity projected images. Then we fuse these 2D images on different modalities using different color spaces. The resulted set of 2D images are then passed to our model. The backbone of our model is a standard unit, 2D unit, that's randomly initialized. The model receives a color fused 2D projected images extracted from the MRI volume of different modalities. The output of unit is then used to reconstruct the volume using linear reconstruction, where a voxel value in the tensor, is defined as the sum over the corresponding 2D projected values. Then we follow with denoising the segmentation with average pooling, layer, and instant normalization. For training, we use a joint loss function of dice loss and cross entropy loss with equal contribution. For our experiment, we use the BRATS dataset from MICAD Medical Imaging Decathlon. And we consider for our experiment two classes only, the pathology, which includes enhanced and non-enhanced tumor, and the background class, which includes the edema and the background labels. For the evaluation, we use 4 metric: DICE score, intersection over union, precision, and recall. We evaluate our model on 4 different networks: a standard 2D unit, which learns to segment the MRI volume on slice-by-slice basis; a 3D unit, which on the opposite uses the 3D convolution to segment the 3D volume; and 2 other transformation-based techniques, namely projection unit and the 2.5D unit, that are comparable in the architecture to our model. And from this table, we can see that our model scores second after 3D unit with around half the number of training parameters. Our model outperforms the other methods with large margin while preserving model complexity. Here we report on the performance of our model for each modality separately, and then using a color fusion. From this table, we can see a significant improvement using modality fusion with color spaces. And from this HSV hue saturation value color space stands out and performs the best on most metric. Here we can see the effect of our different model choices of our network, starting from a model, the model that proposed by Angerman and Haltmir. We re-implemented the model and tested it using different MRI modalities. We can see the results here. And then we report on the effect of each modification we made on the network over their model. I invite you to read the paper for more details and for the link of the implementation code. So to conclude, we presented a method to fuse multiple MRI modalities that uses color space transformation. We showed that this fusion improves the results of segmentation significantly with no significant additional computation. And we proposed improvement of our recent projection-based segmentation network and showed an ablation study to demonstrate the effect of our choices. And our model outperforms the previous projection-based network with more than 12 points while preserving the same model complexity and training parameters. Thank you for listening.
Sorry, we can't hear you.
Hello. Yes, thank you. I would like to I'm watching if there is any question, please post them on the in the chat. I don't see a question. Okay, in this case, I would like to ask again if paper 10 speaker is here to present this paper, the speaker of the paper 10. Okay, no, I cannot see the speaker. So in this case, I will give back the mic to Dora.
Okay, thank you. Thank you very much for your hard work. And we will begin our session 4. And let me introduce our session chair, Dimitris, who comes from University of West Attica, Greece. Let's welcome.
Thank you, Dora. Good morning from me. I wish that we're going to have a nice session. We're going to the oral session 4, machine learning and deep learning. I come from the Department of Biomedical Engineering of the University of West Attica, and I will serve as your session chair. From a fast check, I see that all speakers are connected. So we will not waste any time. Please have in mind that the duration of each speech is 10 minutes, and we have 3 minutes for questions and answers. So I'm going to invite the first one. Also, I will apologize in advance if I don't pronounce your names correctly. The first paper is number 12. The title is 2B3Net, combining 2D and 3D convolution and neural networks for 3D PET scans predictions. So the presenter is Roman Thomas from Jura Nova, France.
Yes, hello. Can you see my screen?
Yes.
Yes.
Yes, okay, thank you. Let's begin. So today I will tell you about my paper 2B3Net, combining 2D and 3D convolutional neural networks for 3D PET scans prediction. Positron emission tomography is an imaging technique that allows to visualize the metabolic activity of cells in the body. Doctors use this modality to plan the appropriate cancer treatment. There are 2 main methods to exploit this image modality. First one is radiomics. Radiomics are features related to a segmented region of interest that describes this region. First step is the segmentation of this region of interest. A doctor or an algorithm produces a segmentation map of the tumor. Then radiomics can be extracted. They are related to the intensity, the shape, or the texture of the tumor. Final step is the training of the machine learning model to make the appropriate prediction. However, this method has two main drawbacks. The production of the segmentation map is a time-consuming step and is subject to intra-observer variability. A PET image is really noisy, and as a result, it is difficult for two different doctors to produce the same segmentation map. The other main method to exploit a PET scan is convolutional neural network. 2D CNN perform well on natural images. However, due to their 2D nature, they can't be applied directly on 3D PET images. Therefore, a 3D CNN is the perfect fit to exploit the 3D spatial information contained in the PET scan. There are two main drawbacks to 3D CNN, that are they have much more parameters than 2D networks, and there is no pre-trained 3D model available to initialize the weights of the 3D model, meaning that we have to train it from scratch. In the medical field, PET datasets are usually small. Sorry, I hear an echo. PET datasets are usually small, and it is therefore harder to train a 3D CNN, which implies an overfitting tendency. We propose a new innovative method that takes advantage of a pre-trained 2D network and combine it to a 3D network. The first part of the architecture is a 2D network. It is helpful to use a 2D network because it will ease the training of the global architecture. The combination to a 3D network enables it to exploit the 3D spatial information contained in the scan. Finally, we assembled several public datasets from the Cancer Imaging Archive to constitute a large PET dataset. Now, I will detail the different parts of our architecture. First, we split the 3D volume of a PET scan into k 2D slices. We select only k out of n slices as we need a consistent input to our architecture. The slices are cropped to also diminish the global size of the image. Second step is that we apply a 2D feature extractor on each of the image. We used a ResNet 50 to extract intermediary feature maps. We use an intermediate layer of the ResNet so that the features extracted are relevant to our case. The extracted feature maps are of size 256 by 23 by 23. Then we combine them to reassemble a 3D volume. This 3D volume then had an additional shape of an additional dimension of k. The last step is the application of a 3D CNN to make the prediction and exploit the 3D spatial information contained in the scan. This architecture has several advantages. It has less 3D convolutional layers to train from scratch than a full 3D CNN. That also implies having less parameters to train. And the 3D volume reassembled is smaller than the original PET image. That will also contribute to facilitating the training of the 3D CNN. We evaluate our architecture on two tasks. First is a correlation of spatial information. Our objective is to compare three models on their ability to correlate spatial information between slices. We compare 2B3Net to its 2D alternative version where we replace the 3D convolutional layer by 2D ones and a full 3D CNN. We make the hypothesis that a single transverse slice doesn't provide patient gender information. Then the models have to rely on the correlation of these slices to make the prediction at a patient scale. Here, we can see that 2B3NET achieves superior performances compared to the two other CNNs. The full 3D CNN achieves the worst performances as it had to be trained from scratch on this task. And when we compare 2B3NET to its 2D alternative version, we attribute its best performances to the fact that the 3D convolutional layers can correlate the spatial information contained in the scan, while 2D ones can't perform as a good correlation. The second experiment is a prediction of clinical outcomes of the head and neck cancer. That are the prediction of, there are three outcomes that we consider: the prediction of local regional recurrences, the formation of distant metastases, and the survival of the patient. The idea is to compare our method against a radiomics approach from Martin Valliere, published in Nature Scientific Reports. We will consider two models to compare our architecture with. First one is a machine learning model based on PET radiomics. The second one takes as input PET radiomics combined with TT radiomics and clinical data. Our model only takes as input the PET scan and have no access to any metadata of the patients. This is a difficult task as all the clinical outcomes have a pronounced class imbalance, approximately 80%. Therefore, it is also harder to train a deep learning model on this task. We added one more experimental setup to this experiment. This is a pre-training of the weights of our 2B3NET with the weights of the previous experiments. This serves as a basis for fine-tuning the model. Here, we can see that 2B3NET achieves better performances than 2D or 3D CNNs. It also achieves better performances than radiomics models on 2 out of the 3 clinical outcomes. It only achieves inferior performances on the prediction of distant metastasis. We attribute the best performance of the radiomics model to the information contained in the CT scan. The author demonstrated that this information allows to make a significant contribution to the prediction. To conclude, we propose 2B3NET, an architecture that combines a 2D pre-trained network to a 3D CNN. This combination enables direct exploitation of 3D scans, which can be PET, MRI, or CT. And this combination is a competitive alternative to traditional CNN and radiomics approaches. Thank you for your attention. And now I would like to open the floor for questions.
Thank you for the presentation. I think we have one question from Omer Kaya.
Can you read the question? I cannot see it on the chat.
I see that Omer Kaya has raised the hand. I don't know if it's by accident or there is a question behind this. So if Omer Kaya listens to us, you can write your question in the chat forum so we can read it. So, okay, I have one question for you. The number of slices, K, how does it affect the complexity, the computational complexity of your implementation?
Well, the more you increase the number of slices you select, the more it will increase the number of parameters of the network. As the feature maps, as the recombined volume will be bigger than if you take a small number K. In our case, we took K as a 66, as it corresponds to the size of the smallest scan. The important setting in this task is to select the number corresponding to the size of the smallest scan you have in your datasets, so you can exploit all the scans that are in it. The selection of K out of n slices of the scan also contributes to a data augmentation, as the model doesn't see every slice of the scan at each training step.
Okay, thank you. Any other question? Any more questions? Thank you, Roman Thomas. And we're going to invite the next presentation from paper 21 with title A Hybrid Deep Model for Brain Tumor Classification. The presenter is Hamail Ayaz from the Institute of Technology Sligo of Ireland.
Good day. I have actually submitted the video, but let me present it. Just give me a second. So can you see my screen?
Yes.
So thank you. My name is Hamail Ayaz, and the paper title is Hybrid Deep Model for Brain Tumor Classification. As you know, we have MRIs for CAD system to diagnose between, to classify between different types of tumors. All of these CAD systems work with intensive pre-processing and perform better results. The main idea of this work is to merge convolution neural networks in such a way that fuse together to form a hybrid deep architecture. And to evaluate the results, we use a statistical evaluation such as Atman score, precision, recall, and other statistical analysis. Brain tumor is the second most fatal emergency after Alzheimer's. Alzheimer's is considered as #1 fatal emergency. This study investigates 3 different types of brain tumors: glioma, pituitary, and meningeal tumors. These tumors are available on picture profile online data repository and consist of 3,000 plus MRIs of T1 contrast systems. CAD system today use machine learning approaches for extra computation and along with data augmentation to achieve higher accuracy, as I said earlier. And we keep in mind that we still need a neuroradiologist to annotate the data, but sometimes it is prone to error because of intensive care or intensive timing that they have been using in their laboratories, which actually lead to not identify between benign and malignant tumors, which goes for to certain death rates as well. So that's very important that we are actually helping the through a CAD system that can actually diagnose between or classify between different types of tumors. So for the background of the study, we know that there is an intensive background available when we talk about CAD systems and MRIs or classification of these systems. Do keep in mind that all of these systems use different type of extra pre-processing when we talk about complexities or when we talk about processing of MRI systems, such as region of interest and extraction or segmentation based procedures. Data augmentation is a very healthy procedure as well. This will overcome this particular limitation to use those region of interest, segmentation, and data augmentation procedures to achieve high accuracy based on deep learning models. First of all, let's just go back a bit and talk about how we do things in machine learning or AI, which is well known that they have a CAD system with a manual operation and limited capacity. So we use conventional methods as a feature extraction method for machine learning to produce actually good results, and with state-of-art deep learning methods, we have achieved a good variety of classification results, and we actually achieved 100% accuracy in transverse learning. But the only idea that was limited over there was to use data augmentation, or making similar images comes multiple times with a different type of orientations, with different type of angles. So that is actually to increase or boost the higher accuracy. And with the limitation of machine learning, we came to know that we have region of interest procedures to follow up. We have segmentation procedures to follow up, and then finally selecting a feature vectors, for example, GLCM or SWIFT features for image descriptions, which it actually, when we talk about manufacturing, increase the computational complexity and make an expensive CAD systems. Therefore, this work actually talk about to merge deep models in certain fusion ways that the classification performs better through different type of networks to merge together to reduce the data redundancies. The following equation has been used to describe the deep model that has been used, where we know that each weights and height represent the convolution and the shape of the images. The proposed study consists of two separate state-of-the-art networks, AlexNet network and Squeeze network. That are both a network that has been used earlier, and you know that these AlexNet and Squeeze networks are very well-known vectors when we talk about brain tumor classification. My only idea was to actually merge these vectors together to make a fully connected fusion vector that have all the features from different types of vectors. I know that there's a lot of work has to be done with the fusion of the method, and I'm working on that particularly. I will show you the conclusion, and I will talk about that as well. The feature when merged together produce good results due to the collision of AlexNet architecture that is very low in, that very good in finding features for each layer, and the fun Fireblock network is used that is very low in computational. So we save the computational cost, and all of the idea has been done with just 10 UpX. Previously with the deep learning model and even contrast MRI images, or we have seen that for each model to train and to converge, we need 100 of UpX to make sure the CAD system works properly. But with particular hybrid deep model, we just use 10 of UpX to make sure the model converge. We split the training and testing data into 1820. The dataset images were actually 5 and 12 on overall dimension, but to make sure the paperwork in line with the previous works and previous published articles, we'll use the size to 256 cross 256, and actually it save some computational complexity time as well. To reduce the overfitting and underfitting issues, we used the early stopping method to validate the results and make sure that if the validation loss was not going low after 5 UpX, the training pool will stop. And we actually applied 10K-fold cross validation for the giving data. Several different optimizer has been experimented with this data set, such as Adam, AdamX, AdaDelta, the known optimizers we have. Different learning rates was to be implemented, but the limitation of the paper was 10 pages, so I skipped to that particular parts. We'll publish that work in the next conference, hopefully. And different learning rates give different results, but with the static learning rate that has been produced by the actual contributor, we saw that RMS produced very good results as compared to others. The learning curves can be seen as the validation and training accuracy. You can see that the loss and training of the particular data training has easily converged, and the loss is very statistic in that area. Overall, for glioma results, we have 28 misclassification due to the intense similarities between meningioma and glioma in some MRIs, which was available to us. And you can note the overall accuracy achieved for 94% without any region of interest segmentation. We can achieve a high result with region of interest segmentation or region of interest extraction and then feature extraction, and then goes to deep model to hybrid networks. But that would increase the computational complexity and also make a heavy CAD system, which is we want to subside, and a very lightweight CAD system for neuroradiologists. In conclusion, this work investigate the HybridD model for classification of 3 tumor types: glioma, meningioma, and pituitary. The overall accuracy was 94 with 10 of bugs. That gives higher accuracy of CAD system. The proposed idea opens the door toward how to actually merge these models, then merging into just one network, make sure that each network is a separate network, and then converge together to make a healthy feature vector, and then goes to the dense layers as well. So the current and future direction, we are working on tumor types and targeting more tumor areas. For example, sinonasal tumor area for squamous cell carcinomas or head and glioma, IgGs and LGGs. And then in future, we will talk about the fusion to reduce data redundancies. As I said earlier, that fusion of 2 networks increase the redundancies. And so for that, we're actually trying to produce nonlinear or unsupervised autoencoders to the technique, so that we can actually make sure that the redundancies will be over there, but to the minimum level, and also to improve the misclassification of glioma classes. Some of the references that I've used. Thank you so much. If you have any questions.
Thank you for the presentation. Yes, there is one question on the chat panel. The data set for gliomas was from the BRATS data set?
Yes, it was the BRATS data set. That is actually of 3046 images, I guess, and with this T1 contrast MRIs. That is easily available if you actually Google that.
And another question from me. Do you know if this data set has been histopathologically confirmed? The diagnoses are histopathologically confirmed?
Exactly. There are multiple papers that has used this particular data set to make sure that each and everything is in line. And the recent paper was with transfer learning, and it was published in 2020, and to make sure that it works exactly similar like pathology or histopathology results.
Thank you very much. And the next paper is number 28. The title is A Systematic Literature Review of Machine Learning Applications for Community-Acquired Pneumonia. I would like to invite Daniel Lojano Rojas from the University of Leicester, United Kingdom, for his presentation.
Hello, everyone. Can you hear me?
Yes.
Hello. Okay, brilliant. I will share my screen now. Okay, are you able to see my screen?
Yes, we can see your screen.
Okay, thank you very much, everyone, for coming. I will start now. So here, thank you very much for everyone, not only for the attendees, but also for MICAD organizers for this conference. I would like to present our paper on the systematic literature review of machine learning applications for community-acquired pneumonia. That is part of my PhD project in the University of Leicester. So the outline of this presentation is as follows. I would like to present the objectives of this paper, then a broad description of the disease, and finally going to the literature review methodology, and finally present to you the results. So let's start with the objectives. The aim of the literature review is to create a framework in the field of applications of machine learning for supporting community-acquired pneumonia management. And this, like in the old management process. And the specific objectives of this paper was to create a classification framework for different stages in the disease management, then identify the techniques that have been implemented, how sophisticated have been or what are the gaps for the current techniques that are available, determine a state of the art of the field, and finally identify such areas that can be benefit for the research. So now I would like to talk to you a little bit about pneumonia. Pneumonia is a lung condition that is highly related with mortality. Now we have all the COVID-19 situation, which gives us a really good insight about the implications of pneumonia. Some of the consequences of this disease are the high cost for healthcare systems, the capacity problems also for hospitals, and as I said before, is correlated with high mortality. The symptoms, one of the problems with the disease is that the symptoms are quite generic and can be confused with any kind of infection that are associated with fever, production of mucus, and lack of oxygen. And the other problem is that the different causalities of this disease, which could be bacterial, viral, or fungal. In terms of management, we have two steps. The first one is the diagnosis, which is mainly based on X-rays, and second one, the hospitalization. And the hospitalization, basically, it depends on how the severity is determined. So here in this chart, we can see different scores that depends on the symptoms of the patient. And these scores determine the severity, and they are all used in different countries depending on the healthcare and the guidelines for countries. So there is not a consensus on this. And this is quite important because this is an opportunity to machine learning application. So I would like to talk to you about the methodology, because it's quite important since we took the guidelines and the methodology from Pedersen et al., which is methodology for systematic reviews in engineering. And we complemented this methodology with the PRISMA checklist, which is highly accepted in the medical field. So here we are joining both sides, the computational and engineering side of machine learning with the clinician applicability. The first step in this methodology was to define the literature review, those that we defined based on a machine learning project, basically. So we focus on the outputs of each study, then identify the data, types and source, the algorithms used, how they compare and assess these algorithms, and finally we wanted to know about the interpretability that different researchers gave to their models. We defined different databases, and once in the databases and extracted the study, we define inclusion and exclusion criteria. The main between them are all the studies should belong to peer-reviewed journal or conferences. The studies should get like community-acquired pneumonia as the main disease of study, and we didn't include any COVID-19 study for this purpose. And finally, we extract the main data and the main information from each study, which was data information related to size of the data set, source of the data set, and type of the data, algorithms used, and performance measures. So now I would like to talk about the results. And the first result that we found, even before presenting the studies, was this framework to classify the studies in different steps on community-acquired management. This is diagnosis, outcome prediction, and when we talk about outcome, it could be prediction of severity or mortality of the patient, then ICU admission, whether a patient gets into the ICU or not, and the treatment provided. So now the corpus or literature review was based on 23 articles that, as you can see in the chart, most of the articles are from recent years, which is an indicator of the problem has taken a lot of interest in the community. And also we identified the main outputs, and most of them in the categories that we define are binary, which is important since this means that the field is still in exploratory stage, and it could improve the way that the output and the problem is seen. And finally, we identified that the main data, the main features used are the data gathered in hospital when admissions, the first moment at admissions in hospitals. Now, I would like to talk about like answering each of the questions. Now, we have the data, and we identified that, as I already said, most of the data was from admissions data, but we also identified that images were used, and images are used basically for a diagnosis. This the data sets of the studies have different sizes, but most of them are between 1,000 and 20,000 samples, which are decent size of data sets. However, the representation of these data sets depend on the location of each research. Plus, they have different sources as well, depending on this location. This is important because to compare and determine the state of the art was kind of difficult, given the difference of the data sets and the populations that they were studying. In terms of algorithms, we can see that most of the algorithms used were relational. And when I say relational, is those machine learning algorithms that provide any type of explanation, from random forest algorithms to KNN and regressions. However, they didn't use too much deep learning or neural networks. Here we can see that we have neural networks as the second most used algorithms, which is contradictory to what I just said. But the thing is that most of these neural networks were used before 2012, which means that they didn't went beyond 3 layers. So they are quite small neural networks, and still open the field to the application of more sophisticated neural networks. The fourth question is about the measurements. So most of the study use arrow curves and accuracy as the determination. The arrow curve is really important for the medicals to interpret the results, given the trade-off between the false positive and the true positive. And finally, I would like to mention that most of the study limit the interpretability to the explanation of the model and not to explain how the features interact with the outputs, which is really important in terms of usability in the future. So I would like to mention 2 specific studies that caught our attention. The first one is Sarisetinov in 2019, not only provide the diagnosis of the disease, but locate the clusters in the lungs in the x-rays. And Prisbilla in 2020 provide a model based on Markov chains to predict how the transition of a patient and determine whether a patient could die or not. Finally, we reach 5 main conclusions, but I would like only to highlight the gaps in the field that we identified. And the first one is that to our knowledge, there are no actual application in either in the guidelines or in a hospital in the world that use machine learning to support community-acquired pneumonia. The second one is that there is still a lot of path and space to apply really sophisticated machine learning models to different dimensions. It could be either for prediction of severity, treatment, or ICU admission. And now, complementing this gap, I would like to say that treatment is the dimension that has been less addressed in the whole spectrum of our corpus. And this is really important, since in this area could be a really good opportunity to machine learning to help healthcare systems. These are the big vision of our literature review. Here are the references divided by dimension. and that was it. I'm open to any question, and if you want to discuss further, here's my email. I'm more than happy to answer anything or any questions that you have. Thank you very much.
Thank you for the presentation. So if we are having any questions, I would like to ask you one question. What did you discover, if you discovered any research activity on pneumonia or causing from COVID patients?
Can you go deep in that question? I'm
yes.
Following.
Yes. COVID-19, the new disease, has been shown to cause a lot of patients with serious complications, pneumonia. So did you find any research activity, any research studies with COVID-19 pneumonia?
So the thing is that my project was defined before COVID-19. So we left out all the studies on COVID-19. Of course, like in this moment, there are a lot of studies, and you can find a lot of papers talking about COVID-19. However, our study is mostly focused on community-acquired pneumonia, which is another type of pneumonia, and its main cause is bacterial. I mean, it could be any of the other causes, but the main cause is bacterial, but different to COVID-19, which is viral.
Okay, thank you very much. And we can go to the next paper, paper 31, photograph to X-ray image translation for anatomical mouse mapping in preclinical nuclear molecular imaging. And the presenter is myself from the University of West Attica, Greece. So we'll share my screen. So this work comes from two joint laboratories, one from the company BioMTech, Bioemission Technology Solutions, and the other one from the Medical Signal and Image Processing Lab of the Biomedical Engineering Department of the University of West Attica in Greece. So we are dealing with drug discovery, which is a very laborious and lengthy process. Initially, we try to find the mechanisms of the disease of interest and locate the most important targets that could be used as potential places that a new drug could act upon in order to reverse the disease or control the disease. So initially, we test many different chemical compounds. For example, in this graph, you can see 10,000 different chemical compounds and as potential candidates for the new drug that we want to develop. This is the first phase, and then we go to the second phase that we try to reduce the candidate compounds into a few hundreds, 200, 250. This is a part of the preclinical stage where we are using animal and cell culture models in order to test the efficacy and the safety of the candidates, of the chemical compound candidates for the new drug. And then if some of these candidates pass all the tests, they go to the clinical trials where we apply these new drug designs into humans and we study their behavior. And after a lot of time and a costly procedure, we go to the authorities to ask for a review and approval of the chemical compound as a new drug in order to promote it to the market. So this whole process takes about 15 years and costs about 1 to 1.5 billion euros. So it's a very laborious process. Nowadays, with the COVID pandemic, we have seen a lot of reducing of this time because many research groups and government authorities have funded with big amounts the research in the COVID situation. So we can see even after only 1 year, new drugs and new vaccines on the market with emergency approval. But the general way to do it is not so fast. It takes a lot of time. So usually these studies of preclinical evaluation are performed by thousands of small and medium research groups and companies around the world. The standard method to do the preclinical evaluation is the biodistribution analysis, where we use the animal, we administer the candidate drug to the animal, and then at several time intervals, we have to cause euthanasia of the animal, dissect the animal, and then measure the concentration of the drug in several different places of the animal's body. So this is a bit invasive procedure, which can be improved very much if we have available at our disposal tomographic systems that can non-invasively measure the activity of the drug inside the human body. But tomographic systems are not very easy to be used by small groups because they have extremely high costs, around 500,000 euros, and also they have extremely big complexity in terms of servicing and operating. So the alternative is to use planar imaging, either using radioisotope labeling or fluorescence labeling, which can be used for fast screening. Here you can see one example of such image that we have labeled the drug, and the drug circulates inside the body of the animal, and we can use fluorescent cameras or nuclear medicine, nuclear cameras to visualize at each time interval where the drug is located inside the animal's body. This kind of imaging can provide a lot of answers in crucial questions in drug discovery, such as if biomolecules reach the target, if they are concentrated to organs and tissues, if they remain inside the human body for a lot of time, how long do they stay in the blood circulation, are they stable post-injection, what happens after the first minutes post-injection, what is the best injected concentration, etc. So they are very important studies. Here you can see one type of nuclear radioisotope located into soft tissues of the animal, and to the right image, one type of nuclear isotope that is located into the bone structures of the animal. So what was the purpose of our study? Was to virtually create a tomographic system without the use of buying the real system. And we try to do that by using deep learning and GAN networks, generative adversarial networks, in order to create synthetic X-rays images based on the standard photographic image of the animal, a small animal. And then after we obtain the synthetic X-ray images, we do some kind of registration and fusion of these images into a single display in order to be able in a single display to illustrate at the same time the anatomy and the functionality of the protocol inside the animal. So we are using an off-the-shelf approach, which has to do with the translation of a photographic mouse image into its respective X-ray scan. The method is well known. It has been published in 2017 by Isola and his co-workers, and it's called image-to-image translation with conditional adversarial networks. The activity of the conditional adversarial network is to predict, based on one input image, a new synthetic image on another domain. In our case, we have photographic image that is translated into a synthetic X-ray image. And to do so, it needs two networks. One is called generative network, and the other one is called discriminator network. The generative network tries to produce the synthetic images, whereas the discriminator network tries to identify whether one image is real or fake. So in the beginning, the generative network cannot create real-like synthetic fake images. So the discriminator is very easy to identify that these images are not realistic. But the generative network is allowed to see the exit of the discriminator. So it takes information and it improves itself in such a way that it will make it hard for the discriminator to find the imposter images and to separate them from the real examples. And this interaction is favorable for the training of the network, since at one point the network creates synthetic images that are very difficult to be distinguished from realistic images. So for the generation of our data, we use a custom-made device from the BioMTech company. It's called Gamma-Eye scintigraphy system. Here you can see the internal designs of the scintigraphy system. On the upper part, we can see a standard CCD photographic optical photography detector. And here is the a full extra system that we have the X-ray module. We have the single photon emission computed tomography module, and we have the PET module at the PET module at the right. And in between them, we have the bed that we insert the mouse. So using this Gamma-Eye, we take the optical image. Using the X-ray apparatus, we take the X-ray image. So we have our initial data set, and then we can combine them using registration and fusion into a single display where you can see the anatomical information provided by the X-ray apparatus superimposed to the photographic information. So we have used as less animals as possible, 62 white and 14 black Swiss albino mice. We generated 5 pair images for each animal by placing it in 5 different poses upon the hosting bed. In total, we have 380 inputs, images of 512 times 1024 pixels. So Pix-to-Pix network was evaluated against the mouse color. We had black and white mice, different background due to different material and color of the animal hosting bed, as I will show you later, and presence or absence of acrylic cover. These are standard settings for examining the animals. So we have the mouse color, which is white or black. Bed color, plastic, black, acrylic, transparent, white plastic. Cover, using cover or not, and we have tried to have at least 10% of our data, of our images for testing, and the remaining for training. Evaluation metrics comprised peak signal-to-noise ratio and structural similarity index measure. You can see results. We have the standard photographic image. We have the X-ray image, the fake X-ray image, and we have a real in the middle, we have the real X-ray image. So we have found that both of the evaluation indexes were very good. We have SSIM down to 0.69. Values close to 1 are mean that we have a good production of synthetic images, and PSNR 16.95. The bigger the PSNR, the better for the realisticness of the fake images. And here we can see a real protocol of examination in an animal regarding candidate drug. We have 50 microcurie at 50 microliters of a radioisotope called technetium-99. We have imaged the mouse using the gamma-I scintigraphy system, and we have produced a synthetic X-ray image using the Pix-to-Pix network and combining with the functional image into a single display. And it was a very nice representation, because at the same time we can visualize the anatomical, the morphological, and the functional information into a single display. Also, a very important advantage of this methodology is that we don't need to use a lot of mice, and we don't need to call euthanasia into these mice as in standard biodistribution methods. And we also don't need to buy the very expensive X-ray tomography unit. But about our future work, we are planning in balancing the dataset in terms of mouse color and different background in order to optimize predictions in many other realistic scenarios. We would like to reduce the resolution of the images because it took a lot of time to train the networks. And fun fact, with MATLAB, it took 5 days to train the networks. But with Python, just, if I remember correctly, 16 to 18 hours to train the same network. And so we would like to reduce the resolution because it's not the output image not intended to be used for animal mapping, so we can accept a lower resolution scenario. And also we wish to apply some kind of pre-processing to remove any background other than the actual body of the animal. So to conclude, this study has been financed by the Greece and European Union under the ESF fund, using under the program Deep Learning Algorithms for Molecular Mapping Application. And the publication of this research has been funded by the University of West Attica. Thank you, and we can go to questions. Okay, I cannot see any question, and I cannot ask myself for a question. So we can go to the next presentation. We are moving to paper 32, active strain statistical models for reconstructing multidimensional images of lung tissue lesions, from Ekaterina Guryanova, Russian Technological University of Russia.
Hello, ladies and gentlemen. I'm Ekaterina Guryanova from MIRA, Russian Technological University. I'm here to present my research paper, Active Strain Statistical Models for Reconstructing Multidimensional Images of Lung Tissue Lesions. coupling augmented reality data with data from previous medical studies is most useful for surgeries on organs with little movement and deformation, e.g. skull, brain, and pancreas, as there is opportunity to more clearly define the edges of the organ. The proposed coupling methods can be used on other operations. Besides, organ imaging techniques can compensate for the lack of tactile feedback during laparoscopic surgery for providing the surgeon with visual cues, improving hand-eye coordination, including robotic surgery. Using the combined images of MRI, CT, angiography, and ultrasound individual adjustment of inclusions and cutting plans, optimal position of pacentesis needles and position display of the organ main component are realized. Blood vessel structure data can be superimposed on this surgical cavity using vessel counter recognition. For this purpose, a model for identifying vessel counters in the video stream was developed using active strain statistical models for recreating multidimensional images. The training procedure for active appearance models begins with normalizing all shapes position to compensate for differences in sail, tilt, and offset. For this purpose, the so-called generalized procrustin analysis is used. Purpose: to investigate computer model of contour selection to propose a model for identify vessel contours. A literature survey. The mathematical apparatus of active appearance models has been actively developed at the moment. To approach to the construction of such models can be distinguished. The classical one, initially proposed by Curtis, and verse composition-based proposed by Mattis and Baker in 2003. Math is based on constructing a model of lungs affected area, and deformable models give relatively high recognition rates on extensive collection of images with a potentially large number of lunge images. The learning experimental procedures was carried out on the computer tomography images of lungs with the affected parts. On this slide, we can see the anomalies such as the COVID anomalies. Computer model of contour stream. The model process here consists of following steps: extraction from the training images of the textures that best match of basic shape. Region mapping is carried out using piecewise interpolation of the training image. From the training image for the textures that best match the basic shape. Region mapping is carried out using piecewise interpolation of training image resulting from triangulation to be corresponding regions of the texture to be formed. A matrix is formed for the textures, each column containing the pixel values of corresponding texture, similar to the S matrix. The texture uses the training, word single channel, grayscale, and multi-channel RGB color space. First, consider the common parts of the true approach. Two parameters are modeled in the active appearance models: shape-related parameters, shape parameters, and parameters related to a statistical image model or texture appearance parameters. Before use, the model must be trained on a set of pre-marked images. Markup of images are done manually or in a semi-automatic mode when using an algorithm to find approximate mark location, and then they are clarified by an expert. Each mark has its number and defines a characteristic point to the model we'll have to find during adaptation to the new image. Example of a markup at this slide. In a model of this type, the authors also need to calculate the vectors of combined parameters, which is given by the following formula. There, WS is the diagonal matrix of weight values that allows balancing the contribution of pixel distances and pixel intensities. For each element of the training sample, the texture shape pair, its vector B is calculated. Then the resulting set of vectors is combined into a matrix, and its main components are found. In this case, we synthesized vectors of combined shape and texture parameters is defined by the following expression. B. Here, C is the matrix of principal components of the combined parameters, and C is the vector of combined appearance parameters. From here, obtain new expression for the synthesized shape and texture. Synthesized shape and synthesized texture, S and T. In practice, the matrix phi is also subjected to removing noise components to reduce the effect of overfitting and reduce the number of calculations performed. After calculating the shape, appearance, and combined parameters, this so-called prediction matrix R is required, but the sense of minimum roots mean per square error would satisfy the following linear equation. Experiment procedure, active strain statistical models superimposed on the texture presents on this slide. Analysis of active form model. The model of active deformable forms was trained and verified to identify contrasts. Preliminary training gave a confidence score on 0.75, the result of unsatisfactory. The training sample was expanded and number of reference points was changed to 128 per closed counter. As a result of training, confidence increased to 0.937. The implementation of counter detection was performed with the confidence at least 0.88 in contrast to the level on 0.73 for the gradient method. Conclusion. A method for constructing a model of the contours of lung segments to identify affected tissues is shown. Strain statistical models are used to reconstruct multidimensional images to build contours. The model showed an accuracy of detecting contours equal 0.1 millimeters, which meets the requirements for detecting affected lung tissue and can be used in a medical system for early diagnosis. Acknowledgement. The project is supported by Foundation for Assistance to Small Innovative Enterprises in Science and Technology, Russian Federation. Project number 63437, application NTI 84099. Within the framework of the implementation of the innovative project, development of an intelligent software package for the preventive diagnosis of human respiratory diseases based on active deformation and statistical models for recreating multidimensional images using an immersive environment to implement HealthNet action plans, roadmaps. Thank you for attention. We can go to the question.
Thank you for the presentation. Are there any questions? I have one for you. So did you take under consideration the change of the shape of the lungs during these different breathing phases?
Please repeat the question.
If you have considered that the lung changes its shape when we inhale or exhale, it changes, it becomes larger or smaller, and if you took under consideration this effect in your model?
Yes, we research this effect by many data sets. We use the CT data of Moscow Radiology Center and with the help of experts marked them very detailedly. We researched the effect about you said in state training procedure by with experts of radiology.
Okay, thank you very much. And we can go to the next presentation. Paper ID MD201, evaluating mobile teleradiology performance for the task of analyzing lung lesions on CT images by Omer Kaya.
Hello.
Hello.
I'm sorry, screen.
Sorry. I moved to paper. Yes, it's paper 44.
Okay.
Sorry. Inconvenience. We're going to Daniele Perlo from the University of Torino, Italy. Dysplasia grading of colorectal polyps through convolutional neural network analysis of whole slide images.
Welcome, everyone. I just share my screen. Okay. Can you see my slides? Okay.
Yes.
Welcome, everyone. I'm Daniele Perlo. I'm a PhD student from the University of Turin.
and I'm working in the computer vision lab called the ADOS lab at the Department of Computer Science. And this project is funded by the Deep Health European project. I'm talking about the dysplasia grading of colorectal polyps through convolutional network analysis of slide images. In this presentation, I would like to focus on colorectal polyps classification problem, and after that, the dysplasia classification, the focus on the dysplasia classification. Rapid look to the whole slide analysis and also the data set we have collected, the method that we use, pipeline training and inference, and our findings. At the end, beside the whole slide inference performances, I would like to show you some visualization in order to better understand our works. The colorectal polyps classification is a key factor to early diagnosis the carcinoma and colorectal. The colorectal polyps is a fleshy growth occurring in the lining of the colon. Some attempt for make automatic classification on whole slide analysis is done. Whole slide scans are high resolution image from biopsies. And the data is collected within the European project Deep Health from the Unit of Pathological Anatomy Department here in Turin. Why we are focusing on the dysplasia? Dysplasia is defined as the abnormal cellular development of an organ or a tissue, generally consisting in a loss of control mechanism with the replacement of mature cells by immature cells. And it can be a condition that predisposes the neoplastic process until the carcinoma. The dysplasia classification is not taken into account in previous works, but different colonoscopic surveillance routines have to be set to prevent carcinoma for the patients. And the dysplasia grade is a major risk factor which influences the routine choice. The glandular dysplasia grades, the glandular dysplasia is divided into different grades, low, medium, and high. The middle dysplasia grade, for example, is not reported in each medical institution guidelines due to the difficulties in concordance between the pathology itself. To work with the dysplasia classification, we take in consideration different types of tissue. Beside the normal tissue, we have a non-neoplastic polyp, like a hyperplastic polyp, and tubular and tubular adenomas with a high and low grade of dysplasia. Taking a look to the whole slide analysis, the whole slides are big resolution images with the tissue that is taken from the biopsies. We asked to our pathologists not only to label the whole slide with the diagnosis, but also to enlighten the tissue that is representative for the diagnosis. So the tissue that is informative for them to make the diagnosis. And we call this region of interest. Our model is based on patches. So we crop the relevant tissue into small patches, and we try to predict the type of the polyp from these patches. We have a look to our data set, and we see that the number of the slides for each pathology is related to the frequency of the pathology itself. Also, the relevant amount of the amount of the relevant tissue that is taken from the biopsies is related to the diagnosis hypothesis. So we have a huge imbalance between the annotated tissue. The dataset also includes the slide sources of the already public available on this topic Unitropatho dataset. We divide our dataset in at slide level because one slide means one patient. So we don't have any overlap between patients from the test set and the training set. A validation set is taken at region of interest level from the train set. Talking about the method and the pipeline is quite similar for training and inference. We take the region of interest image, we slice it into patches, pre-process those patches, and after that, we train the neural network on the patches that predicts level label, the slide label. Also for the whole slide, we take the whole slide, we slicing it into patches, pre-process, feed the network, and after we have the prediction for each patch, we can try to make a prediction on the entire whole slide by maximum voting criteria. Our model is a fine-tuning of a ResNet model pre-trained on ImageNet, and we choose the best model in terms of balance accuracy on the validation set. The patches are taken by using a sliding window method and resized to the common resolution for the ResNet. We use a lot of data augmentation for this data set to achieve better performances, and we include vertical horizontal flips, random operations, issues in between rotation, equalization, solarization, inversion, and contrast announcing. So our findings are on the preliminary work we've done to take into account these tasks. We can see in this graph the balance accuracy achieved by using a patch of different resolution, different physical resolution. And we find also different results by having a different type of preprocessing. We can see that the grayscale images do not remove useful information, and on the contrary, helps in removing the expected color biases. Goal that is not achieved by using techniques for color normalization like Machenko. We find these results also when we have the whole slide inference. We can see how by using grayscale patches, so grayscale images, we have better performances for hyperplastic polyps and normal tissue. So this result can extend also to the whole slide inference. I would like to show you some evaluation metrics, for example, F1 score and balance accuracy. And these graphs are show the score for each class, each type of tissue. And we can see that there is no unique choice for the patch resolution. If we want to maximize the performance for finding high-grade dysplasia, for example, we know and we observe that there will be a drop of performances, for example, for hyperplastic polyps. Let's talk about some visualization. I put here some examples. The first one is a normal tissue, is an inference for the normal tissue in white. That is worked pretty well, like the hyperplastic polyp example in red and low-grade dysplasia in green. But I want to focus on the last image for the grayscale dysplasia, and we can see that we can find also low-grade features inside the tissue that represent high-grade dysplasia. At the end, we evaluate the attention map generated by our model by using the GradeCam algorithm with our pathologists. And we can show that effectively in the top right corner, for example, the hyperplastic polyp, the model is focusing on the serrated gland. And talking about the dysplasia, the pre-neoplastic lesion, it can be found at the bottom right corner. That is an example of high-grade dysplasia sample. And that's, thank you for attention, that's all. And if you want to contact me, you have the mail on the bottom. Thank you very much.
Thank you. Questions? I have some questions. First, I would like to ask you if you know what type of staining was used to create these images and the magnification of these images that you showed us, which is a magnification factor.
Of course. hematolin and
hematoxylin
stain.
and eosin. Yes.
Yeah, of course. And the resolution is over there is 20 per magnification.
And did you try to, or are you willing to test also for other magnifications, this method?
No, because the material, the slides are given by all pathologists, and some examples are 40 per magnification, but we have to take the lower of the all data sets. So we have not all the samples with different magnification. We have not the effort to make so much scans.
Okay, okay, thank you very much.
Thank you.
Now we go to paper MD201, evaluating mobile teleradiology performance for the task of analyzing lung lesions on CT images by Ömer Kaya, Çukurova, University of Turkey.
Yeah, hello from Turkey.
Hello.
Now it's really my turn.
Yes.
Sorry, this one. Can you see my screen?
Yes.
Yes. Okay. It's okay. Hello again. I will present you evaluation mobile teleradiology performance for the task of analyzing lung lesions on CT images study. This study was conducted for Ezi Kara from Boğaziçi University as a PhD thesis. But as two radiologists, İbrahim İnan and Ömer Kaya, looked to the CT images and evaluated the lesions. First, as introduction, I want to say the accurate and precise measurements of lung lesions on computed tomography images is a challenging issue in cancer management. Lung lesions size measurement at baseline CT image is necessary in assessing the likelihood of malignancy and in determining the algorithms to be used for follow-up. Lesion size determination on CT images is also required for assessing response to therapy. For the patients, also we are looking to follow-up CT images for lung malignancy patients and comparison the lesions measurements. The different causes of uncertainties in lesion size measurement have been investigated. It was found that inter and intra-observer variability can be substantial. Other uncertainties are related to imaging parameters such as imaging system hardware, software, and imaging acquisition, display monitors, ambient light conditions, and patient's motion. However, to our knowledge, the effect of mobile teleradiology on measurement uncertainty has not been addressed before. Generally, we are looking to the CT images also on normal computer screens, but this study we evaluated mobile teleradiology, mobile screen. The use of portable displays in the telemedicine practice is becoming increasingly important. Recently, a number of portable technologies such as laptops, tablets, and smartphones have been evaluated for their suitability for teleradiology. It has also been pointed out that these technologies start to make a major impact in global health by providing the cooperation between distant medical centers. Our objective was to investigate the achievable performance in mobile teleradiology using a mobile phone in comparison with normal computer screen. For this study, data were imported from the cancer imaging archive and 271 lesions between 3 and 51 millimeters were assembled. Of those, lesions less than 5 millimeters are often ill-defined on CT scans and have not been considered for measurement experiments. Overall, 183 lesions were considered for the measurement studies. Images were obtained using different CT scanners, technique factors, and slide thicknesses. The measurements have been conducted by two radiologists from University Hospital from Adana and Birun University Hospital Istanbul, Dr. Ibrahim. Radiant Digital Imaging and Communication in Medicine, DICOM, viewer version 4.1.60 was utilized to examine lung CT images on ViewSonic DICOM calibrated PACS monitor. A mobile DICOM viewer named Medfilm was used on the iPhone 6s model smartphone. The images were shown in random order to radiologists with at least 7 years experience. Data were produced by the radiologists who evaluated the images on each display with a time interval of 3 weeks. In the slide, we can see the technical specifics of displays, the screens. As expected, of course, the normal monitor is also better than the phone screen, you can see. As a statistical analysis, the blend Altman method was used to analyze the results. Normality of data was assessed by using the Shapiro-Wilks test as well as visually by inspecting the histograms. The limits of agreements were defined as 0.025 and 0.675 percentiles. Whereas for compared using the non-parametric squared rank test. In this slide, the statistical plan for measurements are seen. I want to tell more details from the numbers. We will speak in the other slides details. Observers accurately detected 98.2% of the lesions on the medical monitor, while we detected 92.8% of the nodules on the phone screen. We can see that in normal monitors, in normal display, also we detected more than the phone monitor. The undetected lesions were all under 5 millimeters. They were all really small lesions. And Table 2 demonstrates that there is a small offset in the difference between the types of measurements. The bias between the two observed readings was found negligible for both displays, for normal monitor, for iPhone screen. There was no bias really much. The uncertainty and the bias do not seem to change sensibly with tumor size within this chosen range. For a lesion of 10 mm and higher, these uncertainty intervals for two readers are quite smaller than the 5 mm interval for deciding stable disease. Also, it's as expected for bigger, larger lesions. Uncertainty interval also smaller, but for the less than 5 millimeter small lesions, it's much. With each one observer, the use of phone versus the use of medical monitor, normal monitor, was found to produce less uncertainty than the one produced by two observers using a standard medical monitor. The standard deviation of errors due to the difference between observers is lower for the medical monitor. The results confirms the previously stated conclusion that readings by multiple observers consistently are not recommended in assessing lung lesions. I think in this study also the first objective was to compare the screens, but in the results I think this is the most important part because for example if we follow up a cancer patient. If the first evaluating made by me and the other one from another doctor, there can be also some changes in measurements. So others must be the same doctor in follow-up. To the best of knowledge, this study is the first one to assess mobile teleradiology. We didn't see another study just like this for lesion measurement purposes using lung CT images. Our results show that the phone may present difficulties in detecting new small lesions. It's really a handicap now that for the smaller lesions with a small screen. Sometimes we can detect it. Also, a previous study on iPad, there was a previous study with iPad, but not phone, had shown that lesion detectability can be satisfactory for these small lesions. The previous study mentioned above had shown that iPad is adequate for detecting these lesions. The two studies can indicate that mobile teleradiology may be feasible. Based on above given findings, it may be preferable to have the same radiologist perform reading using a portable display outside the hospital rather than have another radiologist perform the follow-up reading using a medical monitor. I said it before. It is really important. Follow-up, if we can, follow-up must be made by the same radiologist. DICOM collaboration and the use of better, larger portable displays, such as tablets, can be expected to further reinforce these conclusions. Further studies, therefore, can be beneficial with a higher number of radiologists and different types of medical displays, DICOM viewer software programs, and types of portable displays, which may be greatly changed from hospital to hospital. As a conclusion, mobile teleradiology can be a potential feasible alternative for the accurate measurement of lung lesions on CT image when needed. However, due to lower lesion detectability on the phone, a larger and higher resolution screen technology may be necessary in order to detect new small lesions less than 5 millimeters. Results also suggest that subsequent readings by the same radiologist with mobile teleradiology may produce less uncertainty than reading by different observers on medical monitor. Future studies are needed to extend these results to other mobile technologies. Also, I suggest you read the full text. Thank you for listening. It's finished.
Thank you for the presentation. Are there any questions? I would like to ask you one question.
Yeah,
do you
please.
think that the radiologists are open in accepting this kind of transformation in their routine and using their mobile phones if they prove in the future able to, for diagnostic purposes? Or they want to stay in their traditional ways?
I think can be. For example, in our university, in our department, now we are, I think, 10 lecturers, and 2 of them, me and another doctor, make this. We can use, if we follow up this same patient, we can use our laptops or our tablets. In fact, our tablets from house, if you are not in the hospital, we are following up the lesions by our tablets. I think in the future, more radiologists will use this technology. Because it's really important that following up must made by the same doctor, because, for example, if there is a lesion, like, for example, there is a Superman S, this is a lesion. I'm making the measurement like this, and the another doctor make the measurement like this. It is different. So it's really important issue, and I think in the future most of radiologists will use this technology, especially in university hospitals.
Okay, thank you very much.
Thank you.
And we're moving to the last 2 presentations, which will be given by the same person. First one with MD202 paper, Learning Transferable Features for Diagnosis of Breast Cancer from Histopathological Images, from Maisum Mohammed Al Zorgani from the University of Bradford, United Kingdom.
Welcome everyone. My name is Maysoon Al-Zergani. I am a PhD student at University of Bradford, UK. My pleasure to be one of the participants in this conference. The subject of my presentation is learning transferable feature for diagnosis of breast cancer from histopathological images. The outline of my presentation is divided in introduction, the objective of study, material and methods, experiments, results, and conclusion. Concurrent with the progress in the whole sliding images scanner for digitizing histopathology slides, it has become necessary to develop computer-aided diagnosis systems for optimizing the diagnosis efficiency of diseases, as well as reduce the diagnosis time and cost. The CAD systems assist the pathologist with some of the tedious and laborious routine tasks, hence reduce this their workload. Recently, the CAD systems that build on a deep learning have achieved agreed results in the application of histopathology image analysis, whereas employing of such systems avoid the use of hand graphic technique that extracted of specific visual feature manually. Furthermore, they need trained pathologists for selecting the useful features. So we need a deep learning technique because it can extract high-level abstract feature automatically from the image in standardized way. The objective of study. Nowadays, deep transfer learning is considered as a perfect solution to overcome the problem of data scarcity that is necessary for training deep learning algorithms from scratch in the digital histopathology domain. Fine-tuning a pre-trained convolution neural network and off-the-shelf feature extraction are the common deep feature learning approaches. The architecture of a deep learning network has a significant role in choice of the optimal learning transferable features to adopt for classifying a cancer's histopathology images. The objective of this study is investigating three architectures of a pre-trained convolution neural network, ResNet, DesNet, and ShuffleNet, for classifying the grade of breast cancer. Material and methods. I will start with a target dataset. Our target dataset is a breast cancer histopathology challenges 2000 dataset, and always known as the batch. A batch challenges was coordinating with the 5th International Conference on Image Analysis and recognized it. There are two main parts in the challenges. The goal of this, the first part, was to classifying hematoxylin and eosin staining breast cancer images into 4 classes. You can see in these images: normal tissue, benign tumor, in situ carcinoma, and invasive carcinoma. And the goal of the second part was to segmenting the pixel-wise labeling of whole sliding images. In this paper, we work on the first part, which composed 400 images with the same size, 2048 and 1536 pixels, and each class contains 100 label images. Continue with the material and methods. as a batch dataset image are not standardized, we still normalize them as stated in the reference file to reduce the color variation. This reference can and others introduce the non-linear mapping approach to normalize of hematoxylin and eosin stain in breast histopathology images by using image-specific color deconvolution methods. There is a stain normalization toolbox for some technique in this website. And for more information, you can visit this paper to understand how the authors normalize the images. The batch dataset images were divided randomly into training set 80% and testing set 20%. As the batch dataset image number is small, hence we have increase the training images number by rotated and flipped them in both directions. The choice of the appropriate off-the-shelf feature extractors for our application is essential step. So we have investigated three pre-trained models, namely ResNet 50, DisNet 201, and ShuffleNet models. This figure illustrates the proposed framework architecture of image-wise classification. The framework consists of three parts. The first, batch model, global model, and hierarchy voting model. Let's start with the batch model. The original image divided into 12 non-overlap batches with the size 512 by 512, and the batches resized according to the feature extractors. And the deep features here represent local feature vectors that use it to train target classifiers. Let's go to global model. The global model take original image and resize them into according to the feature extractors, and these features represent the global feature vector for the images, and use it to feed or use it to train the target classifier. The last model, hierarchy voting model, consists of two batch level voting and global level voting. For batch level voting, to select a specific prediction vector that represents a high probability, where the global level voting to get the final classification. Go to the experiments. Three experiments were carried out by using batch dataset. In each experiment, one of the three models was employed as a feature extractor to extract deep features from the average global layer. The extracted deep features were utilized to train two target machine learning classifiers, namely kernel snable and support vector machine. We set the support vector machine classifier with an error correcting output coding function, and the experiments were implemented in a MATLAB 2020 environment on this specification of a desktop computer. Now let's move to the results. We can get these results matrix of target classification with the different feature extracted by using the confusion matrices, 4x4 confusion matrices to represent the predicted result of our result. Here we can use this, and by applied in this equation, we can get this result. You can observe it. You can see from the fig that support vector classifier with the DISNet get the good result or the highest result according to the others. And you can see from this table, DISNet support vector machine get accuracy 93.75 and default 0.9379. Comparative analysis. The comparative analysis of the obtained results from our experiment with the sum of the published work that used the same batch dataset is reported in this table. It can be observed from table 2 that a DISNet with support vector machine achieved the highest accuracy of 93.75. While DISNet with the nurse neighbor 88.75 achieved a good result compared to the others. This result confirms that our framework in terms of accuracy, classification accuracy outweighs the other methods that use the same image dataset. In this study, we can conclusion my work as in this study we have explored three off-the-shelf feature extractors to overcome the automated multi-classification challenges of breast cancer grades. We leveraged of the generalized property that makes the deep feature transferable to other applications. So such property is useful when the dataset is not enough for training the convolution neural network from scratch, as in the batch challenge dataset. Target classifiers that trained on the extracted deep features from the net model outperformed the others in terms of classification accuracy. The deep features of this net architectures are learned better than the deep features of the other architectures. Our results indicate to the high robustness of the proposed from work. This is references. Thank you for listening. Any questions?
Any questions? Yeah, I would like to ask you one. Do you remember how many neighbors did you use in constructing the k-nearest neighbor?
Can a nurse neighbor use?
Sorry, it was not clear because you had some interruptions.
Your question, what the value of k, yes?
Yes, exactly.
Yeah, my value of k is 4 because I classified four classes.
Okay.
Yes.
Okay, thank you. And we can go to the last presentation.
Yes.
Paper MD 200. Yes.
It's me, yeah.
Yes, I know,
Okay,
but I will just read the title of the paper,
okay,
and
yeah.
you can have the floor again. Okay. MD 205. The title is Deep YOLO-based detection of breast cancer mitotic cells in histopathological images. And please.
This second talk about deep YOLO-based detection of breast cancer mitotic cells in histopathological images. The outline of this presentation, introduction, the objective of study, material and methods, results and conclusion. Let's move to the introduction. Starting with a Nottingham grading system that has been widely used to estimate the breast cancer grades based on 3 morphological features. in histopathology images. A nuclear tiba, a tubular formation, and mitotic cell count. In histopathology image analysis, the mitotic cell counting is a significant biomarker in the prognosis of the breast cancer grade and its aggressiveness. However, counting task of mitotic cell is tiresome, tedious, and time-consuming due to difficulty to distinguish between mitotic cell and normal cells. Computer-aided diagnoses have been lately advanced to perform counting tests of the mitotic cell in histopathology images. Hence, the pathologist can utilize this as a second opinion system. The objective of my study, since the improvement of CAD systems is unimportant with the progress of deep learning networks, so this work is investigated deep YOLO, you only look once version 2 network for mitotic cells detection on international conference on batch recognition. And now this dataset is also announced mitosis 2012 dataset of breast cancer histopathology. Now turn to the material and methods. The first step in our methods, data pre-processing steps. We still normalize images of mitosis dataset as stated. I talk about this reference in the previous representation because it is a new reference and there are toolbox exist in the website to reduce the color variation. We augmented training data to enlarge mitosis dataset by rotated the training image with a large of 180 degrees and then flipped them in horizontal and vertical direction. The second step, data preparation. This is important for my subject because I am here establish training data table and testing data table as MATLAB files. And each table contains two columns. Column for holding the image paths and the other for holding the dimension of mitosis bounding box. Each bounding box is a vector with 4 elements on formula, x, y, width, and height. As you like in these pictures, this is point x and y. And this dimension is height, and this dimension is width. And the other step, anchor boxing choice. The mitosis dataset is annotated by the pixel level ground truth type, which provides us with enough information to estimate bounding boxing for mitotic cell using intersection over union distance metric. From numerical analysis, we determined 32 anchor boxes with 64 and 128 scale 265 YOLO version 2 performance requirements. Proposed architecture. The proposed architecture is inspired by YOLO version 2 architecture. It's composed ResNet 50 as a feature extractor, followed by YOLO 2 detector layers as illustrated in this figure. This is image, and I touched the image with the size 521 by 3. And this represents the feature extracted ResNet 50. That means the weight is here is initializing from this model and added 2-layer detector layer here, this and this YOLO detector layer. And this is for classification, and this for transformation, and this output to 32 anchor boxes. Result recall precision and F1 score. Substitute precision and recall here to get F1 score. A T1 here, number of the predicted cells that intersection with the corresponding in ground table, ground truth. A false negative is number of cells in ground truth that have not been predicted. A false positive is number of the predicted cell that wrongly predicted as the mitotic cell. Results. The analysis of our detector with some of the work that were previously published on the same mitosis dataset is illustrated in a table, this table. It can be observed that the obtained result of the F1 score is 0.7903. This result confirms that our proposed detector is in terms of detection accuracy outweighs the other methods that use the same image dataset. Conclusion, in this study, we have investigated YOLO architecture to tackle the detection problem of mitotic cell in breast cancer histopathology images. Therefore, I present a simple data detector based in YOLO architecture to leverage of XSP. The proposed detector is the modified YOLO version 2 with the ResNet 50 backbone network as a feature extracted. The result evaluated on a mitosis dataset demonstrate that our detector is robust. Reference, thank you for listening. Any question?
Thank you. Any questions?
Yeah, you have a question.
I have a question for everyone. The question is whether you think that your detector could be applied in the analysis of apoptotic cells, cells that undergo apoptosis.
No, I can't understand. What's the meaning of apoptosis?
Apoptosis, cell dying, when the cell dies.
Yeah, yes. We can apply this algorithm on this, but you need to training the algorithm to this image.
Mm-hmm.
Yeah.
Okay, thank you very much.
Thank you very much.
And thank all the participants for the very interesting presentations and timely presentations. So I think I can give the floor to Dora if she's connected. The
Yes.
conference has, yeah, okay, so you can go on from here. Thank you.
Okay, thank you, Dimitris. Thank you very much. And now we will take a break. And after the break, we will have the keynote speeches. And it is wonderful not to be missed. So please be back before 11 o'clock. Okay.
Thank you. Bye-bye.
Thank you. Bye.
Thank you.
See you later.
Thank you.
The summer's calling. The summer's calling. If the kingdom is overthrown, meet me at the cornerstone. I know that I can't be without you. This bond is solid gold. We're a diamond and an emerald. It took me forever to find you. 'Cause when it's all over, the love that you give will be there to guide you in every way. Now we've been through the cold and darkest days. The summer's calling. As we wait for the smoke to clear and we watch our dreams appear, I know that we can rise together. This vision that we share is ours. Together we can touch the stars. I know that we will see December. 'Cause when it's all over, the love that you give will be there to guide you in every way. Now we've been through the cold and darkest days. The summer's calling. Faded in this dark and smoky room, with your face reflecting bright green, brights and blues. You know I kinda want to disappear with you, but I don't think that is what I would usually do. You know it's just like I felt the heat the moment he pressed his lips up against mine. Don't wanna fuck this whole thing up like I do every time. Fire is burning through this silence. I can't take it, can't control this flame we started. You know I'll find in my heart, yeah. In the quiet, all my thoughts run free. So I drown them out at night with my TV. You know I got to try to ignore these thoughts that go What does perfect even mean? Is there even such a thing? Ooh, can we switch up all the rules and imagine a utopia? Darling, I'm just so fed up with these expectations. They keep weighing me down. My heart is begging me to get the hell out of my head. I'm gonna live inside the upside down for a minute and pretend, honey, I'm a perfect 10. Whoa, whoa, honey, I'm a perfect 10. Whoa, whoa, and if I say it enough, it gets ingrained in my head, and I start to see, honey, I'm a perfect 10. Honey, I'm a perfect 10. Whoa, honey, I'm a perfect 10. Honey, I'm a, yeah. Yeah, I've discussed it with myself, and I'm disgusted with the way we're told to have a certain face, a certain weight, because we aren't pixels on a screen. No, we're human, we breathe. Every single thing we see curated, it's overrated. These expectations, they keep weighing me down. My heart is begging me to get the hell out of my head. I'm gonna live inside the upside down for a minute and pretend, honey, I'm a perfect 10. Whoa, honey, I'm a perfect 10. Whoa, and if I say it enough, it gets ingrained in my head, and I start to think, honey, I'm a perfect 10. Honey, I'm a perfect 10. Whoa, honey, I'm a perfect 10. Honey, I'm a, yeah. Oh, oh, oh. empty town. I'm searching for the lost and found. But you don't care, you're unaware. Keep moving like the scars aren't even there. It's in the air, like a blazing flare. Don't stare, cause the flames will burn us. I thought you were the one for me. That's why I gave you everything. Held you close by the stormy seas. Oh, you meant the world to me. I used to kiss your head when you cried for me. Hold your hand while the pain was over. Keep you warm by the roaring sea. You meant the world to me. Oh, you meant the world to me. Oh, you meant the world to me. My darling dear, you're never here. When I'm in pain, you hide and disappear. Like shadows in the atmosphere, charting the stratosphere. Yeah. I prayed for you and kept you near in hopes you'd chase away my fears. I'm on my own, you made it so. And now I'm chasing nightmares through. I used to run with you through the great big leaves. Laugh at you when you laugh at me. Hope for us because I believe the home was just you and me. I thought you were the one for me. That's why I gave you everything. Held you close by the stormy seas. Oh, you meant the world to me. Oh, you meant the world to me. Oh, you meant the world to me. Oh, I'm gonna do this on my own. No point in blaming you, you did not know. Oh. I thought you were the one for me. That's why I gave you everything. Held you close by the stormy seas. Oh, you meant the world to me. Oh, you meant the world to me. Oh, you meant the world to me. Oh, I'm gonna do this on my own. No point in blaming you, you did not know. Oh, oh, I'm gonna do this on my own. No point in blaming you, you did not know. I thought you were the one for me. That's why I gave you everything. Held you close by the stormy seas. Oh, you meant the world to me. must be more to life than this. Reaching for the stars, traveling so far, like a dragonfly. Just grab my hand from heaven send. With me tonight, I run away. hidden from heaven sent with me tonight. Trying to find a place in this world, reaching for the stars, traveling so far like a dragonfly. Keep your secrets there, hide them everywhere. Just you and I. We'll never forget the past, but what counts is our brand new start. Even if it hurts me or I get scared, just come take this risk now. We'll be prepared. Trying to find a place in this world, reaching for the stars, traveling so far like a dragonfly. Keep your secrets there, hide them everywhere. Just you and trying to find a place in this world. I was so sure of our love. I never thought of any reason, a doubt about us. And now I'm right back at the start. Halfway through a bottle, baby, and nothing to know. I thought that I could keep it low. Take it easy, take it slow. We ended up just like before. So take it easy, take it easy. I thought that I could keep it low. Take it easy, take it slow. We ended up just like before. So take it easy. And you know how to forget all the wrongs and every reason why we've changed. And there's a storm inside my head. It's getting me in trouble, baby, and I can't break away. I thought that I could keep it low. Take it easy, take it slow. We ended up just like before. So
表もらって今から埋めなきゃいけない。あ、ちょっとそこ閉めてるけど今から僕ね、講演するんだわ。ありがとう。でね、鍵かけといてくれね。ボタンピッと押すと鍵かかるから。
Hello.
Hello.
Hello,
Okay.
Dora.
Yes, welcome back. And now we will begin our keynote sessions. And I would like to invite our session chair, Professor Yudong Zhang. Okay, let's welcome Professor Yudong Zhang.
Thank you, Dora, and good afternoon, ladies and gentlemen. I'm Professor Yudong Zhang at the University of Leicester, UK. I'm also the General Co-Chair of the MICAD2021. Thanks for our conference chair, Dr. Rui Dan Su. Without his efforts, we cannot have such a fabulous conference. Please allow me to introduce the next keynote speakers. The next keynote speaker is Professor Kensaku Mori. He is a professor with the Graduate School of Informatics, Nagoya University, Japan. And he is the director of the Information Technology Center of Nagoya University and MICAD Fellow. His speech title is Future of AI-Assisted Endoscopic Procedure. Let's welcome Professor Mori.
Thank you very much for a great introduction. I will start to share my screen slide. So just wait a moment, it will start. Okay. So thank you very much for inviting me to the MICAD conference. This is a very, very nice meeting. I enjoyed the talks yesterday. So these are very, very great talks, and I learned a lot yesterday. So today, I'd like to talk about some of the future of AI-assisted endoscopic procedures. So my name is Kensaku Mori, and I'm from Nagoya University. So this slide just summarizes my research works at my laboratory. So basically, we have been working on the image analysis, including image processing, machine learning, and visualizations, and sensor fusions. Some of the research topics of us is multi-organ segmentations, and then we convert these results to the surgical navigation systems. So one is a laparoscopic procedure assistance, and the other one is bronchoscopic navigations. Also, such kind of the results can be used for the virtual reality things. Also, we are working on endoscopic assistance procedures like colonoscopic colonoscopy assistance system. So that is certificated by Japanese PMDA. So this is just a summary, and so I just go to the main topics of this today's talk. So this is just the pictures of last meeting in Chicago of the 2019. So last year, all of the others meeting was on the virtual platform. However, this is 2019 pictures. It was on-site conference, and as you can see, the RSNA is going to the AI. So everything now of the RSNA is AI things. And these are the pictures of the AI-related company booths. So the one big floor is occupied by AI, radiological AI companies. So as you can see, the medicine is going to AI now. So it's a big trend in this field. So I think the medical AI is a big innovation in medicines, and many procedures will be automated by medical AIs. Probably this future will come in the next 10 years. And medical AI will completely change the medical science in the next decade. So this is also the probably big topics in these areas. And I think that we are now the status or state of the how to develop medical AI to how to work with medical AIs. So I think that most of the researchers are working on developing a medical AI. Of course, we have to continue this way for our next 2 decades. But also the important point is how to work with medical AI. This is not how to use, it's how to work with medical AIs. Because I think in the future, so the scenes where the medical AI becomes colleagues in medical fields. So such a future is very around the corners of us. So it's maybe in the after 10 years, so the medical AI will become a medical colleagues in the clinical field. So one of the key words of such artificial intelligence or AI is symbiosis. And symbiosis is not a new word, so it's a very, very old word. And this is some of the, this is machine-computer symbiosis papers published in the 1960s. I think also this is one of the textbook of the artificial intelligence. And I think the symbiosis between the humans and artificial intelligence can be said to be a relationship that enhances each other's abilities. So such trends will happen in medical field in the very, very near future. So the most of the current medical AI is kind of the mono-assistant systems. And it will then convert to the multi-assistant. So the AI can diagnose multiple disease simultaneously. And then it will go to symbiosis. So you will work with AI in the future. So I think in operating room, environmental intelligence will exist in the future. One is for decision support or co-worker in the operating room. And in the planning stage, the medical AI coexist with you. And also if you perform some of the patient consent, so also the medical AI will exist with you. So it's, you will work with AI in the future. So this is a very, very, marketing thing. So it's a kind of economical issue. So medical AI market is showing a very rapid growth. And so it's almost, doubling every year. So it's almost, it's very, very hopeful world, hopeful market. So it's probably, it's going to be a very, very big market in the future. So I have been working on the bronchoscopic navigation in 2000. It's a very, very early years of 2000. So that's 2000 or 2001. And that is a bronchoscopic navigation system. And the left side shows virtual bronchoscopic image. So this is a work of 90s. And so you can now fly through the inside of a human body like this way. So it's fly through navigations. And combined with endoscope, it's in the bronchus case, it's a bronchoscopy. So you can, connect bronchoscope and virtual bronchoscope to navigate the physician to the target point. And as you can see, this system is showing at the current location of the bronchoscope. Also, that is showing the anatomical names of the bronchial branches on the real bronchoscopic images. So it's kind of the intelligence. However, at this moment, it was not using any of the machine learning techniques. It's a very, very rule-based technology to segment bronchus from the CT, or just it's a very, very rule-based assignment to bronchial branches extracted from CT. So here is some of the summaries of AIs in endoscopic procedures. One is probably the abnormal region detection from CT or endoscopic images. And the other one is qualitative diagnosis assistance. So we just assist, the AI assists qualitative diagnosis of the endoscopic images. As a third topic, maybe endoscopic procedure decision support. So one is anatomical structure understanding, and one is the surgical flow analysis or surgical procedure analysis. And the other one is probably medical staff support. So this maybe can be done by a surgical workflow analysis or surgical tool recommendations for nurses. And also the patient and their family support is a big issue. But however, in this talk, I will omit this one, but assisting patients or their families is quite important issues when we look at some of the situations in the hospitals. So here, this is a figure just to show the flows from the diagnostic process to the post-operation diagnostic processes. So every of these 4 steps, the AI can be used. First with CT scanning or endoscopies. So the system is using AI for improving the image qualities or for reconstructions. And post-processing is also using AI, such as segmentations and anatomical structure understanding. And surgical planning, so we can use any of the AI systems. And during surgery, so we also use some of the AI techniques. And post-follow-up diagnosis, so we will use AI. So everywhere the AI or deep learning. So I want to show some of the examples of AIs of the endoscopic procedures. First one is colorectal cancers. So the colorectal cancer is also the #1 cancer in Japan, and it is, however, the colorectal cancer, it is possible to completely care for early stage cancers. So if you do the colonoscopy and find the polyps in very, very early stage, so you don't have to worry about the polyps. And however, we have to find the colonic polyps at a very early stage. So colonoscopy is quite important tools to detect early stage polyps. However, we have a problem of lack of colorectal endoscopists and pathologists. So this is a big issue. And recently, Olympus has developed and commercialized endocytoscopy systems. So this is a very, very new endoscope, and it can possibly perform a conventional observation and super magnified observations. So this is this video shows endocytoscopy. So you can see the very conventional endoscopy images with very super magnified views of the colonic polyp surfaces. So you can see some of the cell things on this images, on this endoscopy images. So the total colorectal screening is quite important anyway. So if here's some of the curves of the TCS cares. So this is, if we do a colorectal cancer screening by endoscopy, so we can suppress 53% of colorectal cancer deaths. And also, however, the overlooking of polyps causes 6% of post-colonoscopy colorectal cancer. So we have to prevent the polyp overlooking in the endoscopy. However, 25% of polyps are missed in colonoscopy. So we have to, solve such problems by using AIs. And here shows some of the causes of overlooking of colonic polyps. One is perceptual errors, and the other one is exposure errors. So perceptual errors, so the polyps can be observed on the screen. However, the physicians missed it. And exposure error is polyp is occluded by household falls and cannot be observed physically. So this error can be, this error can be, perceptual error can be solved by using AIs. And so I will show some of the colonoscopy AIs that is called end-brain systems. So the end-brain consists of several functions. One is polyp frame detection and estimate the polyp size, and the other one is this polyp is cancer or not. So firstly, I will talk about the if you find polyps and it's a cancer node functions. So this is just a video of the endobrain system where it has a polyp detection functions like this way. And if the computer finds polyps, it beeps a lot. And then we detect the super magnified views of the polyps. And this system immediately answers the probabilities of this polyp. So this polyp is neoplastic in 98%. This is another polyp like this way. And the computer now can detect the polyp existence. And then we go to the polyp site and then capture the very super magnified views of polyps like this way. And this is non-neoplastic way things. Because we have a basic research on the very super magnified views of the colonic polyp surfaces and also pathological image comparisons. And we found if you take the super magnified views of the polyp surface, and we can estimate the pathological diagnosis from these images. So to do such a classification, so we have firstly introduced texture features and hierarchic features. So this is a very, most of the people or attendees of this conference knows about hierarchic features. And we found that these features are quite useful for classifying the super magnified views of the colonic surfaces to classify this image into the neoplastic or non-neoplastic. And this feature is classified by support vector machines, and we obtained the classification result. And during real-time assistance, we are just showing likelihood that is easily computed from this support planes. And by combining such systems, so we can create this type of a system. So, well, if you find polyp and take super magnified views of the polyps, and then the computer automatically diagnose. And this is another option. So another polyp, sorry. Yes, and the computer diagnosis at a non-neoplastic, so you're like. And of course, we have constructed such AI endoscopy system. So the goal is to commercialize or as a medical equipment to enable us to use such devices in the real clinical field. So we have a lot of work to get a certificate from Japanese FDA. And we have compared, first we have compared the ECCAD computers and experts and non-experts. And first, these are very, very fast papers, and we found most of the diagnostic accuracy of the experts and computers are almost same, and also very, very low in a non-expert medical doctors. So we found very significant differences between the computer diagnostic abilities and the non-expert abilities. And to obtain the certificate, it's a very, very long way. We consumed almost 4 years, and however, we got some of the approval from Japanese FDA, and we just made and we commercialized these systems from Olympus in February of 2019, and it was very, very long way. And the current system can diagnose the polyps in 3 classes. So maybe I hope you can see the video correct way. And however, it is in other 3 classes classifications. And if you have to do some of the biopsies, the computer asks you to do a biopsy. And the polyp detection is most of the basic functions for colonoscopic AI. And in such case, we have to consider about spatial temporal structures in the movies. And we have constructed some of the 3D CNN to detect the polyps from the video sequences. And this is a very, very, simple architectures of the polyp detections from video frames. And this is a very, very fast trial to detect the polyps from the colonoscopy videos. And this is a real, everything is real time, and the computer detects the polyps like this way, and it shows the likelihood of the polyp existence in the left side corners of the movies. And if the computer detects the polyps, it beeps. And in the computer detects the polyps in this such case. So now the physicians are putting a colonoscope, and here there was a polyp here. It's just behind of the half-circle fold, but the computer was able to detect such polyps like this way. So the computer is quite powerful to detect such polyps. Well, of course, the polyps showed up. Probably it's 2 or 3 frames in the video sequences, and that can maybe easily missed by physicians. And combining everything of the polyp detections and the qualitative evaluation of the polyps, so we can create such systems. And it's a kind of the replay of the videos I showed in the previous slides. To go to the next slide. And the polyp size estimation is quite a big challenge for us. And polyp size information is quite important. So we have to, estimate the polyp size. It's over 10 millimeters or less. So, and how to do that? Of course, the appearance-based polyp size estimation is quite a difficult problem. So, it's the appearance sizes and how to estimate the very, very, absolute size of the polyps. So we have introduced some of the, depth image to estimate the polyp size, and also we, gave up to estimate the size. So we just size estimation problem into the 2 class classification problem. So it's a 10 millimeter over or less. And we infer the depth images from input RGB image by using CNN. And depth image is combined with RGB image, and then the classifier estimates the polyp size. This is a depth estimation of the colonoscopic movies. So the right side is estimated depth image, and the left side is RGB image. And we just use the 2 images so we can estimate the polyp size of this. And here's a very simple way of CNN to classify the RGB image for the polyp size. And the computers, actually, so the computer can be classified the polyp size by using the depth images of the polyps. And now, so we were enabled, we were able to estimate the polyp size, but that is, of course, is two classifications. And so I will skip these ones. So the end-to-end series is now extended to the 4 products, and we are commercializing these systems. So one of the specific point is this polyp classification system is extended to other diagnostic system. So of course you can purchase this system in Japan. And the other topic is laparoscopic procedures. well, laparoscopic surgery is a very, very difficult task, and some of the surgical navigations are required. And surgical assistance systems can be summarized as the surgical planning systems and surgical navigation systems and laparoscopic video analysis systems. So one of the big issues of this laparoscopic surgery for stomach is that you have to understand the anatomical structures of the stomach. That is quite complicated. And one of the assistance methods is to display the anatomical structures extracted from preoperative CT dataset by using a deep learning. So it's kind of the unit-based anatomical structure segmentations, and also the blood vessel anatomy is very important in abdominal surgery. So this is a brief overview of the blood vessels of the upper abdominal areas. And of course, you can extract the blood vessel regions from CT dataset. However, you have to also understand the anatomical names of the blood vessels. So we have utilized the graph convolution network to assign the anatomical names to each blood vessels like this way. And the another surgical assistance system is the scene recognitions and showing of the 3D views, which is very appropriate to the this kind of surgical scenes. And now the computer is understanding which process of stomach cancer surgeries, and this one is some of the place of the cutting the blood vessels, and the computer understanding such scenes and then showing the 3D rendering to assist such surgical procedures. Also, surgical scene recognition is very important. One is anatomical structure recognitions, and bleeding area recognitions, and instrument recognitions, and surgical task recognitions, and surgical process recognitions. So everything provides a very, very big areas of AI or deep learning based image segmentations. And by using a multi input directed units, so we are segmenting the blood vessels like this way. So this is IMA, inferior membranostic arteries. So that is a very main arteries in the lower abdominal areas. And the computer is segmenting a very important blood vessels from laparoscopic videos. However, the future, we have to find some of the correspondence of the preoperative CT scans of these extracted blood vessels from laparoscopic videos. Or by combining Euro and units, so we can segment the bleeding areas from the laparoscopic videos. So now the green area is our cyan area is bleeding areas that are recognized by computers. So it's a bleeding area recognition is also important point. And surgical instrument segmentation from laparoscopic video is important. And I will skip these topics, slides. However, here some of the segmentation results. So we are training the AI, or that is kind of based on the unit by using a synthetic data set to make a lot of images. And this is surgical to segmentation result. Well, of course, this domain conversions probably will help us to endoscopic procedure in the future. The upper row is virtual colonoscopic views constructed from CT or rendered generated from CT dataset. And we can convert such colonoscopic views, virtual colonoscopic views, to very, very realistic colonoscopic views like this way by using cyclograms. And this kind of the views can be utilized for some of the assistance of the endoscopic procedures. So I think the environmental intelligence in operating room will become possible in the next 10 years or maybe 15 years. So as from now, we have to start to think about how to work with AI in operating room. So this is just summarizing my talk. And well, of course, I can say the anatomical structure information is key information in AI in endoscopic procedures, but it's hard to obtain annotated medical data. So it's we have to think about this, and also we have to think about implement a mechanism to train the AI in different institutions or countries. One of the solutions will be a federated learning or the utilization of the synthetic images. And computer resources are quite important issues for developing medical AI. Thank you very much. That's it. And this is my talk. And thank you for joining my talk.
Okay, thank you, Professor Mori. So I will leave it to our audience. So do you have any questions or any comments? So try to drop the messages in the chat box or in the Q&A. Hi, Professor. May I ask you a question?
Yes.
Yes. I saw from your slide you said the colorectal cancer is like the #1 cancer in Japan, and you mentioned you have developed some endocytoscopy, which is a new endoscopy that can achieve like a 300 to 500 magnification. Can you introduce more to this new endoscopy?
Oh yes, this is it's not out of my work. However, so I can show some of the videos from the Olympus. It's a kind of the endoscope which has the very big microscope inside it.
Thank you.
Yes. So that is why you can take very super magnified views. So the conventional endoscope lens location is fixed. However, in this endoscope, so you can move the lens location like a zoom lens of the camera, and that is why you can take a 300 times or 500 times magnified views. Okay.
Okay, thank you. So I think our researchers and particularly our audience, suppose they also focus on the colorectal disease, they may benefit from this new method. Okay, thank you.
Thank you.
Okay, cheers. So now we will move to our next keynote speaker, Dr. David Golan. So please allow me to briefly introduce Dr. David. He is a co-founder and the CTO of Vis.ai, a digital healthcare company harnessing deep learning to analyze medical data and improve clinical workflow. Prior to founding Vis.ai, Dr. David was a Fulbright postdoctoral scholar at Stanford University. That's very hard to obtain. And he is working on leveraging deep learning for the analysis of medical imaging and genetic data. So his title is Saving Lives at Vis.ai. So let's welcome Dr. David.
Hi everybody, and thanks for the opportunity to speak here. I think this is to me particularly exciting. Myself, I'm no longer a researcher, an academic researcher for quite some time, rather, I guess, a real-world practitioner. But we are lucky to live in an era where the two things converge, and we're seeing more and more applications of medical imaging analysis and AI in the field, actually helping patients, actually improving care, and saving lives. So I think we're all very lucky that we can exercise our skills and exercise our passion in a way that's so meaningful. So as you kindly introduced, I'm the Chief Technology Officer and co-founder of Viz AI, and our main focus at Viz has been treating stroke. So just a brief background on stroke, or specifically here ischemic stroke, which is the most common type of stroke. So ischemic stroke is typically caused by a blood vessel being clotted. So here you see a clot blocking the blood flow in a blood vessel in the brain, and brain tissue here is deprived of oxygen and nutrients, and very quickly deteriorates and dies. And basically, dead brain cells, they never recover, so the patient may lose very important functions and even die. So our goal of treating these strokes is to open the blockage or reperfuse the patient as fast as possible, open the blockage either with a mechanical procedure or with drugs. So why is stroke so interesting? First of all, top 5 killer all around the world. In the first world, there are other conditions that kill more people than stroke, but stroke is by far the single largest healthcare expense, because of the unfortunate reality that stroke patients who don't die often remain with significant functional issues, and they often can't work anymore. This creates a lot of expense for the healthcare system. They may need assisted living, and of course there's loss of income for the patient and their families on top of the personal tragedy. It is also one of the most time-sensitive conditions in all of medicine. So 1 minute of delay in providing the therapy to a patient translates to nearly 2 million dead neurons, which means over 4 days of added disability on average per minute, which is it's just an astounding number. And people have also done financial analysis of the cost to the healthcare system of the additional disability and so on. So every minute we're talking about an additional over $1,000 of healthcare expense that could have been saved, and that's just for 1 minute of accelerating. And here on the right, you can see how the probability of a patient surviving a stroke with and being independent, being functionally independent, drops very, very, very dramatically over time. So we have a serious condition that is killing a lot of people, hurting a lot of people, creating huge expense, which is also indirectly hurting a lot of people because that money could be invested elsewhere. So, one of the surprising things is that, as I started learning about stroke, is that there's a huge problem of undertreatment. So only between 10 and 15 or 20% of patients actually get the appropriate treatment, and even less they get it on time. And then one might ask, if we have something that's such a big deal from a healthcare perspective, from a health perspective, why do we see such massive undertreatment? And the reason is kind of mundane, but it's really, really important to understand when you're trying to connect AI applications in the real world, and that is medical workflow. So let me quickly walk you through the workflow of what happens when a patient is having a stroke. So assume a patient is having a stroke, they identify it, or a family member identifies it, they call 911. Immediately, EMS rushes over, they take the patient to the hospital, they go to the ER for a quick evaluation and triage. From there, they are typically sent to a CT scan very, very, very quickly. They go back to the ER while the results are being processed, read by radiology. Sometimes, if we're lucky, they can cut through the queue and get to the radiology fast. In many, many circumstances, they get in the queue, especially if it's night, weekend, if it's a teleradiology service, it may take a long time. The results go to the ER saying there is a suspected stroke. Now we need to involve neurology and make the decision on medical treatment. The neurologist might need to consult with an expert because they may be less experienced. At this point, they're starting to consider surgical options like mechanical thrombectomy, a more serious intervention. So they need to talk to an interventionalist. That interventionalist is often not even at the same hospital, because most patients arrive to the nearest hospital, and most hospitals don't have the capacity to provide intra-arterial therapy to stroke patients. So we need to somehow communicate the patient data to the interventionalist, and from there we need to activate a team, because the mechanical intervention is a serious process. So we need to transfer the patient to a different hospital. We need to get an anesthesiologist, a nurse, the residents, everybody need to get together in their hospital, and only then we can treat the patient. So there is a very, very long series of steps and handoffs here. Each one is an opportunity for a failure, of course, and each one is an opportunity for a delay. And this is why, despite the fact that we're obviously racing against time here, we're seeing very, very significant delays, and this is actually the norm rather than the exception. Here we're looking at average statistics over, the stroke registry in the US, so very, very diverse amounts of data. And what we're seeing is, and this is breaking down this patient journey that I described into the different blocks. And what we're seeing is that actually most delays happen after the patient is in the hospital, and actually after the patient has already been scanned. And when we started working on stroke at Viz.ai, this was sort of the aha moment for us, that we said, how can this be that on a computer somewhere, there is the data, there is a CT scan that shows that the patient has a stroke. So the data is there, but it takes so long before this data is put in front of the right doctor, right? It goes from one doctor to another, to another, to another, until it gets to the decision maker. And it's a serial process. It's a long process with a lot of opportunities for delay. So the vision of Viz.ai is to really change how this is done and use artificial intelligence to identify those stroke patients and immediately communicate to everybody in the team. So we're moving from a serial process to a parallel process. We're making everything, all the data and the images accessible through a mobile app. So wherever those people are, and we've seen cases where some of the team were on a plane or driving or even on a boat, they can all get the information in the mobile app, they can communicate. And our vision was that this could facilitate much, much, much faster care, right? And actually shift the treatment timeline from what you see on the top here to the bottom, and just take this human-based serial handoffs and make them into computer-driven, AI-driven parallel process that's just way more efficient. Right. So that's basically the vision of our product. We've built it and actually got FDA clearance 3 years ago. So this is how the system works. Indeed, the patient walks into a scanner in a hospital, any hospital. The data goes to the cloud, is analyzed within 3 minutes by the artificial intelligence engine based on deep learning, and I will dive a bit deeper into that in a few minutes. And if we identify a stroke, we alert everybody in the team, facilitating faster transfer, faster treatment, and so on. So over the last 3 years, we've seen very rapid commercial adoption of the Viz.ai system in the US, starting from very few hospitals, now in over 600 hospitals. And initially, as we started rolling this out to more and more hospitals, there were more and more anecdotal evidence that this is actually working. People posting very exciting posts on social media. Here, for example, on the left, we have Instagram, Twitter, LinkedIn. So on the left is one of my favorites, Boca Raton, Florida, one of the first hospitals to use the system. And I'll just read quickly from here. They're saying, the cloud-based software sends real-time alert to your iPhone, definitely reduced time to reperfusion in 2 stroke cases we completed before noon today. And what you see in the images is you see the alert that the physician is getting, and then you see the CT angiogram, and the purple arrow here indicates where the occlusion is. So this here is the stroke, the clot that is blocking the flow. And here below on this 4x4 is the actual clot that was pulled out of the patient brain, reperfusing, renewing the blood flow, and saving the brain of the patient. But what's even more exciting than this anecdotal evidence is, as more and more hospital systems have implemented the Viz.ai system, we've started seeing more and more publications where those institutions have compared their performance pre and post implementation of the AI system. And we've seen publications demonstrating significant time savings. So 66 minutes here, for example, in a system in Texas, reduced length of stay of patients in the hospital, improved outcomes, which is the holy grail, what everybody is looking for, actually demonstrating that this AI makes a difference in the real world. So the NIH stroke scale and the MRS modified ranking score are two ways to measure the neurological function of a patient. And we're showing a significant decrease in the score. So high score means a bit more issues. Low score, 0 means normal. And also we're seeing that implementation of the system stops leakage and increases the number of procedures that are actually performed. And that's really important because these are patients who just had no opportunity to enjoy the benefits of therapy. So with the system, they're not lost between the cracks, and the system picks them up, make sure that the right people know about them, and they can actually activate the system and treat those patients. Right. So for us at Viz.ai, this has been probably the most exciting thing that we've always deep in our hearts believed very strongly that the system can make a real impact on patients. But now seeing the evidence pile up is very, very exciting, and seeing more and more hospitals adopting the system, with so many more hospitals adopting the system, actually generates opportunities for additional research. So this is a paper we published that surveys the performance of the system, what we call performance in the wild, quote unquote. And sort of the motivation of this paper was typically when someone develops an AI system, they write a paper about it, testing it on a relatively limited or relatively homogeneous data set, typically from their own institution or from a data set that's publicly available. And even commercial applications, even FDA clearance is typically based on data from 2 or 3 medical institutions. And these are, it's not only a small number, these are typically very good, very cutting edge academic centers that have good, they have high budgets, they have good equipment, they have good technicians, they have good staff. So it's not surprising that the performance, there's some sort of bias here where we're generating overconfidence in the ability of AI systems all over the world because we're looking at very biased and high quality data sets. So the motivation here was to provide a very robust estimate of performance. So we have here data from 2,500 patients in almost 140 hospitals. And we made a lot of effort to have no cherry picking. So we annotated sequentially data from these sites. So not dropping out problematic sites, not dropping out low quality scans, including both what we call primary stroke centers, which are the smaller hospitals, and comprehensive stroke centers. So different quality of hospitals, all CT makes and models. So as you go out to the field, you find sometimes surprisingly old, some antiquated CT scanners that obviously generate lower quality scans. So really want to include everything. And we estimated the sensitivity of our algorithm at a bit over 96% and the specificity at 93.8%, which for us was very good to see that our performance is robust even at those sites. And the combination of the high performance of the system and the proven clinical impact has led the Centers of Medicare and Medicaid Services to grant this technology, what's known as a new technology add-on payment, which is a reimbursement code. And this is the first and only reimbursement code for AI in the US. And essentially what it means is that when the patient is scanned and the scan is processed by the Viz.ai system, the hospital may be eligible for up to $1,040 of reimbursement. And that's obviously a significant amount and a strong motivation for hospitals to adopt the new technology. And this is exactly what the NTAP plan was designed for, to accelerate the adoption of new technology by providing incentives via reimbursement. So, enough fluff. So let's talk shop for a bit. How does it actually work under the hood? So here's an example case. This is a scan. We're seeing the CT angiogram. On the left, it's the axial view. On the right, it's the coronal view. This is a 49-year-old female that was scanned. Well, all the cases I'm sharing here, by the way, are real cases from our production environment. And this was flagged as a stroke, as a large vessel occlusion stroke by our system. So let's see what the algorithm did behind the scenes. This is the input of the CTA scan. I mean, here I'm showing only the 2D MIP, but this is actually a 3D, obviously a 3D scan. And this is important. Everything that the algorithm does works in 3D. From an implementation perspective, this was definitely fair price in terms of performance. The CT angiogram scans are typically very high resolution, so it's a big, big 3D array. But as I will show you in a bit, it really did pay off in terms of our ability to find small small strokes and so on. So first step is extracting the soft matter. Second step is alignment or registration of the soft matter to make sure, and we're seeing a lot of variability in how patients are positioned within the gurney of the CT scanner. So just normalize it. And then we're feeding the scan through two neural networks. One is a semantic segmentation-based unit-inspired network that segments only specific vessels. In this example here, you see the what we call the MCA, the middle cerebral artery, on the left and on the right. So it identifies specific anatomical segments. And the second network provides a full segmentation, a 3D segmentation of all the vessels in the brain. So one of them is very specific and identifies specific targets. One of them is broader and segments even very, very small vessels. And then these two are combined into what we call the vessel tree. And you can see, I think in this picture, it's nice to see just how variable the vascular anatomy in the brain here it can be. Even if you look at compare for one patient, if you compare the left and the right sides, you can actually see a lot of difference. For example, here, this patient this is the right side of the image, the left side of the brain, has here what's known as a fetal origin PCA. This small vessel here is a vessel that we all have, while we're fetuses in the womb, and it typically disappears a little before birth. But about 30% of us, it doesn't disappear, so we live with an extra blood vessel in the brain, and we've had to actually overcome this. This has proven a challenge in early development for networks because it may bypass certain blockages. And you can see this patient has it on one side and doesn't have it on the other side. Some people have it on both sides, and of course, most people don't have it at all. So again, we're combining these two, the outputs of these two models into a vessel tree, and then we're tracing the vessel and identifying endpoints. And for each endpoint, there's a classifier that decides whether it's an actual occlusion or just a byproduct of the scan quality or something like that. So in this case, the algorithm identified the endpoint, said yes, it's an occlusion, marked it here, and we generated an alert. This is another case here, a more distal occlusion that smaller and smaller, and again here the sort of the 3D modeling approach pays off, because if you're looking at 2D at those small vessels, it's not at all clear whether there is an occlusion or not. And I'm not a neuroradiologist by training, but we did show this to neuroradiologists, and yes, this is indeed a hard case. So we can actually go pretty far with this approach that is like not a black box deep learning classification, but rather using deep learning for very good segmentation and then tracing the vessels and then using another classifier. Lastly, the last example that I remember this, and this was a very exciting case for me personally. So this is an alert we received. So this is how it looks in the mobile app. It opens at the slice, and you see. And my initial thought looking at the scan was that this was a mistake of the algorithm. I monitor the algorithm very closely. It's sort of it's a personal thing for me. So I mean now it's more challenging with so many hospitals, but until I don't know, a few months ago, I was looking at almost every alert. So here I was thinking, oh my God, this is the algorithm screwed up. We need to improve. But a few minutes later, we get what's called a perfusion scan, and the perfusion scan analyzes the blood flow in the brain and actually shows that there is this green and red that you see indicate a perfusion deficit. So there is a stroke. Okay, so I go back to the scan, I'm looking very carefully, and I can't really find a stroke. And again, I'm not a trained neuroradiologist, just a hobbyist, I guess. But in the app, there's actually, and this is on a mobile app, there's actually a free-form 3D rotation capabilities. So after investigating this a bit more, you can actually see that there is a branch, there's a vessel here that is occluded here, where the cursor is showing. And this is, if you're looking at the axial view, it's actually completely hidden. If you go back to the previous image, you see this branch here is just completely hidden from sight. The occlusion is exactly hidden from by another vessel that is hiding that occlusion. So it's actually a very hard occlusion to spot. And we've received very good feedback on the fact that the system has caught and flagged this occlusion. So yeah, so I would like to stop here and see if there's a question from the audience. From my perspective, again, this is a very exciting time to be practicing the art and craft of medical imaging analysis and deep learning in this context, as we're really seeing this going out to the wild and making impact on patients. And yeah, and I appreciate again the opportunity to be here and present to you. And we'll stop there and take some questions.
Okay, thank you, David, providing us such an excellent presentation. I will leave we have still like 3 minutes, so only one question can be raised. Professor, may I ask you a question?
Yes, of course.
In your presentation, you mentioned you have developed an AI-powered stroke triage system. Can you introduce more to that system? Whether, for example, they have helped the practical situations in the realistic patients?
Yeah. So I've showed some of the publications where actually we are seeing the system making a big impact on patients. And there's several publications out there, more coming out, that actually showing how healthcare systems work faster because we're generating this automatic link between patients and users. And being academics, we'll appreciate the power of scientific research and publications. But what's really impactful is the anecdotal, like the stories. So, for example, often what happens is you have a patient in a small rural hospital, and they get a scan done, and the alert shows up on the phone of the interventionist in a different center, right? And they read the scan, they confirm the stroke, and they call the different center and say, hey guys, you have a patient with a stroke, we can help them. We actually sent the EMS to pick them up. And these guys here, they're not even aware that the scan was completed. So this is making a big impact on patients.
Okay, thank you, David. I think our researchers have a lot of also engaged in the research of the stroke triage system. They will definitely benefit from your developed system. Okay, thank you again.
Thanks. And I think there was the interesting question from James Duncan here on the performance in the wild. So I'll just take 30 seconds to answer that. So definitely, we're collecting a lot of data. Outside of that, we're constantly annotating and looking, and definitely you can see which scanners and which configurations cause lower performance. So definitely. And one of the most interesting things is that we are now identifying, now we have so much data, we're doing sort of a big data analysis, identifying which configurations yield better performance, and we go back to the sites and we recommend that they switch. And we've been able to identify sites that use, for example, a wrong convolution kernel, use a body convolution kernel for head scans, and we'll say, hey guys, why don't you switch it? And they switch it, and all of a sudden you had plus 5% points in accuracy. So definitely, this is providing a very powerful tool.
Thank you, David. And due to we have limited time, we will not accept any new questions. So maybe suppose any audience have any new questions, you can email David. Okay, thank you, David. So now we are very honored to have the opportunity to of inviting the Mr. James Duncan as our final guest speaker of this session. So please allow me to briefly introduce James Duncan. Professor James Duncan is the Ebenezer K. Hunter Professor of Biomedical Engineering and a Professor of Radiology and Biomedical Engineering, Electrical Engineering and Statistics and Data Science at Yale University. He is a Life Fellow of IEEE and a Fellow of the Amber and MICAD Society. He has served as the co-editor-in-chief of Medical Image Analysis and an associate editor of IEEE Transactions on Medical Imaging. And his speech title is Neuroimaging Analysis in Autism, from Model-Based Estimation to Data-Driven Learning. Without further ado, please welcome our keynote speaker, Professor James Duncan.
Thanks very much, Yudong, and thanks for the invitation from the organizers, and I enjoyed the last few talks, so nice to be here. So I'd like to talk today about our work in neuroimage analysis in autism, as it was introduced, and this is a collaboration between our image analysis machine learning group, Larry Stabe, Nisha Dvornik, myself, Xiaoxiao Li, who's now at Princeton as a postdoc, and Juntang Zhuang, as well as Pam Ventola, who's in our Child Study Center at Yale and is a child psychologist. Basically, our goals of this work are to find biomarkers for characterizing autism and then use them to help guide and predict therapy. So autism is a spectrum of disorders. It's basically characterized by impaired social interactions, sometimes language problems and repetitive behaviors. But there's a variety of comorbidities, including anxiety and mood disorders and hyperactivity and other things, and even sometimes intellectual disability. So it's a spectrum because of these range of symptoms and severities. And its prevalence is high. This quote says 1 in 59 in the United States, but I think it's up to 1 in 45. And it's about 4 times more common in boys than girls. And still, causes remain unknown, and psychologists and therapists tend to treat symptoms. Our initial work at Yale was in collaboration with Bob Schultz, who was at our Child Study Center back in the early 2000s. He's moved on to University of Pennsylvania. But in our earliest work, we looked at structural magnetic resonance images, trying to look for things like volume changes indicative of autism. But Bob brought us into looking at functional MRI, task-based fMRI. And his earliest studies were to look at, trying to look at the differences in reactions to alternating 24-second faces, houses tasks with subjects in the magnet, with the idea of trying to bring out an emotional response, perhaps, or recognition of faces. And so the initial study was about 14 autism subjects and 14 controls, young male adults. And using just general linear methods and this task-based fMRI, Bob's work found that in the young male adult control, the normal subjects, both two areas lit up in response to this task. A blue-purple area that was a parahippocampal place area, really recognizing that objects are present, as well as a fusiform face area showing recognition of the human face. But in the autism subjects, only the parahippocampal place area lit up, implying perhaps that there was no real recognition of human forms or faces, and that the autistic subject just saw faces or houses as simply a thing or a place or an object. So fast forward to about the early 2010s, Bob left. Kevin Pelfrey became our new collaborator at the Child Study Center. He's also since moved on to the University of Virginia, but we still collaborate. And around this time, Archana Venkataraman came to us, graduating from Polina Gollin's lab at MIT as a postdoc. And Archana said, let's relook at this problem in a different way. And particularly, let's apply the neuroanatomical atlas. She chose the Destrio atlas of about 150 regions, and then look at correlations between these regions, as the field had been doing and is doing, to get these connectivity maps based on basically Pearson correlations. And there was one set of data, or one set of subjects for the typically developing control subjects, and another set of data for the autism subjects. And she's hypothesized or posed the idea that there were underlying neurotypical and latent organization of autism spectrum templates that could be found and uncovered, guided by the idea that there were communities or groups of regions that might work together in a certain way. Basically, the idea here was to look for connectivity, or she called synchrony, and discretize into low, medium, high, or simply low and high synchrony or high connectivity, and then compare group data between regions to decide if the synchrony was lower or higher in autism or in normal groups. So this was then set up as a joint probability density function with the two data sets, B and B star for connectivity, the underlying F and F bar, the functional organization of the connectivity, and then the region membership in one type of community or another. Given that there were so many communities, just a few were posed in certain prior parameters. So in this work, Archana used expectation maximization to solve a maxima posteriori estimation problem and estimate the underlying synchrony or connectivity maps and whether any given regions belong to one of just two or sometimes three abnormal functional communities. The task was a little more sophisticated than faces and houses, but tried to do the same thing, basically that there was a human light point form of trying to bring out a human response, and then scrambled a pattern of just these lights these tasks called biopoint, and alternating 24-second increments. So in this biopoint task, there were 72 children, ASD children, 43 age-matched controls. And here are the results using this Bayesian estimation algorithm. With two communities posed, the pink community that was found was declared hyperactive or hyposynchronous in that there was increased connectivity in autism subjects, F bar being greater than F for the regions in that community, and a blue or hypoactive or hyposynchronous community where there's reduced connectivity in ASD, F bar being less than F. If you took these regions and mapped them out onto this popular neurosynth database that's gleaned out of the lots of papers in the neuroscience literature, you can see that the hyperactive community maps onto things that are strengths in autism, like visual perception and pattern recognition. But the hypoactive community, more prevalent, better connectivity, reduced connectivity in autism, mapped onto these more emotional regions. So these are strengths in the normal subjects, but weaknesses in autism. So all of this is group data. And we wanted to get to individual and subject analysis in order to guide therapy. So the next evolution of our work was to move towards individualized biomarker detection from task-based fMRI again. And we started doing a classification task and then using this task then to uncover biomarkers. We started this work using intensity-based data, using convolutional neural nets and data-driven work and ROI ablation analysis to see which were important. But we most recently evolved to using graph convolutional networks. And this work's shown in MICAD2019 and 2020. So let's look at this setup. Basically, as other groups have certainly done, we think of the brain mappings as a graph. We switched to the Desikan-Kiliani atlas, which posed about 84 regions of interest. And so the graph nodes are each region of interest plotted here as a graph. Hanging on each node are node features, and started with about 100 features in each one of these regions, including the bold signal mean, the bold signal standard deviation, Pearson regular correlation, if you will, to all ROIs, and then the ROI coordinate. The node edge or the graph edges or connections were formed by basically control correlations between regions, not controlling for everything else or all other relationships. Basically a partial correlation, which gave a sparse connectedness for the E or the edges. Now we, unfortunately, as Dave was talking in the last talk there, we are also using small sets of data sets for a variety of reasons. So augmentation was important by basically resampling, training data to get resampled values and build up the database. So the processing pipeline for our graph neural net brain network analysis, we have task-based fMRI data, brain parcellation using the Desikan-Kiliani atlas. And in each region, there's basically mean time series that come out from that. We do a correlation, in this case, both Pearson and partial correlations, and you can represent it here, and then change that into this functional graph. The graph network processing then reduced it to, after graph convolutional layers, to fully connected layers to do the classification. And from this, we infer communities, do classification, and extract biomarkers. We could use this same scheme for prediction, but we haven't moved that. We do that a different way, excuse me, as you'll see later. You might say, why graph neural nets? Well, we like the scalability of adding features and nodes. As you'll see, they turn out pretty effective. And because of the sparse nature of the nodes, they're quite efficient. And also, I would argue that they're a little bit more directly interpretable in many cases. So here's our brain graph neural net, brain GNN. Take the initial graph and run it through these graph convolutional blocks, basically 2 of them in series. Each one of these blue blocks has 2 blocks embedded in it. One, a graph convolutional layer, or a node convolutional layer. And this basically is aimed at, where here the node features are changed and are reduced to some efficient information, but the graph structure doesn't change. And then in a second step, there's a node pooling layer where the node features don't change, but there's a reduction in the number of nodes to make it more efficient. And then at the end, everything's aggregated into a vector. So the first stage then is this graph convolutional layer in this classification biomarker and recovery stage. We call it region-aware graph convolution. And we would say that in the traditional graph convolutional net, all nodes are treated identically. Basically, you're applying the same kernel to all nodes. But when the nodes have spatial relationship information, and we're going to assume this and embed it using the community ideas that I talked about earlier in our group work, we want to use this to reduce the number of features at each node, basically based on ROI-aware relationships. So we start with a we have to determine and declare the number of communities, and then declare a random initial community assignment. And then the processing will do a conditional kernel embedding based on the communities and do a feature reduction. Basically what this means is we're assuming a basis function for each beta for each community, and we get a weighting alpha and an offset B that sort of filters down the overall weightings to map them into this community-based space that'll reduce the features. And furthermore, we start with the H sub I features at each node and the E weighting to the surrounding H sub J information and get out a set of weights. But this new set of weights are going to be based on this setup in the community representation. And in this, I would just note that alpha I sub IU is the membership likelihood of ROI I in community U. And again, beta sub U is each community's basis function. So we start with the raw features, and then after these sequential steps of our region-aware convolution, get a new H tilde, and that is based on the relational information, the surrounding information, but embedding the idea of communities. These are the weights that have to be learned, both the ultimately the basis functions, the offsets, the weightings alpha that then end up weighting the W's. All of this is done to reduce the feature set, as I said, and is done for all the processing. So if we start looking at it, again, using these same 72 ASD and 43 healthy controls, we have to declare the number of communities. We declared 8 for starters. And this came out of work from a sister lab at Yale, Todd Constable's group and Emily Finn, where they looked at community clustering and autism and came up with that number approximately. This is from these data, and you see the 8 communities clustered here. And the community membership, as I said, is declared by, here's all the ROIs, the 84 and the Desikan-Kiliani Atlas. And then here's the 8 different communities listed here. And community membership is declared after looking at the alpha values and usually thresholding for only those that are greater than a half in order to cluster into the 8 communities. So that's the first stage. The second stage of processing is this pooling stage where we do salient ROI selection. And as I said, then from the first stage, we reduce the number of features now. Oh, I wanted to point out, actually I meant to do that back here, that basically you could think of all this as kind of a PCA-like reduction into the principal components that are the basis functions of the communities. So by limiting the number of communities from the maybe many, perhaps 50 or tens at least, if not 100, to just 8 communities, we look to reduce the number of features at each node to about 10 with H bar. And then we do a projection. There's different ways of then doing pooling. You could do magnitude-based reduction. We project onto a virtual pooling vector that's normalized between 0 and 1. And then giving values to all the different nodes and their feature sets. This ultimately yields a node score assignment of different values. And then basically we do a top K-like reduction to just keep the high scoring nodes. So it keeps the same number of features, but reduces the number of nodes. As perhaps some of you know, there's some limitations on top K pooling in terms of the ability to regulate pooling scores, and perhaps some issues with rankings different for different input instances. Because of these limitations, we propose to do pooling using an overall loss function for the training of this overall graph convolutional neural net scheme, and embed these distance and group level consistency losses into the loss that's just the cross entropy training of the training data, the original data. So LCE is classification loss. The second term is a distance loss that enlarges the distance between important and unimportant nodes. And the final term is this group consistency loss. And what this allows is whether we want it to be fully individual terms or learning, or we allow some group training from the data set or consistency towards the group data to come into play. So here's that loss function just repeated, just noting that the group level consistency is basically taking the pooled data and saying each individual subject should be close to it over all the regions based on a norm. So the final term, as I just noted, is to do this node reduction. And I would just point out here's that when we weight the group consistency loss very low, like 0 perhaps, you have more of an individual biomarker. And as you weight lambda 2 higher and higher, there's more common important ROIs over the training data. So you move towards a group biomarker, although probably the answer is a compromise in between the two. And in fact, here's 3 visual results of 3 different subjects looking at the left-hand and right-hand side. And then with 3 subjects here plotted in the columns with lambda 2 equal to 0, 0.1, and 0.5. And as you see in these circled regions in each of the subjects, as you apply or enlarge the lambda 2 values, a little more smoothing in here. Now, we haven't mapped these to the NeuroSynth database yet, but we do feel we're getting plausible regions that are reasonable biomarkers compared to our former group data. So we are, these are some selections out of these 72 actually ASD subjects. The classification testing overall, so remember we go through these early convolutional stages, then do a fully connected reduction to do classification, and that's where the previous biomarkers were extracted from. But just to look at the classification accuracy and compare to other methods, we augmented the data 30 times, the 72 times 30 and 43 times 30, the ASD and control subjects to get these kinds of numbers. So we had over 3,400 data sets, divided that into 5 folds. So it's about 690 graphs each. Use 3 folds for training, 1 for validation, 1 for testing, and then do rotate that and do a cross validation. So if we compare the different methods in the literature, some simple methods, and here's the number of parameters you need to learn on the bottom here, times 1,000. So that's just 3,000 parameters, 138,000, et cetera. Support vector machines, the classification accuracy is only 62%, same with random forests, but you do have less features. When you get to multi-level perceptrons, a little bit better, but there are lots of features. A convolutional neural net based on just intensity time series data, you are getting up to pretty good accuracy, but you have over 1 million parameters. And then different versions of our own work and work in the literature got a little better with graph nets. Here's our sort of current approach for the brain GNM. We're getting up to 78% accuracy, which is some of the best we've seen in comparison. And we have a mid-road, sort of about 41,000 parameters that we need to train in these networks. But we feel the work is promising. We're getting towards individualized biomarkers, and we're encouraged. So now I'd like to switch gears a little bit and talk about prediction. And can we predict outcome from baseline information according to certain ASD severity scores? Now, ultimately, we want to use the classification-based biomarkers to steer or guide attention to different regions. But in this initial work, we used all the regions on another atlas. But where we're headed is the most effective autism therapy seems to be different cognitive therapies. And at Yale, one in particular that's been doing well is pivotal response therapy. And this is our collaborator, Pam Ventola, and her daughter, who doesn't have autism, just sort of showing the therapy. It's a really intense therapy over 4 months with every day 5 or 6 hours of commitment to work with the children to try to teach social skills and bring out social responses. There's no one size fits all, but it's important that early intervention is done to help these children, these subjects. So can we predict treatment outcome from baseline imaging measures is the question. So we again did task-based fMRI on these children at baseline using a variation of our biopoint task with human like forms as 24 seconds alternated with scrambled light patterns. Here are the acquisition parameters, about 3.5 cubic millimeter voxels and these alternating coherent and scrambled light point patterns. We only had 21 children to start with because these are such difficult 16-week treatments. We're now gathering a larger and larger database, and there were 14 male and 7 female. Typically, the early work was done with subjects or participants who had reasonably high IQs for autism children. And the measures that we had were both pre and post-treatment severity scores, a variety of autism diagnostic observation scale measures, but the one we focused on was this social responsiveness scale score and asked, could we predict that? So the idea is to predict treatment response. We looked at % change in this social responsiveness score between post and pre-treatment with cognitive therapy. And can we predict this based on pre-treatment baseline scan information only? And it might be helpful to know that the lower the SRS score, the better the social function. And the idea with all of this is that predictive modeling could help guide treatment assessment and encourage parents to participate in these difficult and involved cognitive therapies. So in this work, Nisha Dvornik, my colleague, and worked with us and helped develop this scheme, was published initially in MICAD 2018. And here we used an automated anatomical atlas. About 90 regions were used, neuroanatomical regions. Within each region, there is a time series data set that was pulled out. And we included phenotypic information, as you'll see, mainly age, sex, full IQ, and initial SRS scores, and ran it through a learning algorithm to do a regression and to get the change in output. And as you'll see, this learning algorithm we used initially in all the regions was a recurrent neural net based on long short-term memory modules. And then the outputs were this treatment outcome, as we said. So this is an interesting idea. I really learned, I enjoyed, we're still working with these LSTM ideas, long short-term memory recurrent networks. And perhaps, as some of you know, these LSTM modules are each made up of sets of learnable weights, basically 4 layers of these, a forget gate layer, an input gate layer, a current state update, and an output layer with a variety of connections. Again, because of the obviously lower amounts of data, we had to do some augmentation. So we randomly sampled voxels in each region and replaced the time series in those with time series information from the training data randomly. So the 90 AAL regions were used, and we'll steer these later on biomarker analysis, as I said. So we sample the voxels in the ROI with replacement, compute the average time series, do this data augmentation resampling about 50 times. Here's the architecture for the recurrent net. So there's, we looked at 156 time points, basically seconds, and each time point or time window had its own LSTM cell. And a vector of ROI values, 90 of these, were put into each cell. So for each cell, then, there are 8 LSTM nodes, as I showed earlier, and for each node, there's 4 sets of weights that need to be learned. All this is task-based fMRI, as I noted, and they run sequentially and then go through a fully connected output layer to do the regression or prediction. To add, we added the phenotypic information as an initialization, basically, to initialize the first hidden state of the first cell, and then connect the phenotypic inputs to a dense layer representing the initial hidden state and the initial cell state, and then propagate it all and pass it. So using that architecture and the basically 20 subjects for training times 50 augmented data sets, we got to about 1,000 training subjects, and then 1 test subject was used with a leave one out rotation. to do cross-validation. And just again, reminder that 90 regions per time point. So here's the algorithm predicted outcome, and here's the true outcome, which is change in the social responsivity score. So if you just use the raw image data, there's a correlation between predicted and true of just about 0.35, although it is significant. If you add the bootstrapped fMRI information, we get up to about 0.53. And if we add the augmentation of the initialization with these phenotypic variables, we're getting up to a promising 0.77 correlation. And I would point out that if you used any of these variables alone, there's basically no significant correlation at all. In fact, it's really low, below 0.1 or so. So this really adds something to the prediction problem, and we're quite encouraged and are further pursuing this work, now again steering by the biomarkers from classification. In fact, here's our next directions. We want to include the brain GNN gives us spatially nice spatial analysis, and we want to divide up the time series into windows and do these over all these time windows, and then put it into the retaining LSTM recurrent neural network. And we'll do both classification and prediction, steering perhaps the second stage with biomarkers from classification. And we call this the dynamic spatiotemporal graph. So that's the work. I'd like to summarize by saying we feel these new graph convolutional methods for biomarker identification are promising as early ASD indicators. This machine learning strategy is also promising for predicting response to behavioral therapy, initially using the recurrence strategy. And both, in general for this work, the data-driven networks are important for both of these identification and prediction tasks. Complete time series information can be incorporated. The grouping into communities and subnetworks seems promising for interpretation as well as computational reduction, although we did show that comparison to traditional models. And our next directions are to, there's a lot more resting state data around, so we might do some transfer learning to the task-based data, and also try to look towards using that for looking at invertibility and explainability in the networks. We also have a collaboration with our MR spectroscopy group to look at metabolic biomarkers in addition to fMRI. And personalized and individual analysis is key and will be our future focus. This work supported by NIH, the National Institute for Neurological Disease and Disorders, through this grant. Thanks a lot for your attention. Thanks for the invitation, and most happy to take questions.
Thanks, Professor. We know how busy you are. We want to thank you for squeezing your time out of your busy schedule and for your insightful and thought-provoking presentation. And we, on behalf of all our members of our MICAD conference committees, and particularly our conference chair, Professor Ruidan Su, several in our audience have expressed appreciation for the information you presented, particularly on the brain graph neural network and the ROI-aware graph convolutional layers. And they said that they were unaware of those networks. I will pass over to our audience. Here we receive a comment from Dr. Zhou. He asked, thank you for a very inspiring talk. On the graphs of ASD, can you provide more details on how data augmentation is performed on the graphs?
Sure. So for the prediction graphs, that was this slide, and basically, maybe I went through it fast, I apologize. Basically, it was, we consider each regions randomly, and then the voxels in those regions, and just sample them, sample a certain amount, and then go to the training data, and for the sampled voxels, let's say even up to 50% of them, just replace them with random time series data from the other training data. So basically, it's just the augmentations. You have training data, you have the regions, you look at them randomly, you look at the voxels randomly, and you do a sampling and replacement with training data in order to build it up. And that just gives you new instances and new examples. For the classification, it's basically similar, I forget, for the graph nets, it's also basically the same rough idea. we just go in and I don't know if I have the right graph here. It's just, again, just sort of sample the nodes, sample the features, and do random replacement. I'm sorry, I don't remember which slide I put it on. But it's the same idea, just trying to do sort of augmentation and get variation in the data as best as possible.
Oh, okay, thank you. And I received a second question from one of the audience. And so I forwarded the question in our Q&A. The question is, the loss consists of 3 parts. What are the meanings of these 3 parts?
Okay, let me go back to that. Yeah, okay. Oh, right. So, yeah, so here's the loss. Yeah, thanks. So, right. So the first one is the overall network loss. So that's the cross entropy loss. You have training examples where you have ground truth, let's say in the classification, you know, whether it's task, you know, whether it's ASD or normal. And then you have the input graph, and that's, you're just training up whether the overall loss to whether it classifies accurately or not. These other 2 terms are important for the pooling layer. And I had other slides, but I don't think I have them in here. This one is just basically looking at pooling distributions, and you're trying to sort of force the top K loss to enlarge or emphasize the difference between important and unimportant nodes based on these node scores from the projection onto a pooling vector. And the final one is this group consistency. It's a little harder to understand, but it's basically, I showed it here, it's just an L2 norm for the information in that region from the group training data. And for that individual subject, what's the difference for that region from the group data? And you can weight that, as I was saying, to include a higher or a less weighting as to similarity to the group data. So the 3 terms are basically the normal cross entropy loss for training, a term to sort of emphasize the differences in the important and unimportant nodes for pooling, and an overall consistency to the training data, which is something you can kind of dial up or down and see. It's really empirical at this point of how to set that lambda.
Okay, thank you, Professor James Duncan. Sorry, the time is limited. We received many other questions and comments, but because the next session will start, so I just suggest to those audience, if you have any more questions, you can contact Professor James Duncan via the email or some other things. Okay, thank you again, James, and we hope that we can meet you next year. Thank you.
Yes, thank you for the invitation. Thanks a lot. Have a good meeting, and hopefully next time in person.
Okay, thank you. Cheers. Bye.
Bye.
Okay, thank you, Professor John. And let me introduce our next session chair, Professor Joseph, and who comes from the University of Iowa, and he is a fellow of IEEE and AIMBE. Okay, let's welcome Joseph.
Thank you. Hello, everybody. Good morning or good afternoon or good evening. It's very nice to be here. Thank you for inviting me. So I'm the chair for this next, and I think last session. We have 3 speakers. And let me introduce our first speaker, Dr. Liu. So Dr. Lei Liu received his MS degree in 2004 and a PhD in 2007 in computer science from Johns Hopkins University. In 2006, he joined Siemens Corporate Research at Princeton, New Jersey as a research scientist. During his 7 years at Siemens, he made significant contributions to the company's CT colonography and LungCAD products. From 2013 to 2017, he worked as a staff scientist at the National Institutes of Health Clinical Research Center. He went on to found NVIDIA's Medical Image Analysis Group, at which he held the role of Senior Research Manager until June 2018. Since then, he's been the Executive Director at PAII Incorporated, Bethesda Research Lab in Maryland. Dr. Liu's research interests lie in medical image computing and analysis, statistical deep learning, clinical informatics, and novel imaging biomarkers focused on the areas of oncology, radiology, and discovery of cancer treatment solutions. Please join me in welcoming Dr. Lei Liu.
Yeah, thanks for inviting me here. I'm very happy to share our recent work. It's really the work we published in the last 2 years. Let me share my screen. Okay, so you can see my screen, right?
Yes.
Okay, I will start. So yes, happy to share our work for everybody here. We are a research lab located in Bethesda. We have teams in Shanghai and Shenzhen. We are part of the Ping An Insurance group. So today I mostly will talk about a full pipeline imaging biomarkers for screening, for diagnosis, and for prognosis. That's basically cover the full spectrum of cancer disease, a very difficult cancer disease. So the following are the hospital we work with. We have other hospital I did not put here, but in general, we are very fortunate to have like many top hospitals in US, in Taiwan, and also in mainland China to work together. So this is my talk will be a little bit more clinical, and also I thank for Jim's talk. I think Jim actually talked about a few things we share. Even he's most working on brain biomarker and mostly on oncology biomarkers. So this are the building where we're located. So this is the main team about doing the pancreatic imaging, including the management team and also the clinical team and also the technical team. So it's really a multi-disciplinary research environment. So here is actually, I give you some brief introductions about oncology imaging, which I worked for almost 15 years since I joined Siemens. So we have a few like a solid tumor, major solid tumor that's listed here, like brain tumor, lung tumor, liver, pancreas, and colon. In my life, I worked on lung, liver, pancreas, and the colon. So I never really worked on the brain, but I cover most in the torso, especially in the abdomen. The few casings in the clinical workflow, they are, I work in Siemens, I work in the hospital. Even right now, I work for an insurance company. So I'm more on the clinical side. So in essence, like technology to enable novel clinical applications, to really down to the earth to how to treat the patient, how to impact the lab positively. So there are a few things under the hood. One thing, of course, we all know is segmentation. The other thing is how you translate segmentation and detection into a diagnosis. That means typically for differential diagnosis means that really, what kind of subdisease this patient has, this type of thing. Why it's important? Because the precision diagnosis directly impact, the treatment plan, right? The other thing, which is very important and become more important, is the imaging genomics. It's not just for genomics. It's like imaging, like radiology. I'm mostly working on radiology imaging. Radiology imaging is less invasive. It has some radiation dose from CT, but mostly it's non-invasive, right? So, so a lot of researchers they're working on to map from the radiology imaging biomarkers into the like pathology biomarkers, genomics biomarkers, and other things. Even just look at those textures, those soft tissue patterns much more closely in a quantitative reproduced way. That's also very important. So this is actually very important about the imaging characteristics, because you try to get the DNA sample or you try to get a pathology, that means you have to basically at least do a biopsy on the tumor. So that's more invasive, or even do a surgery. So I think most of the research efforts have been in this characterization part. But it's become more important. It's about the prediction and prognosis, especially about staging. You know, what's the optimal way of doing staging? For many, many years, it's the TNM standard, like tumor grade, nodule, and metastatus, right? This is the metastatus status. So that's basically the recommended clinical guideline. But by no means it's optimal. It's just what we human beings or human physicians, they can follow in a reproduced way. So certainly there are a lot of things you can go in there for the more precision, more precise staging, quantitative staging based on evidence. I believe there is, you can do a lot of precision medicine there. You can really help patients get a better treatment or more personalized treatment. Another thing, after you get treatment and even on or off the treatment, you will need to see the changes over time of those solid tumors or maybe cancer recurrent, or or even like a metastasis, right? So this changing status also is very important about the cancer recurrent and even the treatment response. So in this talk, I will briefly actually cover all of them. I'm trying to. I mean, this lecture is mostly for like a little bit higher level information. I do give you a lot of detail and pictures, but this is really I'm trying to let I know a lot of people, you probably do not know the whole picture. I'm trying to cover most of the material based on our recent work. Okay, so in this talk, I will use the pancreatic tumor or pancreatic cancer as an example. Why we choose that is, in US, at least in US, right, the 50% of the medical care spent for the last 3 weeks of the patient care. So when they die in the last 3 weeks, it's actually very, very costly, right? And pancreatic cancer is relatively rare, but it's not so rare. But right now it's the third leading death in US, and that will be projected to be number 2 in 10 years, right? And there are many reasons for that. So pancreas cancer, or the major pancreas cancer, is called PDAC. The prognosis, 5-year survival rate is about 9%, 8%, and recently around 10%. So the first time it become 2 digits, right? So the very reason, well, the key reason is they could not, the patient has no symptom at the beginning, right? When they find it, it's often like a stage 3 or stage 4. So it's very difficult to treat, and no matter where you are, and it's really difficult. So the key challenge is there a way we can screening for those very difficult cancer, right? We talk about screening lung cancer and other things, but it has no really like much work about along this line about screening pancreatic cancer. So this is actually a working summation. So this, we believe that's the first work really trying to address the in the scale of screening pancreatic tumor using non-contrast CT, because for general population, you don't do contrast CT just to get a screening, right? And also in China and in elsewhere, people do a lot of chest CT, right? For whatever reason, maybe for lung nodule, maybe for some other reasons, right? So the most of the chest CT covers the majority part of the pancreas. And so, but from the right picture on the top, right? So I'm not sure if you can see my cursor. So from the non-contrast CT, actually, it's very, very difficult. Even if most of the time it's impossible for human reader to find if there is a PDAC tumor in there, right? I cannot see it. But from the bottom left, this is a contrast CT. Human reader actually can see it, right? So we're basically trying to let the machine or let the AI or whatever you call it, it's basically a segmenter, or it's a detecting by segmentation way of doing like a screening cancer to identify it. So on the top right is actually the segmentation output by the machine. it's trending in a way like we transfer the mask, physicians annotated on the contrast enhanced CT, right? Because human beings, a human reader, you could not directly annotate it from the non-contrast CT. Of course, all the patients, we have the ground truth, like we have the diagnosis report, we have the pathology report, and so we their status are certain. So so we really screening, we really like for opportunity screening means like for all the chest CTs, especially non-contrast chest CT, we'll run our algorithm trying to identify a potential T2 or T3 pancreatic cancer patients, right? When they're at T2, mostly they're resectable. And if we can catch them, we perform the surgery right, we can increase the survival rate to 25% to 50%. And the interesting, Michael is not about talking about the technical details, but there should be a publication very soon. We put on archive, you can see it. That's basically using a hybrid transformer, but we do have other segmentation algorithm. The hybrid transformer seems to work better. We have really high accuracy in terms like a 95% sensitivity and 95% specificity. This is very, very high compared to how difficult it is for this problem, in a very challenging imaging domain. So here is, you don't really need to worry about like how machine will outperform human, because this is really not means for human readers. This really means like we build subliminal tools. They're helpful. They can be a special assistant for the physicians to identify pancreatic cancers. And the way is also, when the AI found the suspicious patient, they will refer them actually to a contrast enhanced CT to be confirmed by human physicians, right? So this is a very complementary workflow. Human and the machine, they will live happily ever after for this problem. So, statistically, on the two class tasks, means abnormal and normal, like, we have 8% or 8%, then better than the best human readers. And then for the three class, we're even higher because, machines are better in the fine-grained quantification than our human beings. So that's basically the philosophy. Nothing to be worried about. This really means to be supplementary to human readers. These are more example you can see on the left. I have no way to figure out, and even for the most experienced physician, they could not see it because machine, they're really good at looking at those 12-bit images. Really capture those 12-bit, like those numerical signatures are much better than our visual cognitive system. So this is the static, how many patients we train, and how all the number of reports on the holdout the testing data set. We actually this data set actually covers from 7 hospitals. Of course, under the hood, the most important thing is the segmentation, right? This is a little bit earlier work before the transformer. So basically, the topic about this work I want to discuss about is, what's the way when you have self-collect data, public data set, they are actually in different modality, different phase, and they cover different aspects of the patient, and how, what's the coherent way you can utilize them together to train a better segmentation model, right? So my goal here is not about the federated learning, it's really about underlying hood, how you have a self-learning algorithms, involving teachers, student, and the teacher assistant, all together to get a better death coefficient for pancreatic tumor segmentation. Yeah. So this is basically the data set, the statistics we have, and also the previous work we compare against. So this is actually, this is work was published last year in MICAD. So this is actually the first work, the death coefficient reached to 70%, and before was mostly 50, 60%, because it's really, really difficult. And another thing is like right now we are at maybe 73, 74. You know, I because I know a lot of like audience are Chinese, so I give a little bit Chinese here. So so the key is here about starting the ideas of big data wake label. So I gave a talk like I think 3-4 years ago at the GTC about big data wake label. I think you know, to have more real patient cases are the key, no matter how you utilize it. Because I don't, you know, because human body are very complex and high dimensional, right? It's very difficult, if it's not entirely possible. You know, you can do data annotation, but I do not think you really can simulate a lot of novel disease. So this is basically the data set we have here. So you can consider like a data set B and data set D actually the public data set. And the A and the C are what we collected. And data set A is annotated and data set C is not annotated. So basic way is we trying to infer the labels, the pseudo labels on data set C using a self-learning case, then you know reiterate the training process and using the pseudo mask, and you can increase the reliability or fidelity of the pseudo mask over line. And also another important thing is you know, to find the PDAC much better is you don't only just need the tumor itself, you also need the organs and vessels surrounding. I believe like you know, Professor Murray did a lot of work about the vessel inside the organ and around the organ, right? I remember his early work around that line. So it does help, yeah. Yeah, so then this is actually the third part of the talk. So I give you a little bit, so this is actually into the precision diagnosis or differential diagnosis. Let's say we found some suspicious PDAC, right, or pancreatic cyst. In general, you can call it pancreatic cyst. Pancreatic cyst can be here terms as it contains up to 10 subtypes of malignant and benign pancreatic lesions, right? And they're actually not very rare. You look at the picture on the left, right? So it's actually grow within the age, right? If the people is up to 60 years old, so you know it's kind of like altogether it's about 4 to 5%, right? Yeah, 2.9, 4.0, 8.7. So this number grows, and also Asian risk-wise, Asian is the higher risk population for whatever it may be genetic. We don't know precisely what's the reason. And when people growing older, you know, we are going to have aging society. So we do have more cyst patient, more pancreatic cyst patient, and especially for Asia, you know, for people in Asia, Japan, China, you know, Korea, and maybe even South Asia. So it's a growing, very important like a population health problem. You know, this is the CVPR paper will be present in a few months later. So on the left, this is basically we redraw the picture we learned from the Science Translational Medicine paper from Hopkins. Hopkins has a world-class like a pancreatic cyst center, clinical center. So there are up to 10 types of you know, malignant and benign tumors. And PDAC is about 85 to 90% of that. So the majority are PDAC. They will under different kind of like a treatment, right? When you know when the physician or the machine find a cyst inside the pancreas, or sometimes they can grow outside the pancreas a little bit. The first question they need to answer is, what is it? Is this a PDAC or not, right? So this is the majority question trying to answer. So from the clinical treatment wise, there are three choices. So one is to evaluate if they are resectable or not. You know, if they're resectable, go to surgery, right? So and for other three types, CP, IPMN, and MCN, they can they have a significant opportunity, also have significant probability growing into malignant, but they're not. Right. So this is why you need to classify into high grade or low grade. Some low grade, they never become a cancer, or they have very low risk to become cancer. You don't need to resect them. You need to classify if they're high grade. Yes, you will do a surgery. And for one type is just really like a benign ICN, and then the patient can be discharged. They don't even need to be follow up closely according to the current clinical guideline. So another thing is like a over treatment, right? So you can see is that's actually from the statistics of the Johns Hopkins published article. So about 25% to 78%, it varies from different institutes, right? Under surgery, they actually later found that they are not malignant. So it means that they are not necessary to be performing surgery. They should not be surgery. They're benign. They should be monitoring or discharged, right? So I think most of them should be under monitoring. So you can save a lot of, because the surgery and the resection is actually not very good for the patient. You don't want to go a surgery for a patient who does not really need it, right? So this work is the first. The Hopkins work is really brilliant, and was published in 2019. That's a sophisticated process that I think, or we think, can only be done in a really high level, really sophisticated medical institution. It cannot be performed elsewhere, typically. So our method is address the similar problem, but using or medical imaging, or really, just purely imaging method. The ways we're trying to see, how far we can go just using a pure imaging protocol, right? So our work is mostly on the model underlying is called SMCN. So basically, it's nothing really fancy. It's about first you do segmentation very well, as we explained from the previous work. Then for the pancreas, we actually convert the mass into meshes, and also we can participate the mesh into different anatomical parts of the pancreas, right? Then we actually model the relative geometry from the tumor we found against the anatomy and the anatomical parts. So basically, we know their location, compared to pancreas head, pancreas tail, pancreas body, or which part of the pancreas head body. And also, of course, we collect we collect from the convolution the feature maps. We collect from the feature map. We do the pooling, local pooling from those vertices on this graph. This is basically a graph convolution neural network, right? So this is similar to what Jim was using, but maybe we are just at a much finer scale to really capture the pancreas variations. So in general, we achieve very similar, like go to the next slide. So this is the protocol we use. So as I explained, I will explain a little bit later about how Hopkins was using. So we use pure imaging. We have a more sophisticated imaging protocol for this differential diagnosis, right? Say we find the suspicious patient from non-contrast, then we refer them to do a 5-phase CT scan, and from there, we try to help to do assistance about the differential diagnosis, really the PDAC or not, or other type of pancreatic tumors. So this is a little bit of detail about how the graph looks like. It's actually a figure in the paper. It's already on the archive, so you can refer from there. Now this is a little bit more specific about the segmentation, right? Everything we do, the segmentation is still very important underlying. So our model, the geometry aware model, we capture the autonomy, parts, mass, all this kind of geometry and the texture informations. It helps segment much better for the non-PDAC tumors, right? So from the previous work, almost all the work I work on PDAC, not on the non-PDAC. But this is the clinical need. We need to differentiate PDAC and non-PDAC. So we do need to work on that. And our model significantly better, especially on the non-PDAC mass segmentation accuracy, right? So the deaths improved from 48% to 61%. And also, the detection rate is also much higher, from lower than 70% to close to 89%. Yeah. So this is the statistics about the PDAC and other 9 types of tumor we collect. Of course, really great is how we get this data set, right? So this 1,661 patients is really like we have amazing doctor, we have amazing clinical partners to work with. So we really can advance the science, the clinical, and the technology altogether to provide a better clinical solution for the patients. And this is arguably the most important slides in this work, is about because this is directly clinical relevant, right? The doctor really, they care, but they don't really care about much about how accurate you do segmentation. They do, but it's not direct actionable. So this is actually direct actionable clinical decision: discharge, monitoring, or surgery. We generally did a very comparable result compared to Hopkins, and arguably all these are more unbalanced, so it's a little bit harder. But in general, we say it's similar. So the Hopkins one is really the state art. You can see the beauty of human physicians, the beauty of the top line clinical center, how they perform the precision diagnosis for the patients. Unluckily or unfortunately, most of the people we cannot be treated in Johns Hopkins, right? So they use these clinical features. On the paper you can see what's called clinical feature imaging characteristics. Those imaging characteristics are actually manually performed by the radiologist at Johns Hopkins, and also the cyst fluid genetic DNA sequencing. So it means they do have to get some fluid, from the cyst by doing a biopsy, and they need to do a DNA sequencing, right? This is expensive, and also the tumor can have heterogeneity. The DNA sequence is not always reliable, and also some like a chemical wet lab, markers in there. And our way is really more translational. You perform those 5-phase CT scan. It's not that hard, and many of the places you can do that. And then AI basically can do most of the work after that. And of course we need to improve how the AI and the human integrate workflow, and how we make the result explainable to the physician. It's working online. It's working in progress. We have some exciting result on those clinical trials. So other we're doing computer vision medical imaging. This is basically the picture I want to show. Is basically this is how our algorithm will perform. We basically propose a probability about how the machine think, what's that, and also where's the mask. We hope this way can assist the physicians. So we did a little bit like a preliminary trial. So we only have one reader that's really he's really the expert, and we're comparable, basically comparable to the machine result. This is I move to the third part. It's about the prognosis. What's prognosis about is answer those questions, right? So assume we find a PDAC, and then we ask questions: is this PDAC resectable or not? Right? Or should we do a surgery or not? That's the next question to ask. Then, if the surgery answer is yes, right? Then you want to see is preoperative, means before the surgery. Can we do a direct surgery, or we need to have a chemotherapy to make the tumor a little bit smaller or more resectable or safer to be resected? The surgery criteria is really mainly about the location of the tumor versus the vessels near about it, right? If the tumor is wrapped the vessel, some major vessels is in general considered as non-resectable, but some top line surgeon actually can do it, but still that's more empirical, right? So to answer this question is before is that will be optimal solution for the patient to do a chemotherapy before the surgery, or this this patient can be sent to direct surgery. And also post-operative means like after surgery, should the patient be followed up with radio chemotherapy or just chemotherapy? All these questions right now is actually, it's a little bit more, of course, the physician try the way they can find answer for the patient, but we human is not optimal because this is a lot of guessing in there. There's a lot of guessing, empirical guessing in there. And here is really, we provide a quantitative biomarker, which is highly desirable for personalized treatment with high reproducibility. In clinical, we often emphasize on reproducibility. It means like a intra-operative process. It means like, how this biomarker can be generalizable from one hospital to other hospital effortlessly. I mean, you don't really depend on the special talents of the physician in one institution against the other. Consider you have the top of the line world-class institution, but most of the patients are not treated in there, right? So how we can improve the top of the line physicians, and also this result can be translatable to other a little bit smaller or lower grade hospitals where the patient can get a very similar quality of treatment. Right? That's the goal. That's the how we make technology more useful for the patient is really for this reproducible precision biomarkers that can help as many as patients as possible. So that's really the goal. And underlying you have some novel structures about the network. This is not really the focus of my talk here. And here you can see is we do segmentation. We do like segment a lot of peri-pancreas structures around the tumor and around the pancreas. And so the network actually know all these segmentations that were performed. And here is we use a multitask learning compared to, that's how machine think about, how to deal with this problem. Sorry. So this is basically how the poor or the good overall survival looks like. So human, our work is actually designed from the human beings, from the human physicians, right? They actually they do have a hypothesis. Sometimes they guess what's the poor a good overall survival rate, means how long they can survive. Basically, that's basically the KM curve, right? So there are two things. One thing they guessing is about the tumor attention correction, means how dark they are, how bright they are, how inhomogeneity they are within the tumor, right? Of course, based on manual segmentation. The other thing is after resect the tumor, they will go to a pathology exam and trying to see the cells if there are any like malignant cells on the tumor margin, right? If they are the tumor cells, they call R1. R1 is R0. Of course, of course R0 means like they have better survival.
Dr. Liu, we're running a bit over time. Did you finish?
Okay. Well, I'll finish also. Yeah.
Yeah. So basically, this last slide to explain how the thing work here. So basically is the patient. Basically, there's 3 patients here, and one patient is more deadly. Basically, is higher risk. But you want to have an algorithm which basically can tell them apart before the surgery. About say the patient 1 is actually they have higher risk, they have poor overall survival rate, and patient 2 and patient 3 they have better survival rate. So basically, the algorithm the neural network trying to do is really produce some biomarkers which enable us to stratify the patient so they can undergo a different treatment plan. And this is also show we compare to the traditional radiology radiomics biomarkers where clinical statistically much better. And of course, this can generalize to other tumors as well. That this is OPSCC. That's where Thank you, Dr. Yu. I have a quick question. Could you comment on how the clinicians, radiologists and pancreatic specialists, how have they received this kind of work?
How did you see?
How did they like this kind of work? Are they pleased with this? Yeah.
They love it. Yeah, they love it. We build our things not really to replace him and really do the work they do not want to do, or they feel it's critical. They have trouble to do it, and so it's really about supplementary. It's really about we doing something physicians want, but they cannot do very well, or they do not want to do it, or it takes too long time. They could not do it for each patient to the care to the level they should deserve, basically. Yeah. So it's very all the work here we do is the physician told us what to do, not us to decide what to do. Yeah, it's really trying to address their real need. Yeah, it's about service. We work with them very hard, very we really want to enable them basically to serve patients better. Yeah. Is that answer your question? We of course we do a lot of we do a larger scale clinical trials to how to model how they interact, how the human physician, how they interplay, how they use the machine result. Yeah, but in general, this is actually the task they ask us to do. Yeah.
Thank you. It's a really impressive collection of work. We're a bit over time, so maybe I'll just ask the audience to contact the speaker offline or through a private message if they have a question, okay? Thank you, Dr. Liu. Okay, so actually I'm the next speaker. So I will, I just bring up my slides. So my name is Joe Reinhardt. I'm a professor at the University of Iowa. We're a big public university in the middle of the United States. And I'm the chair of the biomedical engineering program. I'm going to talk about using lung imaging to study chronic obstructive pulmonary disease, but I'll also give examples of other important pulmonary disorders that we can study using lung CT. And I'm a shareholder. I'm the founder of a small company in Iowa that has commercialized some of this work. So this is my disclosure. Okay. So this talk is about the respiratory system. The respiratory system is pictured on the right. It consists of the lungs, the airways, the trachea, the nose, the mouth. It's a very complicated system. Obviously, it changes over time, so it's dynamic. I like to tell people that I describe it as a two-pump system. You have the heart pump, which beats about 1 time per second, and you have the diaphragm pump that moves air in and out every 5 to 8 seconds. So you have this synchronized movement of blood and gas that is required to make the respiratory system work properly. There's a complicated architecture of branching arteries and veins and airways. And there's a very delicate balance between the movement of the air, the movement of the blood, the diffusion characteristics at the alveoli that allow gas exchange to take place. And overall, the main function of the lung is gas exchange. So getting oxygen into the blood and getting waste gases like carbon dioxide out of the blood so that we can exhale. So it turns out that many diseases change the material properties of the lungs. So the tissue properties themselves change and become more stiff or less stiff depending on the type of disease. So for example, you may have heard of emphysema, which is a smoking-related disease that causes the lungs to become less elastic. So they become increased amount of compliance, and it becomes difficult for people with emphysema to exhale air from their body. On the other hand, there are diseases that cause the lung to become more stiff. One of the most serious ones is idiopathic pulmonary fibrosis, or IPF. So the normally flexible and pliable lung tissue becomes very stiff. It becomes hard to breathe air into the lungs and to the alveoli, so gas exchange becomes very difficult. There are other diseases or disorders like cancer, which can cause local stiffness. And more recently, we've learned that COVID-19 changes the compliance of the lung. In some diseases, the airways may lose their elasticity and collapse, especially during exhale, which causes obstruction, airway obstruction, which leads to air being trapped in the lung. And if there's air trapped in the lung, it's impossible to bring new air in. So overall, you have a reduced amount of lung function. One way to measure lung function is using what's called the spirometer, which is a device that measures flow. So it's pictured on the left. Somebody breathes through this device, blows through this device, you measure flow, you integrate that flow to get volume, and you can measure a couple key volumes. For example, the amount of air you can blow out in 1 second is called FEV1, and that's a good indicator of airway disease. The total amount of air you can blow out in a forced exhale is called FVC. And it turns out some of these parameters have been strongly linked to indicators of life expectancy, overall health. The ratio of FEV1 to FVC is what we use to diagnose some diseases like chronic obstructive pulmonary disease, or COPD. So COPD is a combination of chronic bronchitis, so inflammation of the airways, and emphysema, which is the destruction of the lung tissue itself. So COPD is a very serious health problem. It affects millions of people, and there are no real good treatments at this point. There are some experimental steroid therapies, but understanding COPD is a big healthcare problem. There's a staging system for COPD that uses those spirometer measurements I mentioned a moment ago, FEV1 and FVC. But in particular, we grade COPD from the mild stage, which is called the gold stage 1, up to gold stage 2 for moderate, gold stage 3 for severe, and gold stage 4 for very severe disease. So you'll hear me in this talk about gold staging, and that's this staging method for COPD. So the spirometer gives us sort of a global assessment of how the system is working, the respiratory system, but imaging can give us a much better picture, and literally gives us a picture. So on the right-hand side, you can see 2 CT images that show fantastic anatomic detail, picturing the airways and some of the blood vessels. The picture on the top is taken at full inhale, so we ask the subject to take a deep breath and hold their breath, and then we take an image. Image at the bottom is taken at exhale, so we ask the patient to blow out, hold their breath, and we take an image. Since the CT scanner measures density, we see a brightness difference between the top and bottom. The picture on the top has more air, so the tissue is less dense, so it appears darker on the CT. The picture on the bottom is brighter because there's less air at exhale. So analyzing these images tells us about the anatomy of the lungs, and I'll show you in a minute, it can also tell us a bit about the function of the lung. And the most important difference, I guess, between spirometry and imaging is the imaging gives us local information. It can tell us where something is happening and what the spatial extent of that disturbance is. So unfortunately, the methods to analyze lung CTs have not been very sophisticated. On the right-hand side of this figure are two examples from the George Washko lab at Brigham and Women's Hospital. And so there are two CT images here, and on the right side of each one is a histogram of the grayscale values. Turns out that many of the quantitative measures used today are still based on these histogram-based analyses, where you calculate the percent of the voxels below or above a certain threshold in the Hounsfield unit scale. So clearly not very sophisticated. Another way to look at this is to imagine thresholding the CT at one or two different Hounsfield unit thresholds. So in this illustration, we have three subjects in the three different rows. The two subjects on top are what I call gold zero subjects. So they are asymptomatic smokers. So we think there's probably some underlying disease, but on the spirometer, they don't show any disease yet. And you see if we threshold their CT, some of the voxels are highlighted, but there really isn't a large number of voxels highlighted here. So this third column is intended to show those voxels that are less than a certain density on the inhale CT, and we use this to characterize emphysema. And on the exhale CT, we can threshold that at a different density to identify trapped air. The bottom row shows a subject that's gold 4 subject. That's the most severe form of the disease. And you can see the lungs are hyperinflated. See how big the lungs are in this gold 4 subject compared to the two asymptomatic smokers. And you see when we threshold the CTs, there's a lot of emphysema and a lot of trapped air. So there's definitely a difference between the gold 4 subjects and the asymptomatic smokers on top. However, there isn't much difference in the patterns of these thresholded voxels between the two asymptomatic smokers. CT density doesn't tell the whole story. We believe that we can combine CT density with measures of lung biomechanics to get a better picture of what's going on in the lung. So going back to the inhale and exhale image pairs, the inhales on the right, this is an image at total lung capacity. Image on the left is at what we call functional residual capacity. That's the exhale image. If we can discover the transformation that maps voxels in the TLC image to the FRC image, and the transformation that maps back in the other direction from FRC to TLC, we can then associate motion and deformation locally in the lung with the anatomy. So essentially, we'd like to discover H of X and H inverse of X to come up with biologically plausible transformation functions that map the inspiration image to the expiration image. So obviously, image registration can do this for you. This is a typical image registration pipeline where you have a moving image, a deformed image, you have a similarity measure between them, an optimizer that updates the transformation parameters, and some transformation model that you have to choose. And so we need to choose the basis functions for the transformation. For example, it could be a B-spline. The cost functions for the similarity, it could be mutual information, and then some sort of optimizer to adjust the parameters. Once you've done that and discovered the H of X, now you can begin to analyze that H of X function to understand something about what's happening to the tissue locally. So for example, we can take the determinant of the Jacobian matrix, the matrix of partial derivatives of H of X, to come up with an estimate of local volume change. So the Jacobian determinant, which I'll probably just call the Jacobian from now on, tells us point by point in the image how that deformation field is expanding and contracting. So on the left-hand side, if you imagine a region in the inspiration image and a corresponding region in the expiration image, we can now associate a volume change with those two regions. And if we have a volume change in the lung, the only reason for the lung to change, lung tissue to change volume locally would be because air rushes in. And so we can associate the Jacobian determinant with function, and we can use that as a surrogate for lung ventilation. There are other biomechanical measures that are possible as well. In addition to calculating the Jacobian, we can calculate measures of shape change. And our group has proposed two of those measures. Ryan Amelon's PhD work described the anisotropic deformation index, or ADI, and the strain rod index, or SRI, that essentially describe how, say, a spherical shape expands or contracts to become a larger or smaller sphere, or an elongated hot dog shape, or a pancake shape. And so there's a spectrum of different shape changes that are possible as a region expands or contracts during respiration, and the ADI and SRI can help describe that. In some work we did with radiology department at Iowa, we looked at how the Jacobian was connected to other ways of measuring lung function. And we used non-radioactive xenon gas with CT imaging to measure what's called specific ventilation. So we have the subject inhale xenon gas. We look at the time constant associated with the wash-in, and that wash-in is, the inverse of that time constant is what's called specific ventilation. And on the left-hand side in 5 animals, we looked at the relationship between specific ventilation, which is on the horizontal axis, and the Jacobian determinant, which is on the vertical axis. And you can see there's a pretty nice linear relationship with good correlation coefficients between the average Jacobian and the average specific ventilation, which gives us some confidence that there's a sort of physiologic significance to calculating these biomechanical parameters. So in my opinion, the mechanics is a very rich source of information compared to these threshold images on the left. So if we look at what the Jacobian and ADI and a strain map look like for these subjects, again, the gold 0 subjects are the asymptomatic smokers. They're in row 1 and row 2. And the gold 4 subject is the most severe form of chronic obstructive pulmonary disease. So the color scale here ranges from the reds being high to the greens being medium to the blues and purples being low. And so this is sort of a, I guess, a qualitative comparison because we use the same color scale for all 3 of these columns. But the Jacobian is in the first column. So red shows regions of very high expansion. The yellows and greens are regions of moderate expansion, and the blues are regions of much less expansion. So immediately you can see a big difference between the Jacobian map for the gold 0 subject and the Jacobian map for the gold 4 subject, which is not surprising because of the amount of trapped air and emphysema in this subject here. We also see, though, there are differences between the 2 gold 0 subjects. We think from the CT density images that they're pretty similar, and the architectures look very similar on the left, but the Jacobian maps, the ADI maps, which tell us about isotropy of the expansion, and strain, which tells us about essentially length changes in the lung, those maps are different for the 2 gold 0 subjects. So there's something going on here that's not described well by the density images alone. So we looked at a bunch of subjects, 247 subjects from a clinical trial called Spiromics, which is looking at outcomes in COPD. So this is an NIH-funded clinical trial. We looked at the CT images for these subjects. There are about 50 in each of the gold stages from 0, 1, 2, 3, and 4. We did segmentations to identify the lungs, the fissures, and the lobes. And we used image registration to match the TLC, that's the inhale image, to the RV, which is the exhale image in that case. RV stands for residual volume. for the baseline visit for each subject. And then we calculated these biomechanical measures for these subjects to see what relationship there was between the spirometry and the biomechanical measures. So here are 5 different subjects in columns 1 to 5, gold 0, gold 1 up to gold 4. Remember, gold 0 are asymptomatic smokers. The top row is the Jacobian map. So you can see again, the reds are regions of high expansion. So there's lots of volume change in this subject, lesser volume change in the gold 1 subject, which is mild disease, and much less change in the gold 3 and gold 4 subjects. So hardly any volume change at all in the gold 4 subject. And that subject is probably having difficulty moving air in and out. In addition, we see there are variations in ADI, the anisotropy map, and the SRI. And so we can use machine learning frameworks to analyze these patterns or other statistical measures to summarize these results. Looking at the Jacobian, if we plot the average Jacobian across the population for these subjects versus gold stage, we see a decreasing amount of volume change as the disease increases, not surprising. This is for the whole lung on the left-hand side, and then there are 5 lobes in the lung. And so this is the data for each of the 5 lobes: right upper lobe, right middle lobe, right lower lobe, left upper lobe, and left lower lobe. So you see that same trend holds true. And we looked at coefficient of variation for the Jacobian, and we see that there's less coefficient of variation as the disease increases. So the lung is expanding less, and it's becoming more homogeneous over time as that disease progresses. And in a similar way, the anisotropy decreases. So the lung is becoming more homogeneous as the disease progresses. One of our graduate students, Amanda Pan, also looked at robustness of these measures to choice of registration algorithm. The results I've shown you so far are using a B-spline algorithm developed by our group with 2 cost functions. One of them looks at the sum of the squared tissue volume difference, essentially doing voxel comparisons and measuring the fraction of tissue at each voxel, and the sum of the squared vessel matching distance. So making sure the vessels line up in the registration problem. Amanda looked at 3 other algorithms, geodesic density regression, which is a method that was developed at Iowa, the greedy symmetric normalization method, which is from University of Pennsylvania, and the varifold algorithm from Stanley Durlman's lab. So 3 very different approaches, different deformation models, different cost functions. And what she was able to show, there's a lot of data on here, but focusing maybe on just the lung column, each one of these rows is for a different algorithm. So the B-spline algorithm on top, the GDR, geodesic density regression, the second row, the greedy SYN, and the varifold at the bottom. And so while the distributions are slightly different, we see the general trends are the same. The means are decreasing as the gold stage increases, meaning that each of the algorithms is showing less volumetric expansion as the disease increases in these subjects. So it gave us some confidence that all 4 methods, even though they were slightly different in choice of basis function and similarity function, are producing essentially the same results. We also went on to look at how the biomechanics can explain the spirometry. So for the 4 different algorithms, you can calculate the R squared, and we see that each of the registration methods produces explains a large part of the variance in FEV1 and FEV1 over FVC. So the R squareds are about 0.7 for this. So it looks like these algorithms are behaving in a similar way. And then one of my students extracted statistical features from the Jacobian and ADI maps and used that in a random forest classifier to detect airflow obstruction with using a classifier. So the AUCs for that are well above 0.8, and looked at the problem of classifying gold stage, again, with AUCs close to or above 0.8, which is sort of state-of-the-art work compared to other things that have been published. It turns out we can also learn something about what's happening to the normal tissue in COPDs and the biomechanics. So in this figure, we looked at subjects in the COPD gene clinical trial, and we used the image thresholding to identify the normal voxels, which are marked in green here, and the fraction of emphysema voxels, which are marked in red. So you see in the gold 1 subjects, most of the voxels are normal, very few emphysematous voxels. And then as the disease progresses, there are fewer and fewer normal voxels and more emphysematous voxels. And then for each of these subgroups, the normal voxels and the emphysematous voxels, we can look at the mechanics. So for the same gold 1, 2, 3, and 4 stages, we looked at the mechanics in the normal tissue, the green, and calculated mean Jacobian determinant. And we looked at the mechanics in the emphysematous voxels, marked here in red. So we'd expect that the average Jacobian determinant should go down in the red voxels, the emphysematous voxels, because we'd expect there to be less expansion as the lung becomes more compliant due to the disease. However, what we discovered was the red voxels decreased in Jacobian determinant, and the green voxels decreased as well, and in fact decreased to sort of essentially a similar behavior in the most severe form of the disease. So that led us to conclude that in COPD, the normal voxels are not behaving normally. They're either pre-emphysematous, or maybe they're being mechanically compromised by the nearby disease, and they're unable to expand and contract normally. And so this was work that we did with a group from the University of Alabama, Surya Bhatt, using the COPD gene data set, a large nationwide clinical trial. I want to give 2 other examples of how we can use this technology, and then I'll finish up. First of all, COVID-19, obviously a huge healthcare problem around the world. We had a smoking cessation study where we were recruiting normal subjects to come in for a CT scan to compare to smokers. And we had a subject come in, a 30-year-old male, who had a CT scan that looked like this. So this is the baseline exhale image and the baseline inhale image, and in the coronal view and the sagittal views. And so you can see there's an unusual inflammation or consolidation that it's developed in the left lung. So the supervising radiologist sent this person for a COVID test, and it turned out they had COVID. So this is a COVID infection or inflammation. With the TLC, with the inhale and exhale image, we calculated the Jacobian determinant maps, and they're pictured on the right-hand side. And so you can see in the left lung, there's a corresponding dramatic decrease in volumetric expansion in that region of inflammation. And in the coronal view, you can see the disturbance extends very far down from the location of the inflammation toward the base of the lung. So this is this huge mechanical derangement that happens due to this inflammation as the body's trying to respond to the infection. After 30 days, we brought the subject back for a follow-up study, and you can see the inflammation has resolved. So the COVID infection is gone. It's not visible on the coronal view, and it's apparent from the mechanical maps that the mechanical disturbances have been completely eliminated. So it's interesting to think of how we could use these functional measures to track subjects over time and see their progression as the mechanical behaviors in COVID sort of run their course. Another important area for applying these methods is in radiation oncology, where we use radiation, high energy radiation to kill lung cancer. And this is work with the University of Wisconsin-Madison, where we use the Jacobian maps to identify regions of high functioning lung, with the thinking that the radiation therapy plan can be built to spare or avoid the high functioning tissue as much as possible So we can treat the cancer, but reduce the amount of complications and problems for the subject long-term. So here's an example of a conventional radiation treatment plan on the top. So these ISO contour lines show dose, radiation dose that's going to be delivered to kill this tumor, which is located right here. And in the background, we've overlaid the Jacobian determinant maps in sort of the red color. So we can see, these regions of high function here in the left lung, and then some regions of high function in the right lung, but they're going to be hit by this radiation dose on the order of 15, probably 10 to 15 gray for sure. So we can build a plan so that the dose is still delivered to the tumor, but avoids the highly sensitive nearby lung tissue, which is really important tissue to keep that patient healthy. And so the bottom is what we call the functional avoidance plan. So we've pushed the dose away from this important lung tissue here in the right lung to spare this tissue from damage during the therapy. And so the clinical endpoints for a study like this, we have 48 subjects that have been recruited to this type of study so far. We look for things like pulmonary toxicities, so radiation pneumonitis. Dyspnea means shortness of breath. Cough, hypoxia means reduced oxygen in the blood, or any grade of respiratory failure or negative outcomes. And the control arm, those are people that would have gotten the conventional plan as illustrated on the top, have a complication rate of about 27%. The experimental arm, those are people that get our customized plan that avoids the high functioning lung tissue. We have a complication rate of about 8%. So far we've had about a 15% reduction in complication rate by building these personalized therapy plans. So that's the end of my, the main part of my talk. Just in summary, I've described how we can use CT imaging plus image processing to examine tissue biomechanics, to characterize local tissue properties, infer material properties, stiff versus compliant, and use that as a surrogate for regional ventilation. That local assessment of biomechanics using imaging is better than spirometry because it's much more local as opposed to global. There are good correlations with other functional measures like xenon CT. Others have shown that hyperpolarized MRI also correlates well with these ventilation maps. And there are strong correlations with measures of COPD and emphysema. We can use this to assess COPD, emphysema, asthma, COVID, cancer, for guiding therapy for emphysema or asthma, for guiding radiation therapy. And while I didn't have a chance to talk about it, you can also develop strategies for running the mechanical ventilator for COVID using this type of information. There are some things to keep in mind. You need a fast and robust image registration algorithm that can work across these big volume changes. And there have been some really promising deep learning approaches proposed for this, but so far that, in my opinion, they're handicapped by some shortcomings. You also need longitudinal registrations for follow-up studies that are resilient to changes in disease. And you could do machine learning on these biomechanics maps, and we're trying to do that to phenotype subjects to figure out subgroups of subjects which have particular characteristics that make them suitable for one type of therapy versus another. But overall, my hope is that this type of work will lead to a much better understanding of the normal and abnormal lung physiology. So this is my research group, some faculty from Iowa, Wisconsin, some postdocs, and a number of graduate students. And this work was supported by the NIH and by a gift from the Roy J. Carver Charitable Trust. Spiromics was supported by a contract from NIH, and the lung function avoidance work for radiation therapy is a clinical trial at the University of Wisconsin-Madison. So thank you for your attention, and we're close to being out of time. I can answer a question or two if it's quick. Okay, no questions. So I'm gonna thank you once again, and I will introduce our next speaker. Give me just a second. Okay. Okay, I'm very pleased to introduce our next speaker, Dr. Tanveer Syeda Mahmood. Dr. Syeda Mahmood is an IBM fellow and chief scientist and overall lead for the medical Civ Radiology Grand Challenge project at IBM Research Almaden Research Lab. Dr. Syeda Mahmood will be the general chair of MICAD 2023. And the title for her talk is AI for Chest Radiographs, Passing the Turing Test, which sounds very interesting. So please go ahead, Dr. Syeda Mahmood.
Oh, can you all hear me okay?
Yep, we can hear you just fine. Thank you.
Thank you for that introduction. I am going to stay off of video to save bandwidth since I'm doing a live presentation. I just wanted to say hello to everyone first. And let me share my screen. Let's see the code. No, that's not what I wanted to show. Okay, people can see my screen? I'm assuming yes.
Yes,
okay.
Yep, we can see that.
Okay, good. So I'm here to talk about the results of our Medical Civil Radiology Grand Challenge project that has been running for some time. And hopefully this will give you a sense of what does it take to pull off a Grand Challenge project that runs for several years and aims for a very high goal. And in this particular case, it was to essentially, although we didn't call it the Turing test at that time, but in the end, what we ended up building is something that produced a capability that was virtually indistinguishable, at least for the test cases we tried. So before I go on, I just wanted to acknowledge my team. This comes with the truly interdisciplinary effort from radiologists, the majority of the involvement from clinicians, but from the radiologist community, both internal and external radiologists around the country. And my team members who are medical imaging researchers. Some of you may be already familiar with these folks who regularly publish at MICAD. So let's look at what's the Grand Challenge. The Grand Challenge we took on, we started back in 2013, 2014 timeframe, was to look at developing capabilities for assisting radiologists and making good cognitive clinical assistance. Now, this concept has now been adopted and is already in many products. Even our own Watson Health imaging business has utilized the technology from our group. But the challenge that we took on was to build a capability that was provably good. And in this particular case, doing a full preliminary read of a modality directly from images to report. And that was the grand challenges we took. Now, in this particular case, the focus was on chest X-rays. So you may ask why chest X-rays? And I think enough work is now happening in chest X-rays. But back when we started the challenge itself, this was not as popular. But from the point of view of preliminary reads for doing this, these are, even though this is a common modality, they are also one of the hardest to interpret because of the low resolution in the imaging and the cognitive biases. So if you were to look at these two and figure out which of them is actually a nodule, this can be difficult for machines. So in such sense, the idea being that if you could produce a preliminary read, which means going from an image such as this to directly a report, this could potentially assist in expediting the clinical workflow as we go. So the way we envisage is that in future you may have read services that can intercept at any stage of your clinical workflow, from imaging, assisting the technologists to make sure that the imaging itself is of good quality, to ordering the work list of a radiologist so you can interpret them, the more urgent cases first, to actually skipping the dictation process itself, producing a preliminary report report that the clinician can still correct and sign off. So we see this as a way of disrupting the current dictation-driven process if machines got good at producing high quality reports that reflect as many, all the possible findings and flag as few incorrect findings. Now, just to give you the type of capability we reach, you can see a bit of a demo over here. I don't know if people are able to watch this video, but here's an image. You just feed it to the service, and the image is being analyzed, and a report is being generated here. And you can do this by picking any of your images from your packs and submitting to this service and producing a report as such. So in the interest of time, let me move on to the rest of the deck. So you may say, why is this a grand challenge? So the first question that we have to answer is, if you're saying you're going to do a full preliminary read, you have to be able to cover as many findings as the radiologists do in a read. Then the question then comes back to how many findings are there? It turns out that this question has not been adequately answered. And the majority of the work since we started as well has also been only restricted to a small number of findings, like 14 findings or 20 findings and so on. But we don't have a good answer of how many findings are really there and how can we be sure that we've completely characterized them. The second thing is you need to be able to be as accurate as radiologists, at least the entry-level radiologists, in detecting the findings. But how can you be sure what are the radiologist accuracies? Are there studies that that actually document this? And so this itself was another problem that we had to face. The third was to actually look at, when you say you're describing the as good as a radiologist report, we need to be able to characterize the findings at the same level of granularity that we did see them. And here are some examples of actual sentences from reports. And you can see that there are fine-grained descriptions of findings that describe the laterality, the location, the severity, and so on. And if you were to look at the findings, and if you assume that there is going to be a large number of findings to cover, you still need to develop AI algorithm that has that kind of specificity and sensitivity, such that what is actually mentioned in the report is typically only a handful of findings, and we should be able to do that high level of selectivity as well. And overall, we need to be able to produce a report that is of adequate English language description and quality. So if you look at this, the problems to be addressed are both on the radiologist side and on the machine side, because as I mentioned, there isn't even a catalog of all the findings or a benchmark of what the ground truth would be that to compare against and so on. So there's a lot of work we had to do to develop the benchmarks, develop the catalog of findings, and this is where the clinician's involvement was pretty heavy. And then we also needed to develop machines with the capabilities to detect and characterize these findings. So if you look at a typical workflow of work involved in this, there is a lot that, and here's a few of these that one can, and many of you can relate to, have done one or more of these tasks. Obviously, it's not possible for me to go through all of them, so I'm going to touch on a few of these topics in a very brief way and leave some time if there are time for questions. So let's start with the first one, where, as I said, we had to first of all characterize how many findings are there. And as I said, most of the approaches have focused on the 14 findings that were initially released by the NIH dataset, and a subsequent labeling by Chexpert or Mimic or all have also kept to those. And some proprietary organizations have done a larger range of findings, but it's not possible to find them in the public literature that we can actually utilize labeled datasets. So our first task was to build a chest X-ray lexicon that allowed us to catalog these findings, and this is something that we subsequently utilized to our advantage. So for cataloging the findings, one would have to look at what is the radiologist process. So if you look at a radiologist process, the initial interpretation first to see if the image itself is ready for interpretation, which is a technical assessment problem. Then we need to know whether it's an AP or a PA or a portable view, as it establishes some bias as to whether you are in an inpatient or in an outpatient setting. If you are in an inpatient setting, you have to detect if there are any tubes and lines and whether they are properly positioned, or there are any implanted devices or artifacts that need addressing. If you look at the anatomical abnormalities, you have to also detect all the major findings in major areas of the chest and any disease that is implied for that, and you finally generate a report. So this is typically a workflow of a radiologist and showing you the many types of findings that one need to detect. So this gave us the first hint to go ahead and try to catalog the findings as we go. So we collected a team of radiologists and used a process that was a combination of knowledge-driven and a data-driven process from actual mining of reports to develop the largest catalog of findings, as you can see from this chart. This work has been described in the AMIA conference last year at the American Medical Informatics Association, and the technology itself is described in detail there, but at a very high level, we used a clinician in the loop process of mining radiology reports and having a reinforcement learning approach, be in the loop, utilizing word-to-vec representations for finding similar terms within radiology reports and having the clinicians accept or reject the terms as synonyms for the particular core disease characterization that we started with. So as a result of it, the lexicon that we developed has about 11,900 or so terms and about 237 lexical concepts, about 78 core findings and 26 clinical categories. Here is an example of the core findings, about 72 of them listed over here or so. And the details of these has been published in our JAMA paper last year in October issue, so you can also get more details on this day. So that is about the findings itself. The next step was to acquire data that was representative of multi-institutional data sets representing several demographics in the population and handling different prevalence distributions of these findings as such. So in terms of acquiring the data sets, we, at this point, based on the access we had, we looked at data sets from NIH that were supplied without detailed labels like these. So we had to relabel some of these images, and about 14,000 of them we could relabel by reproducing reports out of them. The next was the MEMIC CXR data set that is now in public, but at that time when we started, we were part of a consortium, and we got access to about 500,000 images from them. And the Indiana collection, as we see. And we also kept aside a certain two sets of data for experimentation purposes that did not have an overlap with the training sets for the machines. And this included a data set from a completely different demographics from the hospitals in India. You can see the prevalence distributions of the various findings over here, and you can see that the comparison study data set that we said had quite a different prevalence distribution for testing. It's to test the robustness of our models. Okay, so we got the data set, but none of them came with labels nor the fine-grained descriptions that we wanted to generate. So our next process was to be able to actually automatically label these data sets. The manual labeling process that we first adopted for the NIH reports took about 4 months, and at about 36,000 images, considering different viewpoints, was what we could annotate. And since we had 1 million or so images to go, we said this is not going to scale. So we came up with an automatic labeling method that mined from reports. And I know a number of other approaches have taken automatic labeling approaches as well. So the way you will see them is many of them are machine learning driven or vocabulary driven. What our approach actually is a combination of machine learning, vocabulary, and language modeling, as we go through a bit of a description over here. The first approach that uses a vocabulary from the lexicon directly to to locate these findings can do a course level description of findings. And this one we have evaluated on many data sets, and we published this work last year, which shows that it has pretty good precision and recall on the collections that we have ground truth and tested from clinician ground truthing of these reports. In fact, if you look at the F1 scores comparisons for the findings, and the blue findings are those that are in published list of findings, but as we go, this is a distribution that shows that much larger coverage and also the kind of F scores we are able to maintain in comparison to the state of the art there. Again, this is available in our AMIA paper last year. So that only characterizes the coarse findings. So we would know pneumothorax, but we would not know which lung has pneumothorax or which portion of the lung has pneumothorax. So if you want to go to the fine-grained findings level, we actually have to do a further analysis to be able to characterize descriptions of these findings. So we actually came up with a catalog of what descriptions are actually found in reports. And you can see over here, laterality, location, size, and so on covered over there. So this leads to the next question, the first question of how many core findings we were able to answer by clinicians. But when you go to find finding, there are thousands of variants, hundreds of thousands of variants, and having clinicians go through this cataloging process would have taken us 10 more years. So we came up with an approach that actually tried to use language analysis techniques. So if you take a report such as this, which says clear lungs without evidence of pneumonia, we already know from our lexicon that pneumonia is a disease, lung is an anatomy, clear is a description of a finding, and there is also presence of negations. So utilizing this information and using an English language parser that was adapted for clinical vocabularies, which is called the ESG parser, that is behind the Watson technology, we were able to create a parse tree for this, and then use a dependency parse tree to actually group successive core findings and adjectives and modifiers that describe these findings together to produce findings from a single sentence. So a sentence like clear lungs without evidence of pneumonia would generate an anatomical finding, which is a negative finding in this particular case of a clear lung. And from the point of view of a disease, there is a finding of pneumonia, but it's also a negative evidence. And the pattern itself can be characterized in this 4-part form as such. So, and here you can see over here from a single sentence, we can generate multiple findings as well in this particular context. So this work is again described in detail in our EMEA paper last year, which won the Homer Warner Award for our best paper. So from there, we can, starting from an image like this, if we could had a label of this type, it is relatively easy to generate a sentence that says left basal atelectasis. Similarly, if you had a detailed description of a finding of this type in a label form, it is possible to describe sentences of these types. We actually did an analysis of about 3,000 sentences from about 2,900 reports to see how accurate is our fine-grained descriptions. And as you can see over here, less than 4% error overall, and the majority of the errors were in the negation sense detection, which remains to be a challenging problem in text analytics. Okay, and when you do the full characterization, we can form a tree of this type, and you can see that this represents about 83% coverage of all fine-grained findings, and about 457 fine-grained patterns that we retain that gives a good span of the 100,000 or so findings that we found from about 220,000 reports as we go. Okay, so now we have labeled data sets describing fine-grained findings as discrete labels. So now the question was, how do we build models that are able to handle such large number of findings and still retain the quality of recognition? So in this particular case, we looked at building first specialized deep learning models, which we have published in literature, such as the tubes and lines classifier in MICAD, or the technical assessment model and SPI and so on. But the goal was to develop a general model that covered all the findings. So we, after experimenting with several different network architectures, we settled on an architecture that has a combination of many good features. One of them is a multi-scale representation of the image using feature pyramids drawn from pre-built networks. The other is a dilated block that allows us to represent higher levels of abstraction as we go through findings at different regions and expanding to multiple regions. And then a global square pooling or bilinear pooling that instead of shrinking as you know, in a convolutional operations, the sizes of the filters are such that the image size shrinks, and by the time you get to the flattening stage, you have a small vector compared to the raw sizes of images we look at. So this particular step, we did actually a global square pooling, which actually expanded the feature set before you did a dropout and then a dense classifier as such. The network details are also described in our JAMA paper, but this is the 3-step operation we used for this purpose, and the details of the machine learning model configurations are given over here. So that gave rise to the machine learning model. We'll show you how that model performs when we get to the clinical studies section of it. So last step of the problem was to actually generate the report from such a model that described the findings as such. Now, this is where, as you know, there's a lot of work active going on in report generation by machines, and the predominant approach that is taken is a machine learning language-driven techniques. And in fact, you can see some representative work here. Typically, they start from images and try to generate labels. And from the labels, using any surrounding textual during training, use a language generation approach, variants of LSTM or RNN and so on to actually generate the report. So the report essentially is generated by language transformer type techniques, and it is seeded by image recognition from image findings. And there are variants of this, of course, but the general approach is that. And so one of the major issues with this is ensuring that the report is clinically correct, describes all relevant findings, and sounds reasonable as well. So those three problems are still outstanding as we go. So our approach to this was quite a different departure from these existing techniques. What we did was, first of all, try to describe the findings in a coarse way, such as elevated hemidiaphragm or cardiomegaly. So one model to characterize the coarse nature of findings, another model to characterize the fine-grained nature of findings, which for the same elevated hemidiaphragm will now say elevated right hemidiaphragm mild, which is the label itself, and then go from there directly to a sentence that says the right hemidiaphragm is mildly elevated. And so this uses a technique that is familiar to radiologists in the way they have pre-canned sentences coming from their dictation systems. However, instead of pre-canned sentences, we actually detect the relevant sentence based on the findings by creating a large database of sentences and using a document retrieval style approach as well. So the overall approach would be starting from a prior report. We create actually a database that extracts all the fine-grained labels through this automated labeling process to characterize fine-grained finding vectors. And from these vectors, we extract the sentences per FFL vector and reverse index to know which sentences were contributing to these vectors, and essentially create a ranked sentence database and a ranked report associated with this and during the database preparation step. Given any chest X-ray for during inference, you just take the report and learn the fine-grained labels from it using the model that we build, predict the fine-grained label vector, and then use this retrieval engine to actually retain the relevant sentences, and from there generate the report. Now, during the sentences, we also do some wordsmithing to make sure that the sentences are complete and so on as we go through. So the overall report generation system, therefore, is a fusion module that uses a coarse and a fine-grained labeler and a retrieval module that works off of a database. And you can see here some of the details of these in terms of the database preparation step. About 5,000 sentences are guiding the analysis of each of these findings report generation step as we go through. Now, how to measure that this is a good quality report is also difficult, because most of the measures out there are based on lexical match or some weak semantic matches through scores such as BLUE or Meteor. However, to compare to other approaches, we had to stay with that methodology. But first, in terms of the detection of the findings itself, for coarse and fine, you can see that we have about weighted average AUCs of these. And you can see the depth at which we can now predict from an image findings such as moderate pleural effusion in the right lower lobe as well. And here are some ROC curves we got for the fine-grained descriptions of these findings. This work, by the way, has been described in MICAD last year. So the automated report generation generates sentences of this type in comparison to the ground truth. And you can see that the finding is captured, but also described in an appropriate way. We try to do a comparison with many other methods in terms of how the English language description and the sounds from this using the same scores that they use, such as BLUE score or the Meteor score or the Rouge score. And you can see that this is still the highest, I think, in terms of performance across the board for all the, even though the language generation methods are not the best way to assess our model. There is it still beats the state of the art as of last year. Now, of course, there'll be new approaches coming in this year, so we'll see how that goes. All right, so the last step is now, how do we know how good we are and how can we prove that we have reached a certain capability? So as I said, we needed to conduct clinical studies to measure the radiologist performances by, first of all, developing a ground truth data set that radiologists themselves could agree on is the right data set to evaluate them as well as machines. So in that sense, our evaluation process was split up into the radiologist communities, a set of community that developed the ground truth data set. And these are the senior radiologists who did a triple consensus ground truth generation process with adjudication. Then we had a radiologist committee that acted as the attendings, which are the senior radiologists that assist radiology residents and that assess the radiologist residents. And then we had radiology residents as representatives of entry-level radiologists that we could compare to, and we use our 3 residents as our comparison as such. Okay, so the 3 studies we performed were first for normal and abnormal discrimination. How well does this come? And on completely different demographic data sets. Then we did a comparison on discrete preliminary reads, followed by preliminary report quality Turing study as we go. Let me quickly go through these. So in the normal abnormal discrimination study, this was conducted at the Deccan Hospital. It's a 600-bed hospital and we basically collected a definition of normal patients in this case, but those that had no clinical follow-up after a chest X-ray was declared normal by their radiologists. And so in the retrospective phase, we collected data from them for evaluation. And in the prospective phase, we actually ran this normal abnormal discrimination surveys and had the clinicians themselves use it for several months to record the performance as we go. So the data set essentially had about the training data set came from our MICAD and NIH collection that were auto-labeled by machines as normal or abnormal. And based on that training, we went back and used the radiologist reports that their clinicians at Deccan said were normal, abnormal to get to the classification. So from the ROC curve, you can see that if you pick a point on this ROC curve, we can essentially remove 1/3 of the normal images without missing a single abnormal case. And that tells you that there could be a good potential application for this for normal abnormal screening itself. And then the precision recall curve also is showing you a high level of performance there. All right, so that was on the discrete normal abnormal discrimination. The next one is on discrete label comparisons, and the study was described in our JAMA paper last year. So there are 5 radiology residents that we compared to. These are our 3 residents, about nearly 2,000 chest X-rays, giving about 400 chest X-rays per radiology residents. And then we did basically their individual radiologist performance, average radiologist performance as measured, and then the agreement with the machine reads from the CAPA scores and the average image-based precision and recall measurements. And there is a lot of detail in that paper that you can read, but you can see the AUCs per finding cataloged in here that shows that the sensitivity specificity numbers and the positive predictive values are roughly in similar ranges for machines. In fact, if you do a comparison of the ROC curves, you can see cases clearly where the machines are about the same. On the ROC curve, the radiologists are right on the ROC curve. But there are cases where the radiologists are better, and then there are cases where the machines are better as well. In fact, if you look at the average CAPA scores, you can see the variation is pretty close in many cases. But there are cases where the radiologists are much better, and we'll show you that. And then we also did the variation within residents. Also, there is comparison studies that show differences. Overall results that said that Basically, this is a significant result from the discrete comparison study that said that there is no statistically significant difference in sensitivity, but the specificity-wise, the machines were actually better, which was a bit of a surprise to us, since the number of false positives, as you know, for machines is quite large when you just do it purely as a machine learning model building exercise. But because we augmented this with a report generation and utilized the information about the average number of findings that are typically present, we were able to control the selectivity of the machine to be on par with the radiologist as such. So overall, this meant that they are roughly on a similar level of performance. And in fact, if you look at things where machines are similar, here are the findings that we found they were similar. And there are findings where the machines outperform the radiologist, and there are many cases where the radiologist outperform the machine, and these are the difficult findings associated with tubes and lines and their placements, as well as nodules and certain things that were also a little bit of a surprise as to why the machine missed it. So the last study is to bring this whole thing together to now the prime time testing in terms of how does the machine produce, are the reports produced by the machine good enough in quality that it's virtually indistinguishable from the radiologist reports. So to conduct this study, we actually had radiologists write reports for these same 2000 chest x-rays, and then we had machines generate these reports. We intermixed them and we showed the reports to attending physicians and asked them to assess the quality. Of course, they were blinded, so the clinicians did not know which report was produced by who, and they were asked to rate the quality using the ACR radiology read criteria. And if there was any missed findings, they cataloged those as well, and we asked them to give a qualitative score. The study was done in RSNA 2018 as to get an initial level of performance and capabilities, based on which we modified our algorithms and upgraded with data sets and so on. So the final study that we did was at a symposium in which we had 3 famous radiologists. I think many of you may be familiar with them. Elliot Siegel, Curtis Langlotz, and Chuck Kahn. And they sat in separate reading rooms, dark rooms, and one of them was given machine generated, one of them was given radiologist generated, and one was given combined. But none of them were told who got what. And we were live observing what they were rating their reports by, and these curves were sort of going up. And then we finally revealed the results to the audience. And as you can see from here, here are the reports manually, and here are the reports. These are the radiology resident reports, and these are the automatically readed reports. And you can see that the statistical performance is similar, but also there's a little bit of an edge to the machine in the quality of the reports. There are more excellent quality reports. And the score ranges also show a skew in the higher range for them. Now, this was because of the experiment and because of the time limitation of it, we could only evaluate about 166 reports in the 1 hour time we gave the radiologist to do. So this is one of the caveats to see. So overall, to see I hope I gave you an indication of what does it take to do a grand challenge over multiple years of research, addressing a problem end to end, to think of a capability that is meant for practical clinical workflows, and honing the techniques to the level of sensitivity and specificity needed for clinical workflows. We are going through a commercialization phase of this technology, but if anyone is interested in learning more, I'll be happy to talk and point to relevant papers on this. So here are some publications from this work.
Thank you. Thank you, Dr. Sierra Mahmood, for a very interesting talk. So if there are any questions, please type them into the chat or Q&A. Or really at this point, you could just unmute your microphone and ask the question. So I do have a question. it seems like the focus on chest X-rays is because how common that exam is and how much data there is available. Are there other places this technology could be translated to without a big burden?
Well, so some of the fallouts that came from there was, are there automated ways of building lexicons that would capture the findings much faster instead of spending years with clinicians trying to go? So that's one of the active research areas on the tech side. Similarly, the automated labeling methods are the scalable methodology. So I think going forward, this would be the standard approach that if the text analytics is of reasonably good quality through verifications that you do, you can think of scalable ways to building models quickly for, since reports are available for pretty much all imaging, right? So whether you're talking about cardiology, radiology, neuro, and so on. So you're going to have reports. So, but to understand those reports, you need the associated lexicons or the vocabularies. Doing a totally machine learning approach, people are trying those as well. But right now, the comparison has always shown that the vocabulary-driven approaches beat them hands down because of just the knowledge that they incorporate. So if there is some way in which this technology could, take the next step in there, that would, so you can imagine in future, you won't take that long to build new models for new body parts or new anomalies because we have a scalable method. So that was one of the learnings from there, that we were able to label 500,000 images in a matter of 4 or 5 days, including verification.
Right, that's an amazing amount of work. Wow.
Yeah. So those are the things. The model building exercise, this is a whole image approach we took, which was and I was expecting one of those questions is why not take a regional approach? This was a learning from us that when you have such large scale number of findings, the regional approaches are not going to work as well. And it is better to go with a more robust whole image approach, relying on statistics from what is seen in typical reports to focus on which findings are important to call on, which are critical findings. If you see the evaluation methodology for the Turing test, use the ACR review criteria, which are important to get some critical findings right. And if you don't report a non-urgent findings, it's okay. So we took hedge the bets on which findings are important to characterize and do well in those that are very prevalent. Also, we wanted to do well on those and those sort of things. So these are some engineering good ideas that you can incorporate with deep learning to do practical solutions in that space.
Okay, I don't see any more questions. So thank you again, Dr. Syeda Mahmood, for an excellent talk. So that's the end of our program. I guess let me just take a second to thank all the speakers, especially the keynote speakers for your excellent talks, and also the speakers from yesterday as well. Thank you for your presentations. I want to acknowledge the conference chair, Dr. Ryudong Su, and General Co-Chair, Professor Yudong Zhang, and send my congratulations to them for a successful meeting. And I just want to say that I hope that next year we can all meet together in person. So this marks the end of the meeting. Thank you, everyone.
Thank you. Thank you, Joseph. Thank you, Professor. Thank you. And I'll see you next time.
Yeah. Bye-bye.
Bye.